Hi, and welcome to this learning path on building blockchains using Hyperledger Fabric. We will start off by laying the context for building blockchains with Fabric by briefly summarizing what exactly blockchains are, why they are so appealing for many different industries as a way to record transactions, the different blockchain implementations available in the market right now, and where exactly Hyperledger Fabric fits into that picture to provide a blockchain solution which is truly enterprise grade. We will now have a quick overview of blockchain technology, but first, we can take a look at the prerequisites for this learning path. It is assumed that you already have some fundamental knowledge of blockchain technology because we will just be providing a brief summary rather than a detailed explanation of this. If your knowledge of blockchains is a bit rusty, however, then you don't need to worry because the summarize will refresh your memory. Another important prerequisite is that you should have some knowledge of Hyperledger, and specifically of Hyperledger Fabric. You should have some idea of the different components which make up a Hyperledger Fabric network, which include the ordering service, certificate authorities, organizations which may have one or more peers, and so on. And once again, even if your knowledge is a bit rusty, there will be a quick refresher in this course. And finally, another crucial element for this learning path is some prior programming experience. We will be writing smart contracts using Golang as well as Node.js, and we will later on be exploring a custom modeling language. There will be plenty of configuration files in YAML as well as JSON format, and we'll also be building a web application. It will help if you have some experience with JavaScript and maybe even Golang, though it is not strictly necessary. To do the labs in this course, you should be able to follow what is defined within the code and then perhaps do some independent research if required. And this, of course, will be far simpler if you have some background in coding. Well, that's it for the prerequisites, and we can now dive right in to our overview of blockchain technology. So how exactly can we define a blockchain? Well, one way to put it is that a blockchain is essentially a list of records, and that these records are stored across a sequence of blocks, and these blocks in turn are chained together into a sequence using cryptography. In such cases, it is always best to visualize a blockchain. So here we have a list of records, and you will notice here that we have an ordering of these records from 0 through 8. The goal is for us to be able to store all of these records, which maintains its sequence, but also ensures that they cannot be tampered with in any manner. The way blockchains accomplish this is by splitting up the records into a sequence of blocks. So the 9 records which we have can be broken up into 3 different blocks of 3 records each. Note here that there is a sequence both within the block as well as an overall sequencing of the blocks themselves. To maintain the sequencing of the blocks and in a manner which also ensures that they cannot be tampered with, these blocks are chained together. And the specific technique which is employed in order to ensure this tamper-proof chaining is by using a cryptographic link. A cryptographic link means that each block within the blockchain will include a number of bits of information, but the crucial one is that it will include a cryptographic hash of the previous block in the blockchain. The block will, of course, include a lot of other information as well. This could be a timestamp to indicate when exactly the block was created. The records which are stored on a blockchain are typically data about transactions. And this is the crucial bit of information which needs to be stored in a secure manner. A block will also include metadata, and this could include details such as a version, as well as the number of transactions, and so on. But once a block has been created, a cryptographic hash of the block will be generated as well, and that will be included as a field within the next block in the blockchain. And it is this cryptographic link which ensures that the transaction data in a block cannot be altered after it has been written to it. Well, strictly speaking, that is not true because one could alter the data, but this will compromise the integrity of the blockchain itself, because altering data in one block will mean that its hash will be different, which in turn will mean that the contents of the next block will be different, and this cycle will continue all the way to the last block in the blockchain. This means that if you wish to alter or remove a particular record from a blockchain, then that block, as well as all of the subsequent blocks, will need to be modified as well. And the consequence of this is that any attempt to tamper the data on the blockchain will be caught by all of the other nodes in the system. Since the cryptographic hash cannot realistically be reverse engineered, no one can tamper with the blockchain without changing the cryptographic hash and all of the subsequent blocks in the blockchain. So, as a result of this cryptographic link, each transaction which is recorded on the blockchain is both verifiable, since you can quickly calculate the hash of that block and all the subsequent blocks to confirm that there has been no tampering. And as a result, you can make the assumption that any data which is recorded on the blockchain is immutable or permanent. In other words, if you see some data recorded on the blockchain, it means that it was entered into the ledger by following the rules of the system. Which brings us to the question, how exactly do we enter records onto the blockchain? One way to do this is by means of a smart contract. A smart contract can be defined as a protocol to digitally specify, verify, and potentially even enforce the terms of a smart contract. Essentially, these are contracts but in digital form and written using a high-level programming language. Within a smart contract, you can define exactly how transactions need to be recorded onto the blockchain. You can define different types of transactions which can be recorded on your blockchain, as well as the specific participants who will be able to trigger them. So, you can trust what is written in the blockchain because you know that it is tamper-proof. And within the code of a smart contract, you can define the rules which need to be followed in order to record those transactions. And in a blockchain network, you can rest assured that the rules defined within the contract themselves are not modified because smart contracts are immutable. If you do wish to modify a particular contract, you can copy down its code and then issue a brand new contract in the network. This means that if you'd like participants to follow a new set of rules defined within a new contract, they will need to be pointed to that new contract, and one cannot sneakily modify the terms defined within an existing contract. Another important note is that smart contracts are not controlled by a single entity, but are in fact distributed across the entire network. The recording of transactions onto the blockchain typically requires validation from multiple, if not all of the nodes within the blockchain network. So, to summarize, the immutability of transactions as well as smart contracts ensures that participants in a blockchain network are working in an environment which they can trust. And this is the fundamental reason why many different enterprises are beginning to explore using blockchains in order to record their transactions. So now that we have seen what exactly blockchains are and why enterprises may decide to use blockchains in order to record their transactions, we will now cover a particular use case and see why it's not just blockchains in general which they would like to use, but that the specific implementation of Hyperledger Fabric suits their needs perfectly. So the specific use case we'll take a look at is that of a retail supply chain. So if we consider a product which is stocked at a retailer, we will know that this has been manufactured at a factory in some location. Once the product has been manufactured, that factory will then sell it along to a distributor, who in turn might hand it over to a wholesaler. This wholesaler will have a number of different customers, and this can include a retailer who will eventually stock the product on the shelves of their store. This, of course, may just be a compressed version of a full supply chain, but on each occasion when a good is handed over from one entity to another, a transaction needs to be recorded somewhere. Each of these participants will want to maintain such a record, not only for their own bookkeeping, but also to bring it up in case of any dispute with one of the other parties involved. The most common way in which such data is recorded today is that each of these participants maintains their own ledger and will record any goods which they have bought and then sold on their own books. While this does help with the accounting for each of the individual entities, it does pose a problem when there is a dispute between any of the parties involved. For example, let's just say that a distributor claims that a factory never supplied them with goods which they have paid for. There may not be a single record which both of them can trust to resolve that dispute. One solution which can be adopted to prevent such a situation is to adopt a distributed ledger. In this case, all of the entities in the supply chain will maintain a single ledger, and copies of this ledger will be available for each of the participants. So in this case, the recording of transactions onto the ledger becomes a team effort, and some kind of sign-off process can be implemented to ensure that data is not entered without both parties involved signing off on it. In addition, there must be some way to ensure that the data on this ledger cannot be tampered with in any manner. And this is precisely what a blockchain accomplishes. So we have covered that blockchain networks offer several benefits to participants. First of all, there is no single entity who controls the entire network, and the responsibility of maintaining it and entering data onto the distributed ledger is distributed across multiple parties. Additionally, once the data has been committed to the ledger, it cannot be modified in any manner. As long as the smart contracts which record transactions onto the ledger has been defined correctly, one can implement a process where a transaction is recorded onto the blockchain only if the two or more parties involved in it happen to sign off on that transaction. And once the transaction has been recorded and you are confident that it has not been altered, there will likely not be many disputes because each party will simply need to consult the ledger in order to verify whether a particular transaction has taken place. And this immutability of records on a blockchain is made possible by the fact that each individual transaction can be verified. Another feature of blockchains is that as long as the smart contracts have been coded correctly, then it is possible that you don't need to rely on a particular third party in order to ensure compliance with the terms of the contract. So if you define within the contract that the transfer of funds will take place from account A to account B after account A has signed off on the transaction, then this can be coded into the contract, and there is no question of A either delaying the payment or not making it at all. All in all, blockchains are a great way for all the participants in a retail supply chain to record their transactions. So the question to ask at this point is, what are the blockchain solutions available which the entities of the supply chain could use? Well, there are a number of different public blockchain networks which anyone can jump onto. Let us take a closer look at some of these. The network, which essentially pioneered blockchain technology and is still very much in the news, is the Bitcoin network. One major problem with this network, aside from many of the security flaws which have been uncovered, is the fact that the only type of transaction which that blockchain can record is the transfer of the Bitcoin cryptocurrency from one account to another. There is no support for smart contracts, so there is no question of defining your own bespoke transactions which can be recorded on the blockchain. So clearly, Bitcoin is not a solution for the retail supply chain. A more promising option is the Ethereum network. So Ethereum does support the functionality of smart contracts, and it is possible for each of the entities in the supply chain to record their transactions on the main Ethereum network. So this is the publicly available Ethereum network which anyone can use. Ethereum does come with several flaws, however, which we will be taking a look at in just a little bit. But we can now take a closer look at what public blockchain networks entail. The reason they are public is that anyone can join the network. There is no real screening process, and as long as you have the required hardware and you have installed the correct client, you will be able to participate as a node in the network. As a consequence, public blockchain networks end up having several nodes, tens of thousands in the case of Bitcoin and Ethereum. And another side effect of being public is that everyone can view all of the transaction data as well as data within the contracts. So confidentiality is not something you can expect on a public blockchain network. Moreover, since there are several thousands of nodes involved, there needs to be some way for all of them to arrive at a consensus on what the state of the blockchain should be. And this mechanism should ensure that any malicious entity is not able to take over the blockchain network. So, if you were to choose a public blockchain network for the retail supply chain, Ethereum may be the best option. This is because it is the most mature of the public blockchain networks available, and at the time of this recording, also happens to be the most widely used one. A primary reason for this is that Ethereum supports the notion of smart contracts, where you can define your own custom transactions to be recorded onto the blockchain. However, the invocation of transactions will incur some form of transaction fee, which needs to be paid out using a cryptocurrency called Ether, which is specific to the Ethereum network. The Ether cryptocurrency can be purchased on currency markets though, so for a retail supply chain, using Ethereum is a potential option. However, the reason why they would not use it is to do with some of the main concerns around Ethereum. This includes the fact that this network lacks any form of confidentiality. All of the transaction data is publicly available, not just to the members of Ethereum, but to pretty much anybody. The mechanism used for a consensus is a very complicated one, which is the proof of work, and this ends up using a lot of compute resources. While this does effectively serve the purpose of deterring malicious entities on the network, it comes at the cost of limiting the ability of Ethereum to scale. The consensus mechanism reduces the overall transaction throughput, which makes the Ethereum network not quite suitable for an enterprise which may want the ability to record potentially tens of millions of transactions. It is partly these concerns around Ethereum and other public blockchain implementations which led to the formation of the Hyperledger project, which we will be exploring in the next video. In the previous video, we covered the fact that blockchains offer an ideal solution to members of a retail supply chain who would like a secure way in which to record their transactions. We saw that the Ethereum network and other public blockchain networks don't quite fit the bill, and we will now take a look at why exactly the Hyperledger project is able to address those shortcomings and offer an enterprise-grade blockchain solution. So just to summarize the concerns around the Ethereum network, which applies to several other public blockchain networks, the lack of confidentiality of transactions does deter several enterprises from adopting these blockchains, since they may want the ability to provide special rates to specific customers without everyone being made aware of it. In addition, the consensus mechanisms on many public blockchain networks do involve significant usage of resources, and while this does help keep out some malicious actors, it comes at the cost of limiting the ability of Ethereum to truly scale and then process the number of transactions which are required of an enterprise solution. We can now zoom in on each of these concerns one by one to understand what exactly is required of an enterprise solution. Starting with the scaling concerns. In the case of Ethereum, its overall throughput is just about 3 million transactions per day. When you consider the fact that there is just one main Ethereum network which is available for the entire world, this is hardly an option for many enterprises, such as banks, for example, which may record tens of millions of transactions per day on their own. And the specific reason why Ethereum is unable to scale up is that the verification of transactions, which includes the proof of work consensus mechanism, does take up a lot of time. And it's not just time which is used in a non-optimal manner by the consensus mechanism. Even compute resources are effectively wasted. The proof of work algorithm means that thousands of nodes which participate in the network need to perform this task called mining, where they enter into a race to solve a mathematical puzzle, and in the end, only one of those nodes is declared the winner and gets the ability to write a block of transactions to the blockchain and collect all the associated transaction fees. The efforts of all of the other mining nodes is effectively wasted. The consequence of this is that there is a lot of electricity which is consumed in this mining process across all of the mining nodes in the network. An enterprise which would like to adopt blockchain technology will like to spend their electricity on processing transactions rather than in a race to solve a mathematical puzzle which allows them to process those transactions. So, the big problem here is the proof of work algorithm. So, are there any alternatives to this? Well, yes, but they're far from an ideal solution. At the time of this recording, Ethereum is debating whether to move over to another consensus mechanism known as proof of stake. And while this has the ability to improve the scaling as well as the resource utilization on the Ethereum network, it involves the participants in the network putting up a fair amount of money effectively as some kind of deposit. This again is not a viable solution for many enterprises. Which takes us along to the final category of concerns around Ethereum and public blockchains, which is to do with security and confidentiality. We've already covered the fact that anybody has the ability to view transactions recorded on Ethereum, and this alone is a deal breaker for many different enterprises for whom confidentiality is a key requirement. This also means that in public networks, there is no means to regulate access either. So you cannot restrict anyone from joining the network, and this leads to the possibility that some fraudulent entity could take over the network. In the case of many public blockchain networks, there are just a handful of entities which control a majority of the processing power. If those entities were to combine into a single company, then they could issue fraudulent transactions and then verify it on their own without having to get the consensus of the other nodes. It is these limitations of the available public blockchain implementations which led to the formation of the Hyperledger project. So, the goal of the Hyperledger project is not to provide a single blockchain solution, but in fact, several. So, these are referred to as Hyperledger Frameworks, and the goal is to provide frameworks which are all enterprise grade. This means that they must operate at an enterprise scale and have the ability to process tens of millions, if not hundreds of millions of transactions per day. Another aim of Hyperledger is not to churn out a profit, but to provide solutions which are open source and then increase the adoption of blockchain in the industry. Another factor which will influence the adoption of blockchain is the robustness of the solution. There have been several security holes which have been uncovered in the Bitcoin network, and this is also true of the Ethereum network and a number of other blockchain implementations. Also, since the aim of Hyperledger is not to provide a single one-size-fits-all blockchain solution, but to provide users with a number of options, many of these options can be very specific to one particular industry. For instance, there is a Hyperledger framework which is specifically catered to supply chain management. All in all, you can say that the aim of Hyperledger is to provide solutions which make use of the underlying blockchain technology, which allows participants to record transactions in a secure and verifiable manner, while addressing many of the concerns around platforms such as Ethereum, which has greatly limited its adoption by enterprises. With that in mind, let us take a look at some of the characteristics of the Hyperledger project. So, one very important thing to keep in mind is that it does not offer just a single solution, and it in fact serves as an umbrella of open source blockchain implementations. So, one project, several solutions. And Hyperledger is hardly new. In fact, this project was founded back in 2015, so it has had several years to figure out exactly what solutions it needs to offer, and the specific features in each of those solutions as well. Hyperledger is maintained by the Linux Foundation, which means that the people involved in it have plenty of experience in building and then maintaining enterprise-grade open source solutions. The fact that Hyperledger is meant to provide solutions for several industries has led them to a collaborative approach in that the project involves several industry leaders. So those involved in the Hyperledger project are very well aware of the problems faced by industries and the specific features which they need to build in order to address them. And in order to ensure that general solutions are available to multiple industries, the stakeholders in the Hyperledger project come from multiple different backgrounds. This could be from the tech industry, finance, automobiles, or supply chain management as well. So this diversity of stakeholders means that Hyperledger is able to come up with generic solutions which may be adopted by anybody. Some of the solutions will cater to very specific industries as well. So to summarize, Hyperledger is a project which involves several different stakeholders whose goal is to come up with multiple solutions. Some of these solutions are generic, while some happen to be industry specific. In all cases though, the underlying technology which they use is blockchains. So now that we know that the goal of the Hyperledger project is to come up with a number of different solutions, we can broadly classify these solutions into two categories. The first of these are Hyperledger Frameworks. So these are enterprise blockchain solutions meant for a consortium of organizations. As an example, we can go back to our retail supply chain, where we have a number of different organizations who can together form a consortium, and all of those members will be able to adopt one of the Hyperledger frameworks in order to securely record their transactions on a blockchain. So a framework involves the setting up of a blockchain network which is distributed across multiple nodes, and you can also issue smart contracts and then deploy them onto the blockchain network. So while frameworks do offer solutions, actually implementing them and then maintaining them after that can prove rather complicated, which is why the Hyperledger project includes a number of different Hyperledger tools. The goal of these tools is to greatly simplify the designing, deploying, and then maintaining blockchains and smart contracts. They will allow you to focus on the business logic rather than worry about the nitty-gritty of provisioning and maintaining the networks. We can now take a closer look at the Hyperledger frameworks to get a better idea of what exactly makes up a framework. Well, you can think of a framework as a blockchain network or an implementation of a blockchain. This includes an append-only distributed ledger, which means that once data has been recorded, it cannot be modified. A Hyperledger framework is set up across multiple nodes, which means that there must be some form of consensus algorithm for all the nodes to agree on the state of the network. All Hyperledger frameworks do come with their own consensus mechanisms, and in some of them, you may also have an options of consensus algorithms to adopt. The frameworks also allow you to have permissioned access to various parts of the blockchain network. Within the larger network, it is possible for some of the participants to maintain their own private blockchain in order to record private transactions. And another crucial feature of many blockchain frameworks is the ability to code up smart contracts in order to record your transactions. Some of the frameworks will allow you to define smart contracts in multiple languages. So what are the different Hyperledger frameworks which are available? Well, the most widely used one and the focus of this learning path is Hyperledger Fabric. This is a general purpose blockchain implementation, whereas Hyperledger Iroha is specifically meant for mobile applications. It is very lightweight and has libraries for both Android as well as iOS development. Hyperledger Sawtooth is another framework, and this includes both a permissioned blockchain as well as a permissionless option. The framework Hyperledger Indy focuses on the concept of decentralized identity, so that one's identity is split across a number of different nodes so that an attack on one of the nodes cannot compromise the identities. And then there is Hyperledger Grid, and this is a framework which offers a solution specific to the supply chain management industry. In addition to these, there are a handful of other frameworks which are also available, some of them being in an active state, while others are still in incubation. The focus of this learning path, though, is on one specific framework, which is Hyperledger Fabric. So, Fabric is a permissioned blockchain service which enables one to record confidential transactions on private channels. With Hyperledger Fabric, you do have an option when it comes to the consensus mechanism as well as the membership service. Since this is meant for a consortium of organizations, each organization may have their own certificate authority, and it is possible for them to retain those and use the identities issued by those certificate authorities to connect to the Fabric network. Hyperledger Fabric has been written in the Go programming language, and this is also a commonly used language in which to code up smart contracts on Fabric. The reason why we will be focusing on Fabric in this learning path, though, is because it is the most mature and widely used of the Hyperledger frameworks. This is partly down to the fact that it is a general purpose blockchain implementation and is not specific to one particular industry. So now that we have taken a look at the Hyperledger frameworks and focused on Fabric, we can now move along and take a look at some of the Hyperledger tools. As mentioned, the purpose of these tools is to simplify the process of working with the Hyperledger frameworks, and this can be done in many different ways. For one, these tools allow you to model blockchain networks so that you can define them using high-level abstractions which make more sense from a business standpoint. For example, you can define the different types of participants in your blockchain network as well as the types of operations which they can perform, rather than having to write down the code for all of these. Additionally, rather than having to script down a deployment process, you can make use of some of the Hyperledger tools which will allow you to do this from an intuitive user interface rather than you having to go down to the command line for every operation. There are Hyperledger tools which will also allow you to view the ledger data, once again using an intuitive UI, rather than you having to dig into the file system of the participating nodes. And there are also tools available which will allow you to benchmark your blockchain network and measure its overall performance on various metrics. Some of the tools which are available in Hyperledger include Hyperledger Composer, which allows you to define your network using high-level business abstractions. There is Hyperledger Cello, which allows you to deploy and maintain networks using a user interface. Hyperledger Explorer lets you view the ledger data once again from a UI, and it also includes various details about your blockchain network in general. Hyperledger Caliper is the tool you can use in order to measure the performance of your blockchain network. The metrics which it supports includes transaction throughput, transaction latency, and also resource utilization. And there is also Hyperledger Quilt, which offers interoperability between different ledger systems. Out of all of these, the tool we will be exploring in depth later on in this learning path is Hyperledger Composer. The purpose of this tool is to enable you to model business networks. The key being that you can model your networks, and you do this by using some business level abstractions. A lot of this modeling can be done by business users without a technical background, which goes a long way towards democratizing blockchain technology. And to make it even simpler to work with Composer, it includes a browser-based UI which allows you to model, deploy, and then also interact with your blockchain network. We will be studying this in greater detail a little later. So now that we know that Hyperledger offers several different frameworks and tools, how exactly do we use Hyperledger? Well, Given the different frameworks which are available, we will need to study the features offered in each of them and then pick the framework which suits our requirements. If you're looking for a general purpose blockchain solution, then you could pick Hyperledger Fabric. Or if you wish to use blockchains for supply chain management, then perhaps Hyperledger Grid is the choice for you. Once you have made the selection of your framework, you may be able to select specific components within those frameworks. For example, you can pick the consensus mechanism or the ordering service to use, and this is a choice which is available in Hyperledger Fabric, for example. Once you have used the framework to provision a blockchain network, you can issue identities to different users, whether they are human users or applications, and then assign permissions to each of them. And if defining, provisioning, using, and then maintaining a blockchain network is proving too complicated, then you could use one of the Hyperledger tools, which will simplify that entire process. So far, we have covered the fact that blockchains offer a great way for many enterprises to record their transaction data. And we have also seen that Hyperledger, and specifically Hyperledger Fabric, offers a great solution for these enterprises. We will now focus on the exact steps involved in setting up a Fabric network for such enterprises. And for that, we will revisit the example we have been taking a look at during this course, which is that of a retail supply chain. In this case, we have 4 different entities involved, where a product is manufactured at a factory, who then sells it off to a distributor. The product is then handed over to a wholesaler, who then finally sells it to a retailer, who will stock the product on their shelves and then sell it off to a customer. Let us now say that these 4 entities have decided to record all of their transactions on a blockchain network. So, what exactly are the steps which they will need to follow in order to set up a blockchain network and then get each of the entities to record all of their transaction information on it? Well, first of all, they'll need to make a selection of the blockchain implementation which needs to be used for this. And we have seen that Hyperledger Fabric is often a good choice for such enterprises. And for the sake of our example, we can assume that all of the 4 entities in this retail supply chain have decided that Fabric offers all of the necessary features for them to adopt this particular blockchain implementation for their transactions. They feel that Hyperledger Fabric is the most mature and widely used framework available, which means that it has fewer bugs, potentially more features, and if they run into any issues, there are also enough resources available online for them to be able to debug them and potentially fix them. Also, Fabric allows permissioned access, so a retailer and a wholesaler, for example, can have their own private channels on which they can record confidential transactions. Another important feature of Fabric is that it has a very high transaction throughput. The different steps which are followed when transactions are processed in Fabric are execute, order, and validate. Since execution occurs before ordering, transactions can be executed in parallel, which will greatly increase the throughput of the system. Alright, so the choice is made. All of those entities which we described in the retail supply chain, we want to set up a Hyperledger Fabric network because it contains all of these great features. So what are the specific steps involved in setting up this Fabric network? Well, first of all, the network needs to be provisioned, and this means that the different nodes which make up the network, and that includes the ordering service, certificate authorities, peers, and so on, need to be defined and implemented, and this is usually done by using Docker containers. All of the hosts which will run those containers will also need to be set up and then managed. In addition, for each of these entities in the supply chain, identities will need to be issued, and then they can use those in order to connect to the Fabric network and invoke transactions. These identities can be issued for both human users as well as applications. And in order to invoke transactions, they will need to develop and then deploy smart contracts. Those contracts will contain the logic for how transactions can be triggered and then recorded on the blockchain. Additionally, all of the network participants will need to be assigned specific permissions. These will determine what exactly they are able to see in the blockchain network and also the kinds of operations which they can perform. And since all of these participants cannot be expected to go down into the shell of their machines, connect to Docker containers in order to invoke transactions, they will need to build an app, preferably a web application, which will allow them to submit these transactions to the network and also view the contents on the blockchain by means of an intuitive user interface. So clearly, there is a lot of work involved when it comes to setting up a Fabric network which can be used by multiple participants. So the question now is, what exactly can we do to perform each of these steps? Well, let us look at things from an engineer standpoint. So an engineer is presented with this Fabric network architecture. Here you have three different organizations. Each of them have varying number of peers, but they also have their own certificate authorities. All of them have decided to use a common ordering service. In our retail supply chain example, there were four different organizations present, but for the sake of clarity, I have only included three of them in this diagram. So with this big picture in mind, let us dig down into the details. In order to set up such a Fabric network, we will need to set up multiple certificate authorities, one for each organization. We will need to set up an ordering service and also provision each of the peers which are participating in the network. Each of these will be implemented as Docker containers distributed across multiple hosts. Once all of those have been set up, we will need to initialize the blockchain. This will entail, for example, setting up the Genesis block, and then in addition to that, we will need to provision and then initialize various channels in the blockchain network. There are several tools which Hyperledger Fabric does supply in order to provision all of these, but one will still need to define each of these and then perform all of the steps in order to set up the network. Which takes us along now to the next step, which is to generate different identities for the different participants. The way to do this in Fabric is to issue certificates, and specifically those which conform to the X509 standard. Now you could have a central certificate authority which issues these certificates and then securely distributes them to each of the participants scattered across all of the organizations. Or alternatively, if each org is maintaining their own certificate authority, then every org will need to add all of the other certificate authorities in the network as their trusted CAs. So at this point, all of the participants in that retail supply chain have a Hyperledger Fabric network up and running, and they also have identities which they can use to connect to the network. Now, in order to use those identities to invoke transactions, they will need to develop smart contracts. So within those smart contracts, they can define the specific assets which need to be traded. And then after that, they will need to define various functions within the contract, which will record the trading of those assets on the Fabric blockchain. The logic defined within the smart contracts can also ensure that only valid participants can initiate transactions. For example, you could set that only the owner of an asset has the ability to change its ownership to someone else, which will happen when they sell it off to another participant. So now, those in the retail supply chain know exactly what needs to be done for them to set up the Fabric network and then begin recording transactions. In the next video, we will take a look at the kind of plan which they can draw up and the limitations of that plan, which can be addressed using a tool such as Hyperledger Composer. In the previous video, we saw that if all the entities in a retail supply chain wish to record their transactions on a Hyperledger Fabric network, they will need to come up with a plan for what the different Docker containers will be, the different channels and identities which they will need to set up, and also the smart contracts which they'll need to develop and then deploy to the network. So let us take a brief look at what this plan might look like. For example, they may decide that they need to provision a certain number of hosts and that they will also need to set up a certain number of containers which will be distributed across those hosts. So these will be used in order to set up the peers, the ordering service, and potentially the certificate authorities as well. Once all of the hosts and containers are up and running, identities will need to be issued, and this takes the form of digital certificates. So you need to decide what certificates need to be issued to individual users as well as applications. Since many of the participants will want private transactions, they will need to be set up with their own channels. Each channel maintains its own ledger, and all confidential transactions, which only involve a subset of the participants in the entire network, will be recorded on those private channels. And then following that, in order to invoke transactions, smart contracts will need to be defined and then deployed onto the network. So when you look at this particular plan, who are the kinds of people you can employ in order to implement it? Well, the common thread here is that all of the skills which are required in order to set up such a network come under the umbrella of computer science. So the kinds of professionals you need in order to set up a fabric network can be broadly classified into three categories. Developers who can code up smart contracts, those who have skills in operations to issue the identities and to manage the hosts and containers, and then you will also require network engineers in order to ensure that all the connectivity between the different components has been configured as per specifications. So these are all of the technical folks who are involved. However, this network is being set up on behalf of organizations in a retail supply chain, and there will be several non-technical users involved. In fact, it is very likely that it is these non-technical folks who will be driving the entire development process. So for example, all of the business requirements for this particular network will be provided by the users, and the users in this case could be those involved in the sale and purchase of the products. They could also be accounting professionals who wish to keep a track of all of the transactions and maintain the books for their organizations. But what is very likely is that none of these users will have any significant technical skills. This means that the business requirements will be specified in their own language. In the end, though, since what we need to provision involves hosts, containers, certificates, and so on, what we do need is for someone to translate these business requirements over to technical specifications. For this, a business analyst or some form of intermediary will be required, someone who has some degree of familiarity with both the business language and also a moderate understanding of tech. This individual will then be able to hand over the technical specifications over to the technical team whose job it is to build the network. This technical team does involve the developers, operations professionals, as well as network engineers whom we took a look at a little earlier. And they will go ahead and then set up the fabric network in terms of hosts, containers, certificates, smart contracts, and so on. So in this development process, all of the implementation work at the end is handled by a technical team. Which brings us now to the limitations of such a tech-heavy approach. Anybody who has worked in such a setting will unfortunately be all too familiar with the fact that a lot of the logic defined by the business users will have been lost in the translation to technical specs. And the technical team in turn may not have implemented details exactly as specified. When the network is finally set up and all the smart contracts deployed, there's a very high likelihood that it's not according to the specifications of the users, in which case the business requirements need to be looked at once more, translated into technical specifications on another occasion, and then implemented once more by the technical team. This leads to rather long development and also update cycles when new features are requested by the business users. There is a lot of back and forth and many different cycles of development before everyone is satisfied with the product. In addition, such a tech-heavy approach also requires many different engineers. In recent years, engineering skills have definitely been in short supply, and they also tend to be very expensive for companies. Also, looking at a supply chain problem mainly from the point of view of engineers is clearly not the best way to address it. And in fact, this is one of the reasons which is holding back the adoption of blockchain technology. So while this tech-heavy approach will offer a solution in order to record transactions on a supply chain, given all of these limitations described here, it is perhaps not the best approach. So what is the solution here? We have covered the fact that Hyperledger frameworks do offer great blockchain solutions, but in order to simplify working with those frameworks, we need to make use of one or more Hyperledger tools. And in fact, it is one such Hyperledger tool which we can use in order to reduce the reliance on engineers to build up a Fabric blockchain network, specifically Hyperledger Composer. In the next video, we will take a look at all of the features of Hyperledger Composer which make it such a useful tool in setting up a business blockchain network. In the previous video, we saw that setting up a Hyperledger Fabric network does involve a lot of work, and a very tech-focused approach towards setting up this network can be very problematic. We will now explore how the use of Hyperledger Composer can greatly mitigate some of those flaws. The example we have been working with involves members in a retail supply chain. This includes a factory, a distributor, a wholesaler, and a retailer. They have decided that the most secure way to record all of their transactions involves the use of a blockchain, and the specific solution they have selected is Hyperledger Fabric. In order to set up this Fabric network, business requirements have been translated into technical specifications, and now it is up to the technical team to do the final implementation in order to set up the network. The plan they have put in place involves the provisioning of hosts and then setting up containers to run on those hosts. These containers will represent the CAs, peers, ordering services, and so on. They have also decided to issue certificates to handle the identities for different participants in the network. And they also have to provision channels and then code up and deploy smart contracts. So we have seen that this is an engineer's way to look at the problem, and that there are several limitations to this kind of approach. So rather than look at the problems in terms of these different components we see on the screen, what if there is a different way to approach it? This involves a bit of a paradigm shift, but rather than think of the problem in terms of hosts, certificates, and so on, what if you look at the problem from a different standpoint? For example, the problem can be thought of in terms of the different assets which can be handed over from one entity to another in the supply chain, and then following that, the different participants who are involved in the supply chain, such as the distributor, the retailer, and so on. Beyond that, you can think about the permissions which each of the participants needs to have. Can the retailer see all of the transactions between the factory and the distributor, for example? And then following that, what are the different kinds of transactions which are possible in the network? Someone who owns an asset should be able to sell it off to another participant in the network, but can they change the description of the asset? If these are the details you're concerned with when setting up a Fabric network, it becomes a very business-oriented approach towards solving the problem. This is definitely looking at it from a much higher level and more in terms of what the actual users of the system would like it to be. So with this paradigm shift, let us explore some of the benefits of looking at the problem from a business-oriented standpoint. For one, it is likely that the users will be much more directly involved since they are not entirely reliant on a technical team to set up the network. A lot of the definitions can be performed by the users themselves, irrespective of what their background is, as long as they are willing to spend a little bit of time to learn exactly how they can define these users, assets, and so on. That is, they can define the blockchain network in terms of business level abstractions. When using a tool such as Hyperledger Composer to do this, all of the implementation details will be handled by the tool itself. A consequence of this is that there will be fewer people involved in the whole development process. If the tool itself does a lot of the heavy lifting in terms of the implementation of the network, then you don't need as many engineers to set it up. And if the business users are able to participate in the blockchain network creation directly, then there will be a lot fewer people required in order to translate business requirements into technical specifications. So by allowing users to more directly participate in the process and then abstracting away a lot of the implementation details, a tool such as Hyperledger Composer goes a long way towards democratizing blockchain technology. So what exactly is Hyperledger Composer? Well, their website defines it as a programming model which contains a modeling language as well as a set of APIs in order to quickly define and then deploy business blockchain networks and applications which allow participants to send transactions which exchange assets. Now, this is clearly a mouthful, but there are a few key phrases here. First of all, it involves the use of a modeling language. This language is far easier to grasp than any programming language, and even somebody with a non-technical background will be able to get familiar with it in a matter of hours. This modeling language will allow the network to be defined in terms of participants, transactions, and assets, while the Composer tool will handle the implementation of each of these under the hood. So we can now delve into some of the characteristics of Hyperledger Composer. So this is a tool which is built on top of Hyperledger Fabric. Due to all of the abstractions, this is something which may not be evident to the users of Hyperledger Composer, since all of those abstractions happen to be at the business level. That is, you can define the assets, participants, transactions, and so on. Now, you could define all of these on your own, or if you'd like to speed up your development process, then you could also make use of some of the templates which are provided by the Composer tool. These will include some standard definitions of participants, assets, transactions, and so on, which you can then build upon in order to build up your own Fabric network. So just to summarize, when you wish to provision a new business blockchain network, you have the option to build from scratch, where you'll need to define all of the assets, participants, permissions, and transactions on your own. But then beyond that, all of the other implementation is handled by the tool itself. An alternative is to choose from one of the available templates. This will provide standard definitions for the different types of abstractions which are available, so that you have at least some kind of base on which to build up your network. There are templates which are available for very specific use cases. You could set up a blockchain network to handle property or even set up a supply chain. And all of these selections can be made by making use of the Composer web user interface. The Composer UI also provides something like an IDE, which allows us to create all of the definition files we will need to set up the network. We will take a look at those files in detail in the next video. In the previous video, we discussed the fact that Hyperledger Composer can greatly simplify the task of setting up a Hyperledger Fabric network. But setting up a Fabric network using Composer is not as simple as just clicking a few items on a web UI. And there are a number of definition files which need to be set up. A very important one from these is the model file, and this has the extension of .cto. CTO is a domain-specific modeling language used in Hyperledger Composer. And this is a language which needs to be learned by the users of the tool, though it is not nearly as complicated as a programming language. The details which are defined within this model file include the assets, the participants, as well as the transactions, and you define the transactions in terms of the assets which can be transacted and the participants who are involved in the process. The actual logic of the transaction processing is implemented in a JavaScript source file, which includes one function for each transaction which is defined in the model file. So while Hyperledger Composer does abstract away a lot of the technical implementation details, it does not mean that you can do away with technical skills entirely, and you will need developers who understand JavaScript in order to code this transaction processor. A third kind of definition file has the extension .qry, and this is where you can define the different query operations which will take place on the data in your blockchain network. These queries are defined in a very SQL-like syntax, and since SQL skills are very common these days, you don't require a core technical person in order to set this up. Which brings us along now to the fourth definition file, and this has to do with access control in the blockchain network. This file has the extension .acl, and this is where you would specify the different degrees of permissions available to the various participants on the network. We can now take a closer look at each of these four definition files, starting with the model file. So this model file, as we have covered, has a file extension of .cto. This is in fact a domain-specific modeling language which needs to be learned by the users. However, it is far from complicated, and even non-technical users will be able to grasp its fundamentals in a matter of hours. And while this modeling file is not as complicated as a programming language, it does offer support for a handful of types. These types are very limited in number and cover just some of the very basic types of data which can be stored, such as strings, integers, and so on. This model file, though, is a crucial element of our blockchain network definition, because this is where you will define all of the assets which belong to your network, the different participants, and also a high-level picture of what the transactions in your network will involve. And these are typically defined in terms of the assets which can be transacted and the participants who are involved in such a transaction. You can also define various events within the model file. We move along now from the model file over to the transaction processor. And while in the model file, you can define a transaction in terms of assets and participants, it is in the transaction processing script where the actual logic for this transaction is coded up. So while in your model file, you may define that a particular transaction involves the transfer of an asset A from participant X to participant Y, the actual logic for that transfer will need to be implemented within the transaction script. And it is within this transaction script that you can first perform various checks, and then depending on the output of those checks, you can perform an update to the state of an asset, for example. The type of checks which are not performed within the transaction file are permission checks. And these need to be defined within the access control file, which is in fact what we will now take a closer look at. So within the ACL file of our Hyperledger Composer network definition, we essentially answer two questions. Who can access which resource, and what level of access do they have? For instance, you can define within this ACL file that a particular type of participant has the ability to read data about a transaction but cannot update its state in any way. Which takes us now to the last of our definition files, and this is the one with the query definitions and has the extension .qry. So it is within this file where we define the different types of queries which our application supports. So if you'd like to view the details of all participants who fall into a particular category, you can define such a query within this file. The specific language which is used for this is very similar to SQL, which is why anyone who has a background in SQL can define such a file. Given how widespread SQL skills are these days, you don't really need an application developer or some database expert to handle this. If you'd like to view the results of your query in a web application, for example, then this can be done because these queries can be invoked with a REST call. So with these 4 different files, we now have an idea of what exactly is required in order for us to define a Hyperledger Fabric network using Hyperledger Composer. Once we have defined our blockchain network though, how exactly do we provision a new network out of it? And how can we begin interacting with the network and record transactions onto the blockchain? Well, these questions will be answered in the next video. We have previously seen how we can define a Hyperledger Fabric network using Hyperledger Composer. It is now time for us to explore how we can use that network definition in order to set up a Fabric network and then begin using it in order to record transactions on the blockchain. So we previously covered the fact that in order to provision a business network using Hyperledger Composer, our options include building one from scratch, where you effectively start off with a blank slate, and all of the definition files which you need to set up your network will be built out of completely blank files. If you'd like some kind of foundation upon which to build your network, then you can choose from one of the many templates which are available in Hyperledger Composer. These include templates to set up a network for supply chain management, another one to record real estate sales, and so on. Depending on the specific use case, this will supply a collection of pre-configured definition files, which may include assets, participants, transactions, and even permissions which are specific to that use case. Your goal then will be to build upon those templates in order to define the Fabric network which suits your requirements. Once all of these definition files are ready and you have planned out exactly what your network should look like, what exactly is the next step? So we have defined everything. How can we use those definitions to set up a Fabric network and then begin recording our transactions? We can still stay within Hyperledger Composer for this. And let us take a look now at what our development process might look like. We might set up a business network either from scratch or using one of the templates specified in Composer. Following that, we can define our sources. These include the CTO file, the ACL file, the transaction processor, and maybe even the query file. And we may or may not be building from a template in this case. But at this point, we have the full definition of our business network, and it's time for us to check whether those definitions are in line with what we expect. That is, it is time for us to deploy the network and then test it out. So the question now is, what exactly are the options which are available for us in terms of deploying and testing the network? Is there something within Hyperledger Composer which will simplify this process for us? And the answer, as you may have guessed, is yes. There is something known as Hyperledger Composer Playground, which, according to the official definition, provides a user interface for the configuration, deployment, and testing of a business network. In fact, when you're learning about Hyperledger Composer, it is strongly recommended that you start off with Composer Playground and then use that in order to both define and then test out your networks before deploying it to a production setting. So what exactly are the features of Composer Playground which simplifies the process of developing and testing Fabric networks? Well, for one, it is a web application, which means that you're working with a user interface in order to set up the network. This saves you the trouble of working directly with the file system from within a shell environment, for example. You can stay entirely within Composer Playground in order to define and then also test out your business networks. And all the choice of network templates which are available in Composer can be selected from within the Composer Playground interface. Not only that, Playground also includes an IDE for developing all of the source files for your network definition. So the CTO, ACL, the transaction processing file, as well as the query file can be developed using this IDE. and you don't have to use a separate one in order to define them. So all of these steps cover the definition of your business network. And once you're done with that, you can deploy an instance of your network into a test environment. It is within this test setting where you'll want to check whether all of your definitions have been set up correctly. And in order to do this, you will need to create instances of all of the assets and participants which you have defined. This is something which you can do within the Composer Playground interface. So if we stick to the example of the retail supply chain, you may provision a business network which has definitions for a generic asset, and then you may have participants which include the factory, the distributor, the wholesaler, and the retailer. An instance of an asset could represent a particular batch of a product, let's just say a box of shampoo, whereas the instances of participants may be instances of a real factory, let's just say factory X, which manufactured the shampoo. And then similarly, you will have instances of the other participants as well. Now, for those participant instances to begin using the network, identities will need to be issued for them. These are the identities which they will need to use in order to connect to the Fabric network and then begin recording transactions. For example, to transfer the box of shampoo from the factory to the distributor, for example, and then from the distributor to the wholesaler, and then on to the retailer. And these transactions can be invoked from within the Hyperledger Playground interface because it does include features for you to connect as different participants using their issued identities and then begin using the network, either to just view all of the data or to invoke transactions and then record data onto the blockchain. Within the test setting, you will not only check whether all of the transactions can be invoked by the correct participants, you will also need to ensure that each of them has exactly the permissions which they're supposed to. For example, if you had a rule to only allow the owner of an asset to sell it off to someone else, this behavior can be tested using Composer Playground. And of course, there will be a whole host of other tests which you will need to perform. In the next video, we will now take a look at how you can export the business definition over to a production setting. In the previous video, we covered how we can perform both the development as well as the testing work for a Hyperledger Fabric network using Composer Playground. And we assume that there will be a lot of back and forth where you deploy your definition into the test environment and then refactor depending on some feedback which you receive within the tests. And then you redeploy your network and then test it out all over again. After a few iterations, you may be quite satisfied with the performance of your network and you feel that all of the features which you wish to include have been captured. It's now time for you to deploy this network into a production setting, and it is now time for us to focus on the exact steps involved to make that happen. So once you have a finalized network definition within Hyperledger Composer Playground, it is possible for you to export that network definition into something known as a BNA file. That same network definition can be used in order to set up multiple Fabric networks. But for now, let us just focus on setting up one such network. The next step is to actually provision a Hyperledger Fabric network, and this is done using a blank slate. And then following that, you will use your network definition file in order to install your business network to that Fabric network. So you now have an instance of your business network in a production environment. There is still more to do, however, since that network has not been started up. To use an object-oriented programming analogy, after the installation of your business network, what you had was an object which was declared but not yet instantiated. And you need to do that by starting up this business network. But once that is done, you do have a Hyperledger Fabric network which you can begin using. And it is at this point where you will interact with the network and then begin recording your transactions. To do this, of course, you will need to make use of one of the issued identities. and the operations which you can perform will depend upon the permissions which have been granted to your identity in the network definition. So there is still one more factor to consider when connecting to a business network and using it to record transactions. So we started off with a network definition file with the .bna extension, and then we used that to provision and then set up a fabric network. With that network up and ready, we will need to provision a business network card, and let us now take a closer look at what exactly this network card is. Well, this is the one which contains all of the information which is needed in order to connect to a business network. This is something which needs to be issued to every single identity who wishes to connect to the network. And these are identities which can be issued not just to human users, but also to applications. The applications can interact with the network using the REST API, while users can interact with the network using the user interface. And how exactly can this business network card be issued? Well, this is where Composer Playground makes things easier for us once more, since that can be used to issue a business network card. And you can also make use of the Hyperledger Composer CLI in order to set up one. In this exercise, you will first describe the purpose of Hyperledger Tools. We covered during this course that the outputs of the Hyperledger project can broadly be classified into two categories: Hyperledger Frameworks and Hyperledger Tools. The frameworks are the actual implementations of blockchains, and the Hyperledger tools are related to them. You will need to identify the nature of the relationship and some of the features of the different tools available. Next, you will enumerate the 4 different types of definition files which are used in Hyperledger Composer. When defining a business network using Composer, there are 4 different files which we can create in order to specify exactly what the network involves and the different types of operations which are possible. You will need to list out what those 4 files are and what purpose each of them serve. And finally, you'll summarize the features of Hyperledger Composer Playground. While Hyperledger Composer is a tool which greatly simplifies the task of provisioning a blockchain network, Composer Playground is another feature which adds to the simplification. You will need to identify those features of Composer Playground which ease the process of setting up business blockchain networks. Each of these topics were discussed during this course, so please pause this video and then take some time to perform the tasks on your own. For the first task, you needed to identify the purpose of Hyperledger Tools and then list down some of the features which they offer. Well, the main goal of Hyperledger Tools is in the context of Hyperledger Frameworks, in that they greatly simplify the process of working with Hyperledger Frameworks. Setting up and maintaining these frameworks can prove to be a rather complicated task, and it is up to the tools to abstract away some of the implementation details. For example, the tools can allow us to define blockchain networks using high-level abstractions in a modeling language, rather than have us focus on some of the implementation details such as the provisioning of hosts, Docker containers, certificates, and so on. Hyperledger Composer allows us to define a network in terms of business-level abstractions such as the assets which must be part of the network, the different kinds of participants, as well as the types of operations which the participants can perform on those assets. There are also tools available which will simplify the process of deploying and maintaining blockchain networks by once again using high-level abstractions to allow us to focus on the workflows rather than very specific implementation details. In order for us to view data in a blockchain ledger, we can use a Hyperledger tool with an intuitive web UI rather than having to navigate into the file system of a particular host and then using the shell to examine the contents of the ledger. We can also use Hyperledger tools in order to test out the performance of our blockchain network. For example, we can use Hyperledger Caliper in order to measure the overall network throughput in terms of the transactions processed per second, also check out the total transaction latency, and the overall resource utilization in our blockchain network. Some examples of Hyperledger tools which we covered during the course included Hyperledger Composer, Cello, Explorer, and Caliper. For the next task in the exercise, you needed to list down the different definition files which can be used in Hyperledger Composer. One of the 4 files which we touched upon is the model file, and this one has an extension of .cto. Within this model file, you will use high-level abstractions to define various components of the blockchain network. This includes the various assets which can be transacted upon, the different participants who can invoke those transactions. You can define events, and also a high-level definition of a transaction in terms of the participants and the assets involved in a type of transaction. The specific details of the transaction, however, need to be defined within the transaction processor file. So this is a JavaScript source file, and within this, you will define exactly what goes on within the transaction. If the transaction involves updating the price of a particular asset, then this definition needs to happen within the transaction processor. Another definition file in Composer is a query file, and this has an extension of .qry. The query file has a SQL-like syntax, and much like with SQL statements, you can define exactly the kind of operations which can be performed in order to read the contents of the blockchain network and then publish it to the user. These queries can be invoked using a REST API as well. This takes us along to the last definition file, which is the access control list. This one has an extension of .acl, and as you can imagine, it is within this file where you specify the different level of permissions which are available for the various participants in the network. Within this file, you will define what permissions a particular type of participant has on a specific resource, and the resources include, among other details, the assets, participants, transactions, and so on, which are defined within the model file. Some examples of the different levels of permissions include create, modify, and read. Which takes us now to the last task in the exercise, which was to list down the features of Hyperledger Composer Playground. As touched upon, the purpose of Composer Playground is to ease the development process of a business network. And because it is available as a web application, we can use a nice intuitive UI in order to set up this network. We have the option to provision business networks either from scratch, or we can use one of the pre-configured templates which are provided in Composer. This will provide to us some kind of base with some pre-configured definition files, which we can build upon and customize to our own requirements for our own network. Composer Playground also includes an IDE in order to develop those network definition files. And once we are finished with the development, we can deploy our network over to a test environment. This is where we will actually be performing all of the tests in order to ensure that our network behaves exactly as we want it to. And here we will be testing out not only the different types of transactions, but also the permissions which we have assigned to the different participants. Testing these out will involve us having to create instances of the different assets and participants which we have defined within our model file. And in order to connect to the network as a particular instance of a participant, you can use Composer Playground to issue identities to that instance, and you can use those identities in order to interact with the deployed network and to potentially invoke transactions. There will likely be a few different iterations where you will run your tests in the test environment, find some bugs, refactor your network definitions, and then redeploy it and repeat the testing process. At some point, though, you will be satisfied that your network behaves exactly as you expect it to, and that all the transaction definitions and permissions have been set correctly. In which case, you can export your network definition over to a .bna file, and you can use that file in order to deploy your network over to a production setting. So as the name implies, Composer Playground is a place for you to play around with your network definition until it is ready to be deployed into production. The quickest way to provision a Hyperledger Fabric network is by means of Docker. This way, you can provision Docker containers for each of the pieces which makes up a Fabric network. This includes the certificate authority, the ordering service, as well as the peers. If you already have a fair amount of experience with Docker, then you can skip this video and the next few ones and move directly to the labs of this course. On the other hand, if you haven't used Docker before, or simply wish to get a quick refresher, then you can stick around for this quick overview of Docker. Now, to understand Docker, you need to understand the concept of application portability, which is what we will explore right now. So what exactly is meant by application portability? This means that if you have an application which runs in a certain way on one machine, then it runs in the exact same manner on any other machine. This, of course, ensures that your application runs in a predictable way, and this, of course, is a rather important factor when building any app. So what exactly is involved when it comes to running an application? For that, consider that you have your own dev machine, which looks something like this. Within the machine, you have your application, and that application in turn has a number of dependencies. All of those together will execute on an operating system, and this, of course, is just the software part of your dev machine. All of this will, of course, be running on some underlying hardware, but your OS should ensure that your application is abstracted from it. Out of all of these spaces, it is only the application component which is very much in your control. And the output which is generated by your application, or whether it even runs at all, will often depend on all of the other components. That is, the dependencies and the operating system. To get a little granular, assume that within your dev machine, you have a certain set of dependencies and the operating system. So you're running version 2 of dependency number 1, version 1 of dependency 2, and version 4 of dependency 3. In addition, the version of the OS which you're running happens to be version 2. Now with the specific configuration, when you go ahead and try to run your application, this works exactly as you planned it to. And now that the development work is done, it is time for you to deploy your application over to the test machine. Now you must expect that your test machine may have a slightly different environment than what you did on your dev machine. In this particular case, you can take a look that the operating system version is a little different, as well as one of the dependencies for your application. And due to these minor variations, your application just does not work. And then your production environment may still have a few other variations, which will once again result in your application being unable to run. While it is now far easier to maintain consistency across environments, thanks to various pieces of software, which include configuration management tools, it is not always great design if your application package only works in a very specific environment. So what exactly are the options for us? Well, the environment in which your application did work was the one on your dev machine, which has a specific set of dependencies and a particular version of an operating system. So what if you can package all of this together and then simply deploy that? This is precisely what a virtual machine helps you accomplish, where you can package the entire contents of your machine, which includes your application, as well as its dependencies and the operating system, which of course will include the specific versions of the dependencies and OS which work with your app. So now that your application is effectively packaged as a VM, how exactly can you deploy it? Well, you'll typically deploy your virtual machine or VM onto an environment which is running a hypervisor. This environment will be running its own operating system, which is known as the host OS, and it is one which is capable of running multiple virtual machines. Those VMs are not run directly on the host OS though, and this needs to go through something known as a hypervisor. So while your application will communicate with the OS within its own virtual machine, that OS in turn will communicate with the underlying host operating system through the hypervisor. So in an environment such as this one, you can have multiple virtual machines deployed. So once you have packaged your application into a VM such as this one, you can deploy it onto any such environment, and your application will run exactly as you expect it to. So your application is now portable, right? Well, yes, but not exactly. So we have seen that within virtual machines, the package includes the application which you have coded up, along with all its dependencies, and specifically the versions of the dependencies which work with your app. This VM also includes the version of the operating system which is compatible with your app and its dependencies. So there are several advantages to VMs, which is why they have been so widely used. The important one being that you can deploy your VM to any compatible hypervisor. And companies such as VMware and Oracle specialize in this. And thanks to this factor, it means that your application is now portable. So if your application works in your dev environment, you can simply package that as a virtual machine. And if your test and production environments are also running hypervisors which are compatible with your VM, then your application can run on those without any issues. And though this is a valid solution to your problem of portability, it does come with serious drawbacks. First of all, virtual machine images are very heavyweight. Thanks to the inclusion of the OS, they are often several hundred megabytes or even a handful of gigabytes in size, which means that storage alone can become a problem. Not only that, your VMs are often slow to boot up and to recover. So if you wish to provision multiple instances of your VM, this can take a really long time. And this is due to the OS in your VM needing to boot up on each occasion. Additionally, the size of your VM image also limits portability to a great degree. Since their size can be about a few gigabytes, deploying them to some remote location in the world will take a really long time and is something which you need to plan well in advance. Which is why calling your application portable at this stage is not exactly accurate. Additionally, migrations can also be a problem, and this is once again due to the size of the VM image. And if your app happens to be just one among many which make up a very large system, then you can imagine the complexity of the migration if each of those applications making up the system have been deployed as VMs. So while virtual machines do make your applications more portable, they clearly come with several limitations. And all of these limitations are mainly due to the size of the VM. So you will notice that by far, the largest component of a virtual machine is the operating system. In many instances, the application and the dependencies may only make up a few megabytes, and thus just a fraction of the entire size of the VM. So if you wish to make this a little more efficient, the first question to ask is, does the entire OS need to be included within this package? Well, the answer to that is no, and how exactly that would work is something we will take a look at in the next video. In the previous video, we saw how virtual machines can make your applications somewhat portable. I say somewhat because the size of the virtual machine does limit its portability to a great degree. And in this video, we will see how packaging your application into containers using a tool such as Docker can greatly improve the portability by limiting the size of the package. So we have seen that you can package your application along with all of its dependencies and the specific version of the OS it works with into a virtual machine. This VM can be deployed to any environment which is running a compatible hypervisor, and your app should work in the same way in any environment. The big problem, however, with this approach is that virtual machines are very large, and the size is mainly thanks to the operating system which is packaged into this VM. So even though your app and the dependencies may only take up a few megabytes of space, the full virtual machine image could often take up a few gigabytes of space. And since this size does limit the portability of your application, the question we had posed earlier was whether the entire OS does need to be included in this package. So let us take a look at the OS a little more closely. So in the case of a Linux-based operating system, this is what it looks like. Within the operating system, you have the Linux kernel, which takes up a bulk of its space, and then a much smaller proportion of the space is taken up by the user space of your specific flavor of Linux. And while this is a generic view of any Linux-based OS, let us take a look at some of the specific flavors of Linux. So here we have represented three very popular Linux distributions: Ubuntu, Red Hat, and Fedora. And the reason why these are called Linux distributions is because all three of them use the exact same Linux kernel. This also applies to other Linux flavors such as CentOS, for example. And since this particular component is the same for all of the Linux flavors, what sets them apart is the user space for these OSs. Given the fact that every Linux distribution uses the same Linux kernel, can we use this to make our application packages more efficient? The answer, as you will have guessed, is a firm yes. So one way to make your application portable is by packaging its dependencies and an OS into a VM. And the way to make this package a little more space efficient is by means of a container, where your application package includes the app itself, the dependencies, and just the OS user space. And in order to be deployed, this container does not require a very large machine which is running a hypervisor, for example, but can be run on any machine which has an OS that uses the Linux kernel. And since the user space is usually a fraction of the size of the entire OS, containers are relatively much smaller than virtual machines. And this is mainly due to the fact that the OS user space is just a fraction of the size of the entire operating system. And while this diagram does illustrate that, it does not do justice to how small containers actually are when compared to VMs. This is because applications are typically much smaller than the OS than illustrated in this diagram. So now that we have an idea of how containers can make your application package much more lightweight, let us take a look at some of its characteristics and what the consequences of its small size are. So containers, as we have seen, are rather lightweight and in fact only take up a few megabytes of space. This is compared to VMs, which take up several hundred megabytes and potentially a handful of gigabytes. Another benefit of containers is that these are very quick to create and also to restart. Because they don't include the Linux kernel, they don't need to go through an entire boot process, and a container can be spawned within just a few seconds as opposed to potentially minutes in the case of a VM. The small size of a container means that it is possible for you to host multiple containers on a single host as opposed to VMs. You can, for example, have multiple instances of your application running on the same host, or you could have instances of different applications running on the same machine as well. All of this means that once your app is packaged as a container, it becomes truly portable. So you can quickly create images of your containers and then upload them to a location which you can use to share with your team, which may be scattered throughout the world. Another consequence of this lightweight nature of containers is that this has spawned the creation of microservices. This means that large applications can be made much more modular by breaking them up into a number of small services, each of which can be deployed as containers. So at this point, containers might seem truly magical, and you may be asking the question, How exactly can we create these containers? The most common way to do that today is to make use of Docker. And in the next video, we will see exactly how Docker can be used to define and then spawn containers. In the previous video, we saw how packaging our application as containers can make them much more portable than by using VMs. This is mainly due to the fact that containers don't include the Linux kernel, which often takes up the bulk of the size of a VM. Now the question is, how exactly can we create containers? And a really good way to do that is to make use of Docker. So Docker can be thought of as a piece of software which greatly simplifies the task of creating, deploying, and then running containers. And to understand Docker, there are two terms which you must become familiar with. The first of these is a Docker image. This represents a definition of your application or service, including all of the dependencies of your application, as well as the type of operating system which it needs. Since we are limiting ourselves to Linux operating systems, this will include the flavor of Linux and the specific version of that flavor. So in a nutshell, a Docker image represents a definition of your application's package, which includes the application itself, its dependencies, and the OS it needs to run on. And then in order to actually run your application, this is where you will spawn a container out of the Docker image which you have defined. So in Docker terms, a container is a running instance of an image. To use some object-oriented programming terminology, you can think of a Docker image as a class definition, whereas a container is an instance of that class. We can now zoom in on Docker containers just a little bit. As mentioned, these are in fact running instances of an image. And just as you can have multiple instances of a class in an object-oriented language, you can have multiple containers created out of a single image. So if there is a heavy load on your application, then you can increase the number of instances of your app running in your environment by simply provisioning more containers out of the image of your application. And since containers are very lightweight, it is possible to have multiple containers deployed onto the same host, and you can also set them up so that they share the same file system and are able to communicate with each other. So just to summarize, this is what your Docker container might look like, where you have packaged your application along with all of its dependencies, and with that, you have also included the user space of the OS which your app is compatible with. And in order to run this container, you only need to deploy it to any machine which uses an OS that includes a Linux kernel. However, things are not as simple as simply running this container on any Linux machine, since your container may not be able to directly communicate with the underlying operating system on the machine it has been deployed to. In fact, in order to run a Docker container, you will need something like a middleware which will handle this communication between the container and the underlying OS. This communication will include calls from the container to the host operating system, and then the reverse is also true, where messages will need to be relayed from the underlying OS over to the container. Since your application will need access to a file system, this middleware should be able to map the host file system over to your container, and at least make part of the host file system available for your container. Also, it is fully expected that your container will not be running in isolation, and that other containers may need to access it, or potentially even users from the internet may need to access your container. To enable that, your application may be listening to specific ports in the container, and you will need this middleware to map the container ports to ports in the underlying OS. In the case of virtual machines, we saw that the hypervisor plays the role of such middleware. And in the case of Docker containers, there is something called the Docker Container Engine, which serves the same purpose. So when I mentioned earlier that you can deploy a Docker container to any machine which is running a Linux operating system, a more accurate statement would be that it can be deployed to any machine which is running a Linux OS and has the Docker container engine installed. So just one thing to note, since we have been talking about Linux operating systems, the typical use case is to create Linux-based containers and then have them deployed on Linux operating systems. Though it is possible to deploy Linux containers on macOS as well as Windows 10, this is not quite a common use case yet. With that said, let us move along to see how Docker fits into Hyperledger Fabric. So a Hyperledger Fabric network may look something like this, where you have three different organizations, each with one or more peers, as well as their own certificate authority. There is also a common ordering service for all of the organizations here. Now, if you wish to simulate a Hyperledger Fabric network where you can deploy your smart contracts and then test them out, you could potentially provision a smaller version of a Fabric network where you have, say, just a single organization which contains a single peer and CA. You will still have an ordering service, and in addition to that, you may wish to use some kind of CLI in order to communicate with your network, where you can deploy and then invoke your chain code. So you potentially have 4 different components over here. In which case, does it really make sense to create 4 different hosts in order to test out your Fabric network? Or alternatively, can you simply provision 4 different Docker containers to represent each of these components? Well, in the demos of this learning path, it is very much the latter option which we will exercise. The entire Fabric network which we provision will be done so on a single host. That is, it could also be done on your own desktop. And we will still have peers, certificate authorities, ordering services, and a CLI, since each of them will be running as their own independent, very lightweight Docker containers. For the labs in this learning path, we will be setting up a Hyperledger Fabric network. We will then develop our own chain code and then deploy it to that network, instantiate it, and then invoke operations from that chain code. The Fabric network we will provision will include a few components, such as the peer to which we can install our chain code, also a certificate authority, and an ordering service. All of these, along with a CLI which we will use in order to interact with the network, will be provisioned as Docker containers. All of those Docker containers can be run from a single host, and in my case, I'll be running them on my own machine, which happens to be running macOS. So to do that, we need to install Docker, for which I have now come over to the Docker website, and I'm about to install Docker for Mac. Docker version 18.09 is the latest version of Docker available at the time of this recording, so by the time you see this, newer versions of Docker should be up. Do note here that I'm about to install Docker for macOS. So if you already have Docker installed on your system, then you can move ahead to the 5-minute mark of this video, where we will be installing the Go programming language. Or if you happen to be running a different OS and need to install Docker for that, then you will need to look up the specific installation instructions for your own OS. If you do happen to be on a Mac and you wish to provision the Fabric network on your own machine, then you can follow along with this video. So from here, you can see the different versions of Docker which are available, and you can also default to a previous version if you need to. In my case though, I'm going to stick to the latest available version. And if you would like to browse through the instructions for the installation, you can just scroll down in this page. But in my case, I'm just going to scroll back up and then choose to download Docker from Docker Hub. Once that choice has been made, you can confirm that this is indeed an installation for Docker on macOS. And then once you're satisfied, click on this Please Login to Download button. At this point, you will be prompted to sign in to Docker Hub with a Docker ID. I already have one, so I'm going to enter my credentials here. And in case you don't already have an account on Docker Hub, you can go ahead and create one. You can think of Docker Hub as a GitHub for Docker images. This is where you can store different versions of your various Docker images and then pull them whenever you need to. So once you have signed in to your Docker Hub account, then you can head back to the Docker installation page, and you will see now that there is a button available in order for you to download Docker. So I'm just going to go ahead and click that, and the DMG installation file will get downloaded. You can click on it from the browser to begin the installation, or you can follow along with me, where I have navigated to my file system, where I found the DMG file, and then go ahead and double click on it to begin the installation. Once all of the steps are complete, you can just go ahead and drag the Docker icon into your applications directory, which will conclude the installation process. So this might take a couple of minutes, but once the installation is done, you can bring up your terminal window, where we can confirm that the Docker installation did indeed take place correctly. And to do that, we can execute docker -- version. And the output here confirms that version 18.09.2 of Docker has been installed on my system. Another tool which we require is Docker Compose, and this should have been installed as part of the Docker installation for Mac. In case you haven't used it before, Docker Compose is a tool which will allow you to run multi-container Docker applications. In our case, since our Hyperledger Fabric network will contain multiple containers, this is precisely what we require. And just to confirm that Docker Compose has been installed, you can run docker-compose -- version. And the output lets us know that version 1.23.2 has been installed for Docker Compose, at least in my case. Alright, with that, we have concluded the installation of Docker, but in order for our Hyperledger Fabric network to run, we also need to install the Golang programming language. So Hyperledger Fabric has been written in Golang, which is why we need to install this language. And to do that, you can navigate to golang.org/tl, from where you can download the installation files. You see here that there are multiple options available depending on your operating system. And there are different versions of Golang available. And at the time of this recording, version 1.12 is the latest one. I am, however, going to install version 1.11.9, which I know is compatible with version 1.4 of Hyperledger Fabric. So to avoid any potential installation issues, you can stick with the versions which I am using over here. But since newer versions of Hyperledger Fabric keep coming out every few weeks, it is possible that the latest versions of Golang will work with the newest versions of Fabric. So now I'm just going to go ahead and install this version of Golang, and this is going to be a .pkg file. And just as with the Docker installer, I'm going to go to the file system where the file has been downloaded, and then double click on it in order to begin the installation process. So we confirm that this is an installation for Go. And I'm just going to stick with the default parameters, so just go ahead and hit continue. And then confirm the installation type and hit install. Enter the admin credentials when prompted. And the installation should be done within a minute. So now that Golang has been installed along with Docker, you can just close out of this installation. And if you'd like, you can keep this installation file in case you run into any issues. But once that is done, you can head back to the terminal window, from where we will edit the .bash_profile file to ensure that the Go binaries are available in the path. So I'm using the nano text editor in order to edit this file. I'm going to include one new export statement, and this is going to be to set the Go path environment variable. So Docker and Go are the two prerequisites which we have covered the installation of. However, there are a couple of other tools which you might need as well. If you don't have Python installed on your system, then do go ahead and make sure that you have version 2.7 of Python running. This version of Python is required for the Node SDK in order to write smart contracts for Hyperledger Fabric using Node.js. Once the installation is done, do make sure that your path variable has been set up to point to this version of Python. Once that is done, you can go ahead and save this .bash profile file. And once you're back at the terminal, you can ensure that the changes which you have made do take effect by running source followed by the location of your bash profile file. Now there is another prerequisite for some of the smart contracts or chain code we will be deploying during the labs of this learning path. Hyperledger Fabric supports chain code written in a few general purpose languages including Java and Node.js, and we will be creating a new contract using Node.js, for which you need Node installed. In my case, I have already set up Node version 10.15.1. So if you do wish to develop a contract using Node.js, then make sure that you have some version of Node installed. And if you'd like to play it safe, and make sure that you're using a version of Node which does work with Fabric, then you can install this very same version. With that done, we can confirm the Python installation. So I'm running python -- version, which confirms that my current version of Python is 2.7.15. So with that, we have fulfilled all of the prerequisites in order to set up and install a Hyperledger Fabric network. That is something we will begin to do in the next video. So now that all the prerequisites have been installed for Hyperledger Fabric, we can go ahead and set up the Fabric network. To do that, we will be downloading several files which Hyperledger Fabric makes available to us through their GitHub page. And these will include a lot of scripts as well as a number of binaries, which will greatly reduce the workload in setting up a Hyperledger Fabric network. To download all of these files, I'm creating a brand new directory in my workspace. So to start off, I'm creating a directory called Hyperledger within my home directory and then cding into it. So now that I'm within the root directory of my workspace for Hyperledger, I'm going to go ahead and download and then execute an installation script. So I'm using curl in order to download the installation script and then running it on the bash shell. And this script will perform a few tasks. Firstly, it'll clone a Fabric samples repository on GitHub, which includes a lot of installation scripts, configuration files, as well as a number of chain code samples. It'll download the correct platform-specific binaries for the Hyperledger Fabric installation, and then we'll also download a number of Docker images for the various components of our Fabric network. Note the three arguments which we pass to this bash script, which are 1.4.1, 1.4.1 again, and 0.4.15. These are the versions of Hyperledger Fabric, the Fabric CA MSP tools, and a version for third-party images as well. So on running this command, you can in fact see exactly what is going on. To start off, all of the files are downloaded from this Hyperledger/Fabric samples repo on GitHub. And the output here shows you that it's version 1.4.1 of the Fabric samples which are being downloaded. Once the files are ready, then this will go ahead and install the Hyperledger Fabric binaries which you require. This includes the Fabric and the Fabric CA client binaries. This is followed by the download of all of the Docker images which are required in order for us to provision the various components which make up our Fabric network. The Fabric network will include peers for which we need this peer image. And then following that, there is also an image for the ordering service. The orderer makes use of a CCENV image, which is something which is required in order for us to build chain code. So there are several different Docker images which we will require for the Fabric network, and all of those, along with their dependencies, will be pulled by executing the script. There is a Docker image for the Fabric CA, and there is also one for CouchDB. So this is the database which will be used in order to store the state of the Hyperledger Fabric network. Kafka is another image which is downloaded, and this is one we will actually not be using in this learning path. So if you wish to configure your ordering service to make use of Kafka as the ordering mechanism, then the Docker image which you require for it will already be present in your system. Along with Kafka, Zookeeper will also be available, and this is something which you could use if you were to set up Fabric in a production environment. That said though, you can scroll down to the end of this output where you can get a list of all of the Docker images which have been pulled by the script. Clearly, there are plenty of these, which is why the execution of the script can take a while. However, once you are done, the first step of our Fabric network setup has been completed. We can now take a look at what files have been downloaded and then go ahead and set up the Fabric network. In the previous video, we downloaded and then executed a script which has downloaded a lot of the files which we require in order to set up the Hyperledger Fabric network. We will now take a look at exactly what those files are and how we can use them going forward. So I'm now within my workspace directory, and I'll go ahead and clear the terminal and open up this directory within a text editor. So I'm using Sublime Text here, and you can use any text editor which you're comfortable with. So within this directory, you can see that a new folder called fabric-samples has come up, and this is the one which has been downloaded from GitHub. Within this Fabric samples directory, we have everything we need in order to build out our Fabric network. You can see here that this includes not just a number of binaries, but also some sample chain code. There are also several scripts which will allow us to set up a basic Fabric network, provision a network with multiple orgs, and so on. Whatever approach you adopt, you will need to make use of some binaries. And in order to examine those binaries, we can expand the contents of this bin directory. So within this, you will see a handful of files. Config.txgen is something which is used in order to provision channels on the network. Cryptogen can be used in order to issue keys for various participants in your network. And there are also binaries for the Fabric CA client, the orderer, and the peer. These are the binaries which are used to interact with those respective components in our Fabric network. In addition to those binaries, we can now take a look at the script which we executed in order to download all of the components. So if you expand the scripts directory, there is one script called bootstrap.sh. So this is what was downloaded and executed by us in the previous video. And just to take stock of what was done, we can quickly go over the script. So by default, this will set the version number of Fabric as well as the Fabric CA client to 1.4.0. We had overridden this effectively by specifying versions 1.4.1 for each of them when running the script. Similarly, the third-party image version was also something which we had passed along, but this is the default value which it will use. There are different versions of Fabric available for different architectures, and here the script finds out what OS you're running and the specific architecture by running the uname command. It will also make sure that you are currently in the root Fabric samples directory, which has been checked out from GitHub, and it will take a few steps to ensure that. For example, if you're within the scripts directory, it will navigate up one directory level. And if you happen to be in some other location on your file system, then the script just won't be able to execute. So following all of this initial setup, it is time for the script to pull all the required Docker images, starting with the image for Fabric. And do note here that the specific version of Fabric is something which is obtained from the command line arguments to the script. So in our case, it was version 1.4.1 of Fabric which was installed. The third-party Docker images which are downloaded include ones for CouchDB, Kafka, and Zookeeper, followed by the pulling of the image for the Fabric CA. Fabric CA is an implementation of a membership service provider which we can use to provision certificate authorities and to define the valid identities for our Fabric network. And following the download of the Docker images, the binaries which we just took a look at are also downloaded, and you can see exactly how that takes place over here. But once the download is complete, you will observe that the specific versions of the binaries which have been downloaded are suited to your own operating system and architecture. And following the installation of the binaries, the script will also look to see if you have Docker installed on your system, without which this installation cannot proceed. Since we did fulfill that prerequisite earlier, we will be proceeding over to the next step, which is to install the binaries which have been downloaded. And you can see that there is a bunch of setup work which goes on. So the version of Fabric, Fabric CA, and the third-party images which you pass to the script will be used. And if you did not pass in these arguments, then the default value of 1.4.0 will be used for Fabric as well as Fabric CA. And once everything is downloaded, the binaries and the Docker images will be installed. So we now have a clear idea of how this initial setup takes place for Fabric. And just to make sure that you do indeed have everything which you need, you can cd into the Fabric samples directory which was downloaded, and then explicitly execute this bootstrap.sh script. And because we already downloaded everything previously, on this occasion the script will execute in just a matter of seconds. And you can confirm that the output was exactly the same as what it was before once the Fabric samples directory was downloaded from GitHub. Out of all of the binaries and Docker images which we currently have on our system, we will now go ahead and make use of exactly those components which we need in order to provision our Fabric network. We will be doing that, however, in the next video. We now have all the files which we need, which includes the Docker images, in order to provision a Hyperledger Fabric network. Later on, we will be deploying a smart contract or chain code to this network, and this is going to be some chain code which will effectively keep track of an inventory of fruits. To represent this, we will now create a directory called fruit counter and then cd into it. And then from there, we will copy over the binaries which we will need in order to set up our network. This we can simply copy over from the Fabric samples directory, which we just took a look at. And I'm going to copy with the -r option so that all the contents are copied recursively. So we will just copy over all of the binaries over here. And then we can just confirm that this transfer did indeed take place by running ls. And yes, we now have a bin directory within our fruit counter directory. Seeding into it, we can once more run an ls to examine the contents. And we now have all of the binaries which we saw previously, which includes the configs txgen, cryptogen, and so on. Moving now back to the text editor, which I had brought up previously, and in which the Hyperledger root directory of the project is currently up. Within that Hyperledger directory is this fruit counter directory, which was just created, and we can now expand that and the bin directory as well. So now that all the binaries are here, within the fruit counter directory, we can go ahead and create a new file. And we will now, in fact, create a couple of new files in order to define what our Hyperledger Fabric network will look like. And now that we have a blank file to work with, I'll go ahead and paste the contents of the definition of a channel. Every channel in a Hyperledger Fabric network has its own blockchain. It will connect a number of peer nodes together, and these peers effectively have their own line of communication by means of this channel. The channel definition includes a genesis block as well as what needs to be included in the channel artifacts, and these are defined in the profile section at the end of this YAML file. And that profile section in turn references some of the other components which we will define earlier on in the YAML file. The Fabric network which we will provision right now is a very simple one. All it contains is a single peer and a single ordering node, as well as a single certificate authority. As far as this channel which we're setting up is concerned, it only needs to connect the peer with the ordering service. So I'm now just going to go ahead and save this file and call it configstx.yaml. and I can walk you through each of the details which have been included in this configuration. Starting with the organizations. So here we specify the different organizations which are part of this channel. And here we have also specified the orderer as an organization. This is something which is required for this channel configuration. So here we are referring to this ordering service as an orderer org. Note that the use of the ampersand denotes that this is a definition which we will be referencing later on within this YAML file. So we give this a name called orderer org, and the ID field here represents the identifier which we would like to set for the MSP for this organization. So we call this orderer MSP. We follow this up with the directory for this MSP, and that is where all of the valid certificates for this organization will be available. This is a directory which will be created just a little later in the demo. And moving along now to the real organization in our channel, which we will call org1 MSP, and then we also give it an ID of org1 MSP. Similar to what we did previously, we specify an MSP directory, and that once again is a directory which will be created later on. And then we follow that up with an anchor peers definition. So these are the peers which can be used for cross-org communication. In our Fabric network, this org1 organization will only have a single peer, and we are effectively setting that peer as this anchor peer. This host name which I have set as peer0.org1.lunicon.com needs to match the name for the peer's Docker container in the docker compose.yaml file which we will be provisioning later on. That peer will also be listening on the port 7051. So now that the organizations block of our configstx.yaml has been defined, we will move along to the application block. If you would like your channel to include multiple organizations, then you can use the same structure in order to add additional organizations. And remember to add at least one anchor peer in each org. And within the application block, we don't need to include any specific configurations, and we simply create an organization section and leave it blank. This block is meant for application type transactions, and we won't be getting into the details of these configurations. And we proceed now to the orderer block, where we configure the ordering service for our channel definition. This orderer definition will be called orderer defaults, and the type of orderer is going to be solo. This is something which is meant for use in dev environments and is definitely not recommended for production. The addresses section here references a Docker container which will be provisioned, and the definition for that container will be in the Docker Compose YAML file we will create later on in this course. There are some batch parameters here, including the batch timeout field, which determines the amount of time to wait before creating a batch. The size of the batch is also configured using this batch size field. We can also set our ordering service to be Kafka, which is recommended for use in production. And this is not something we will get into the details of for this course, since we will be using solo ordering. I'm moving along to the last section of this YAML file, which is the profile section. So we have two profiles defined here. The first one is called OneOrg Orderer Genesis, and this includes the details needed to create the Genesis block for the channel. And this represents a channel which contains one ordering node and one organization, which includes a single peer. The orderer for this profile references the orderer defaults anchor, which we defined in the orderer block just before the profiles block. So after the orderer for the channel, we define the consortium. So the name of the consortium is sample consortium, and we define each of the organizations which need to be part of this consortium. In our case, we only have a single org which we reference within that organization section. And then we have the definition for a second profile called OneOrg channel, and this is where we define a channel for this sample consortium. And with that, we have now successfully defined this configstx.yaml file. What is ultimately used from this file is going to be what is defined in the profile section, and that profile section references the orderer and the organizations which we have defined earlier in the YAML file. The profile called oneOrgOrdererGenesis represents the genesis block for a channel, while the second profile called oneOrgChannel will be used in order to generate the artifacts for the channel. So the network which we will provision will contain only a single channel, and the definition of that channel is within this file. In the previous video, we created the configstx.yaml file, which defines the first channel we wish to provision on our Hyperledger Fabric network. This channel is as simple as we could possibly make it. It includes just one organization which has one peer, and then there is the ordering service it must connect to. So we essentially have two entities in our Hyperledger Fabric network, and we need to establish identities for them, which they can use in order to connect with the network. Identities in Hyperledger Fabric are established by means of X509 certificates, and while it is expected that each organization will provision its own certificates for use in production, in the case of a dev or test environment, we can make use of the CryptoGen tool, which is packaged along with Fabric. This CryptoGen tool will require a separate configuration file, which we will now code up by first closing this configstx.yaml. And within this config file, we need to define each of the participants in our Fabric network. So once the file is closed, I'm going to provision a new file, and this will also be a YAML file. And I'll go ahead and paste the contents of this file, and then name it crypto-config.yaml. So let us go over the contents of this file. As I mentioned earlier, this includes the definition of each of the entities for which certificates need to be issued. In the case of our network, there is one ordering node which requires a certificate, and then there is also a single organization with one peer. Starting with the orderer definition, this comes under the section orderer orgs in the YAML file. We give this orderer a name, and then we also specify the domain to which they belong. So the domain here is lunicorn.com, and then within the specs block, we set a host name for the orderer, which is orderer. This definition will ensure that a certificate will be provisioned for orderer.lunicorn.com. So you'll need to make sure that the domain and the host name have been set up correctly over here. So while this will set up all the cryptographic material for the orderer, we move along now to the peer, which is part of our Hyperledger Fabric network. So all of the peers will be defined within the peer orgs block. And since we only have one peer, we can set this a name of org1, and then we set the domain for this org to org1.lunicorn.com. For all of the peers which are part of this organization, we can explicitly define them under a specs block. Alternatively, we can also make use of a template block, which will sequentially create a number of peers based on a pre-configured template. In our case, we have set the number of peers to create out of the template to 1. This peer will be referenced as peer0.org1.lunicorn.com. If we had included additional peers, they would be referenced as peer 1, peer 2, and so on. While this will create an admin certificate for the peer, we can also specify additional users for whom certificates need to be created. In our case, within the user block, we say that one additional user will need to be provisioned on the peer, so a certificate will be issued for that user as well. So with this crypto-config.yaml file defined, we can head over now to the terminal and then to the directory where we have defined this YAML file. And then from there, we invoke the CryptoGen binary so that it will generate all of the cryptographic material for what we have defined within the crypto-config.yaml file. This cryptographic material will not just include the certificates and the private keys, but they also need to be structured in a particular manner. So let us go ahead and run CryptoGen generate and specify the location of our crypto-config file as the config argument. So when we execute this, this will just take a handful of seconds to run, and the output confirms that certificates have been issued for org1.lunicon.com. But in order to see exactly what has been provisioned, we can head back to the text editor, where you can observe that a new directory called cryptoconfig has been created now. To see exactly what cryptographic material has been created and how they have been structured, we expand this directory, and within that we see two subdirectories which correspond to the two big blocks within our cryptoconfig YAML file. So we can now expand the contents of the orderer organizations to see what has been generated here. And within that, there is one representing the domain for the orderer, which is lunicon.com. And then within that, we see 5 different subdirectories. There is one for the certificate authority for this organization. There is one for its MSP. There is one corresponding to the orderers, another one called TLSCA. And then finally, there is a users directory. We can go through them one by one and examine the contents. So the cryptographic material which has been provisioned for the CA of this orderer includes a certificate file, which you can see at the top. This is the .pem file. And then the other file which you see is the private key which has been generated for the CA. We can minimize this directory and then view the contents of the MSP folder. And this includes 3 subfolders. The MSP will need to define who the valid identities are and the valid certificate authorities whose issued identities can be trusted on the network. So when we expand the admin search directory, we view the certificate which has been issued for the administrator of this MSP. And then when we expand this CA search directory, we see the exact same CA certificate which we saw previously. Similarly, when we expand TLS CA search, this also includes a certificate, and this is something we will see later on within the TLS CA directory. This certificate is something which can be used in order to secure the communication channels on the network. So we can go ahead and minimize this MSP directory and head over to orderers, which includes a subdirectory corresponding to the host of the orderer. So within orderer.lunicon.com, there is once again a directory for MSP and then another one for TLS. Within the MSP directory, you have different sets of subdirectories once more. We won't get into each of these now, but these will include the certificates of those entities which the orderer has deemed valid. Heading over now to the TLS directory, and this includes 2 certificate files, one for the CA and another one for the host itself. The private key to be used by the orderer is also included within the server.key file. We can now minimize this orderer subdirectory within our orderer organizations and then head over to TLSCA. And then this includes the certificate as well as the corresponding private key, which can be used to encrypt traffic in the Hyperledger Fabric network. Heading over now to the users directory. And there is just one user in the orderer organization, and this is an administrator. So for that administrator, there is cryptographic material, which includes an MSP. And when you expand this, once again, you will find the 5 directories which we saw previously. And each of the certificates which are stored here can be viewed by expanding each of the subdirectories. So within the admin search directory, we have the one for admin@lunicon.com. And then within CA search, we see the same certificate for the CA. And then within the key store directory for this admin user, we get the private key for this admin. And just for completeness, we can expand the contents of sign search, which includes the admin certificate once more. And then the TLS certificate we saw previously will be visible within the TLS CA search directory again. So each time we see an MSP subdirectory, we get the list of valid identities with which this host can communicate in the form of their digital certificates. And for each entity which wishes to use TLS in order to encrypt traffic, the certificate, the private key, as well as the CA who issued the certificate can be obtained within this TLS directory. We have now examined all of the cryptographic material generated for the orderer in our Fabric network, and in the next video, we will take a look at what has been generated for the peer organization. In the previous video, we defined this cryptoconfig.yaml file in order to specify the entities in our Hyperledger Fabric network for whom cryptographic material needs to be generated. This file was fed as input to the CryptoGen binary, which then went on to generate a host of certificates and private keys for various entities which will make up the network. All of those certificates and keys have also been arranged in a specific format within a directory structure in order for the Fabric network to access them. We saw exactly what was provisioned for the orderer organization. We can now take a look at what has been created for the peer in our network. So expanding the peer organizations directory, we see there is a subdirectory for the single organization in our network. This is the one called org1. So when we expand org1.lunicon.com, we notice that there is a structure similar to what we had on the side of the orderer, except that we now have a peers directory instead of an orderers directory. So when we examine the contents here by expanding the CA directory, just as we did previously on the orderer, a certificate has been issued for the certificate authority for this organization, and the corresponding private key is also available here. Expanding the MSP, all of the certificates for the administrator for this organization, the CA, and the certificates to be used for TLS are included. When we expand the peers directory, we observe that the single peer which has been generated is peer0.org1.lunicon.com. You will remember that within our cryptoconfig.yaml file, we made use of a template in order to define this peer, and the first peer to be created with the template will be labeled peer0. Had we set the peer count to 2, in addition to peer0, there would also be peer1, and the sequence would go on depending on how many peers we had set to be provisioned from that template. The TLSCA directory will include once again an MSP subdirectory and a TLS subdirectory. And again, the MSP directory has a similar set of subdirectories. Moving along now to the TLSCA directory. Again, this is similar to what we saw on the side of the orderer, except this time the certificate is one for this organization. And finally, when we head over to users, you'll observe that there is not only an admin user on this occasion, but there is also one called user1. This is because we had set the user count to 1 in the cryptoconfig.yaml file for this particular organization. So similar to how certificates have been issued for the peers, there will also be ones issued for users depending on what we have specified in the YAML file. I won't go into the details, but you can just expand each of the subdirectories here in order to confirm that the contents are similar to what we saw on the side of the orderer organization. And when you expand the directory for the user, you will see there is a similar structure here as well. So I'll again fast forward the expanding of this directory. And then once all the cryptographic material has been checked, we can minimize this cryptoconfig folder and then go ahead and create a new connection file within that directory. So I'm now going to create a brand new file, and then we'll paste the contents of this JSON file. This file will be named connection.json when we save it. And this connection file, which is referred to as a connection profile, will be used by client applications which wish to interact with the Fabric network. It needs to contain all of the details they need in order to invoke transactions. And this is used to describe the various components which make up a Hyperledger Fabric network. The components include peers, orderers, certificate authorities, and so on. And we start off by setting a name for this connection profile, which we will call basic network, and set its version as 1.0.0. We then specify a client for this connection, which is going to be on org1, and we also define the timeouts for the peer and the orderer. The next block defines the channels which should be part of the network. So there is a channel called my channel, and there is one orderer and one peer which is connected to it. We had previously defined this channel in the config.tx.yaml file. However, in order for transactions to know exactly what the channels are, we need to define it within this connection profile file. Following the channels, we define the organizations which are part of the network, and we don't need to specify all of the organizations which are part of the network, but just those organizations which a transaction needs in order to complete its processing. In our case, however, there is just a single organization which we define within this block. This includes not only the peers which make up the organization, but also its corresponding certificate authority. Moving along now to the orderers for this network, we need to specify where exactly the orderer can be reached in terms of the host, the port, and also the protocol which is used to communicate with it. It is gRPC in this case. Similarly, we also have a peer definition, and our peer, which is peer0.org1.lunicon.com, will be running as a Docker container which will be accessible on port 7051 of our local host. And the certificate authority will be available on port 7054, also running as a Docker container accessible through our local host. So that concludes our definition of this connection profile, which includes all of the components which a transaction will need in order to be fully processed in the Fabric network. So with this file defined, we can go ahead and save it. So I'm going to call this connection.json. And once this file is saved, let us take a quick look at what we have provisioned so far. By means of a script which is provided by Hyperledger Fabric, we managed to download all of the Docker images which we will require in order to provision the Fabric network. And then following that, defined 3 different configuration files. One of these is called config.tx.yaml, which defines the first channel which we wish to provision in our network. That channel includes one orderer and a single organization which has just one peer node. Following that, we define the cryptoconfig.yaml file in order to generate all of the cryptographic material which we will need, which includes digital certificates as well as the corresponding private keys, all arranged in a directory structure which the Fabric network understands. And now, with this definition of this connection.json file, we have set up a connection profile which can be used by applications in order to invoke transactions on the Hyperledger Fabric network. To invoke these transactions, they will need to know what channels are present in the network, what the contents of those channels are, the organizations and the corresponding endorsing peers to which transactions can be submitted, as well as the hosts and ports at which the orderer, the peer, and the certificate authority needed for the transaction will be accessible. So with that, we can close down this file as well as the cryptoconfig.yaml file. These config files, as well as the cryptographic material which we generated, will be used within the Docker container definitions, which we will take a look at later in this learning path. In this exercise, you will start off by listing out the different components which make up a Hyperledger Fabric network. During this course, we have performed the initial setup in order to provision a Fabric network, and we saw that this includes a number of different components. You will need to recall exactly what those are and what purpose each of them serve. Next, you will describe the configs.tx.yaml file which one can define for a Fabric network. During this course, we did spend some time preparing this file, and it does serve a very important purpose. You will need to identify what exactly that is and the specific details which are present within this configs.tx file. And finally, you will describe the connection profile file for a Fabric network. Again, there were many different files which we did work on during this course, and the connection profile was one of them. The name we set for this was connection.json, and as the name implies, it does include a lot of connection parameters for the Fabric network. You will need to recall exactly what those are and what purpose each of them serves. These topics were all covered during this course, so please pause this video and spend some time in doing each of the tasks in this exercise on your own. For the first task in the exercise, you needed to identify the different components which make up a Hyperledger Fabric network. While there are many different components which you can include, the ones which are necessary are the ordering service, and this is something which can be set to either solo if you're running it in a dev or test environment, or Kafka, which is recommended for a production setting. The ordering service will receive a collection of endorsed transactions from client applications, and its function is to arrange them in an order before it can be validated and then written to the blockchain. Another component of a Fabric network is a peer, and there needs to be at least one in any network. A peer will belong to an organization, and an organization in turn can have several peers. And of course, within a Fabric network, especially in a production setting, you may end up with several organizations. When you do have a multi-organization Fabric network, then you will need connections between those organizations, and for that you will need to make use of anchor peers, which allow inter-organization communication on the network. Multiple peers in the network can also be connected together by means of channels. Another component in a Fabric network is a certificate authority, and the purpose of this is to issue identities which can be used in order to communicate with the Fabric network. In a Fabric network, it is possible for each organization to have its own certificate authority and issue its own identities. So while these were the components of the network which we discussed during this course, there will be one more which will be used by a peer in an organization in order to record and access the state of the network, and this is a CouchDB component. The state of the network will include data about smart contracts which have been deployed to it, as well as the state variables in that contract. Each of these components will be run as Docker containers, and once we define the interconnections between these components, we will be able to bring up the network, provision channels, and then deploy and work with smart contracts. Moving along now to the next task in the exercise, where you needed to describe the configstx.yaml file. This is meant to represent the shared network configuration for a Fabric network, which includes the definition of the first channel for that network. Since each channel will have its very own blockchain, this configstx file will include the definition of the genesis block for the channel, as well as the various channel artifacts. Both of these will include the ordering service, as well as the organizations which are part of the network and which need to be connected together in order to form the channel. Given this is a YAML file, we can divide the configstx file into different sections or blocks. One of these is the profiles block, and this includes definitions for the genesis block as well as the initial channel configuration. A genesis block definition will include an orderer as well as a collection of consortiums, which in turn will include a number of organizations. This is meant to connect the different organizations in the channel to each other as well as to an ordering service. The profile section will typically reference the orderer and organizations which are defined elsewhere in the YAML file, which is why there is an organizations block as well. This includes details for the MSP for the organization as well as the peers which are part of that organization and the anchor peers of that org as well. Then there is the section for the orderer, which includes details about the ordering service, including what type of ordering service is it? Is it solo or Kafka? And the URL at which the ordering service can be accessed. Which moves us along now to the last task for this exercise, which was to describe the connection profile file which we provisioned for the Fabric network. This is a file which we saved as connection.json, and it includes all the information required by an application in order to configure a gateway. This gateway will be required in order to communicate with the Fabric network and invoke transactions, and the Fabric network itself will handle the provisioning of this gateway and the network interactions. All we need to do is supply the information to define the gateway. Once that is done, all developers of smart contracts can focus purely on the business logic to invoke transactions rather than worry about communicating those transactions over to the peers and orderers and so on. Setting up this connection profile, though, does involve a one-time configuration, and it needs to be done by someone who has a high-level view of what the different components of the Fabric network are. They will also need to know how each of those components can be accessed and how they need to be interconnected in the case of channels. So the components one can define within the connection profile include the peers which make up the Fabric network, as well as the ordering service. And in order to validate identities, this will also need to know the different certificate authorities in the network. The one setting up the connection profile will need to know exactly which host and which port each of these services are accessible at. And then within the connection profile, they can also set up the various channels which need to be part of the network. Previously in this learning path, we created a few configuration files for our Hyperledger Fabric network. This included a configstx.yaml file, which included the configuration for a channel, and we set that channel to have one orderer and one organization running one peer. That channel configuration file references an orderer and a peer node, which have yet to be defined within a Docker Compose YAML file. That is exactly what we will be doing in this video. So now I'm in the workspace directory of a project we created previously called Fruit Counter. The name represents a smart contract we will soon be defining and then installing on this network, which will keep count of an inventory of fruits. So within this directory, let us now go ahead and create a new directory called config. With that done, we have executed one more step which was required in order to provision our Fabric network. And within that config directory, we will be provisioning a Genesis block for our channel. And for that, we will be using the configstx.yaml file, which we defined previously. And that same config file will also be used in order to provision channel artifacts for the channel we define within that. Just to reiterate, each channel in a Hyperledger Fabric network will have its own blockchain. And for that, we will need to provision a Genesis block. Before we get to that, there are a few environment variables which we will need to set up. Firstly, we need to ensure that the Go binaries are available in the path variable. And in addition to that, we also include the binaries for the Hyperledger Fabric network setup, which is available in the bin subdirectory of our project workspace in this path variable. And the third addition we make to the path variable is the current workspace directory itself. So with the path variable set, we will define one more variable called fabric_cfg_path. As the name implies, this represents the path in which the Fabric configuration details can be found, and we set this to our current directory, which is the project root directory. And the next environment variable to set up is the name of the channel which we will be provisioning. So we set the environment variable channel_name to be equal to my channel. So the Fabric config path and the channel name variables will be referenced a few times, just a little later in the demo. But the next step for us is to create the Genesis block for the new channel we are about to provision. To do that, we can make use of the configstxgen binary, which is available within the bin directory. And this is a binary which will implicitly reference the configstx.yaml file which we defined previously. In order to provision the Genesis block, it needs to reference one of the profiles which we set within that channel, and we can pass the name of the profile to the profile argument for this binary. So the name of that profile is one.org_orderer_genesis. The next argument which we pass along is the output file for the Genesis block, and we will create a file called genesis.block within the config directory we just created. And when we execute this, that Genesis block has been provisioned, and in order to view that Genesis block, you can either navigate to it using the shell, or in my case, I'm going to bring up my text editor and then head over to this config directory. Within that, this genesis.block has been created, and if you were to examine its contents, you'll likely just see a sequence of numbers. This is because this Genesis block has been encrypted. So this includes one of the two config files for our channel, and the next one is to generate the channel artifacts file. To do this, we once again use the configs.txgen binary, and again, this will reference the configs.tx.yaml file implicitly. But on this occasion, we reference the other profile we defined within that file, which is one org channel. This is a channel which has one orderer node and one peer in an organization, and the details of the orderer and the peer are within the YAML file. The details of the channel will be within this channel.tx file, which will once again be created within the config directory, and this file location is passed as a value for the output create channel tx argument. We can also set the ID for this channel using the channel ID argument, and that ID is going to be the name which we just defined in our environment variable previously, which is my channel. So with that done, a channel called my channel has been generated, whose details are included within this channel.tx file within our config directory. I'll now bring up my text editor, where there is a confirmation that this channel.tx file has been created. And once again, this is an encrypted file, so if you were to view its contents, it won't really make any sense. So now that we have created the Genesis block and the channel artifacts, we can add these to whatever we have already created previously. This includes all of the cryptographic material which we generated for the orderer as well as the peer in our network. And then following that, there was also a connection profile which included all of the details of the Fabric network which are required for an application to initiate a transaction. There is just one more file which we need to define now before we can provision our Fabric network, and this is going to be the docker compose.yaml file. We will do that though in the next video. In the previous video, we made use of the configs.txgen tool in order to create the Genesis block for our channel, and also created this channel.tx file, which can be used in order to initiate the transaction to create our channel. So with these, we now have the configuration files as well as the cryptographic material needed for our Fabric network. But in order to put all of those together, we need to define the docker compose YAML file. In case you haven't used one of these before, this is a file in which you can specify a multi-container Docker application. Since our Fabric network is going to include an orderer, a peer, a certificate authority, that is exactly what it is, a multi-container application. So let us now go ahead and create a new file, which will be our Docker Compose YAML file. And this I'm going to create in the fruit counter project directory. Once this blank file is available, as with the previous files, I'll first paste the contents and then walk you over the components one at a time. To start off with, we specify the version of the Docker Compose YAML which we will be using, and I'm sticking with version number 2. Within this YAML file, we can specify the various components which make up our application, and this can include networks as well. While there are several advanced network configurations possible, we will stick with the standard basic network offered by Docker. Following that, we get to the meat of our Fabric network, which are the various services which constitute that network. A service in Docker can be thought of as the definition of a running container, and the first container we define within this Docker Compose YAML file represents the certificate authority for our network. The name of this service is ca.lunicorn.com, and then let us go ahead with its definition, starting with the image, that is the Docker image, from which this container needs to be built out. This image will include a lot of the important information for a container, which includes the certificate authority application, all of its dependencies, as well as the user space of the operating system which it can run with. So following the image definition, we specify the environment variables which this container must be initialized with. All of these environment variables are related to Fabric CA, which is Hyperledger's implementation of a membership service provider. So we set the home directory as well as the name of the certificate authority, and following that, we specify the location within the container of the CA's own certificate file as well as the corresponding private key. These are two of the files which were generated by the CryptoGen tool earlier on in this learning path. The values for these variables are directory paths in the containers file system, and we will ensure that the cryptographic material which we generated earlier will be available to this container at this specified location. We will be doing that in the volume section for the definition of this service. So after the environment variables, we map a port number of the host machine on which this container will run to a port in the container in which this CA application will be listening for connections. The certificate authority service will be listening on port 7054, and we map port 7054 on the host machine to the same port number in the container. In the command section, we can define the shell command which needs to be executed once the container is brought up. And since we need to start up the Fabric CA server, that is the command which we execute here, Fabric CA server start, and then we follow that up with the credentials to start up the Fabric server. And by default, these are admin and admin PW, which moves us along now to the volume section. And this is where we define the directory in the host machine, which will map onto a directory within the container. Since this container will be running on our local machine, we can ensure over here that the cryptographic material for this CA, which we generated previously, will be made available to the container. So we map the crypto config /peer organizations /org1.lunicon.com/CA directory on our local machine to a directory within the container. You will note that the container directory corresponds to the environment variables which we had specified for the Fabric server certificate and the key file. So you can scroll over to the right to view the entire directory path. So what we have effectively defined here is that the files which were generated for the certificate authority, including its certificate and the corresponding private key when we ran the CryptoGen tool, will be made available to this container in the specified directory. The volume definition in this file follows a format of a source directory on the host, followed by a colon, and then a destination directory in a container. So now that our volume has been defined, we can specify a name for the container, which in this case we will set to the same name as the service, since this service will only contain a single container. And then finally, the name of the network in which the service will run is going to be basic, which we had defined previously. Now there is just one more detail which needs to be populated for this certificate authority service, and this is to do with the last of the four environment variables which we defined, specifically Fabric CA server CA key file. So this is the private key file for the certificate authority, and we have deliberately left the path incomplete because the name of this private key file will be different for each person who runs the CryptoGen tool. So to get the actual name of the file, we can expand the crypto config directory, and then from there we can navigate over to peer organizations. And when you expand that, there is a subdirectory called org1.lunicon.com for the single org in our Fabric network, and within that there is a directory called CA. So the CryptoGen tool automatically created the certificate and the private key file for the certificate authority of this organization and placed them within this subdirectory. While the name of the generated certificate file is predictable, the name of the private key file is not. So now I'm going to extract the name of this private key file, which in my case begins with 2e4. You can view the contents of the private key here. And then I'm going to copy over the file name from this text editor. Once I have that name, I'll just close this file and then go ahead and complete the definition of this environment variable to point to the correct private key file. Once that is done, the definition of this particular service for the certificate authority is complete. And we can now move on to the next service in our application, which is for the orderer. We will continue with that, however, in the next video. Now that we have defined the container which will function as the certificate authority in our Fabric network, it is time to define the container for the ordering service. So the name of this service is orderer.lunicorn.com, and this again contains a single container called orderer.lunicorn.com again. The container will be built out of an image called hyperledger/fabric-orderer, and this is something which we already have downloaded on our system. We then specify a bunch of environment variables for this particular node, and you'll notice that one of these points to the Genesis block which we provisioned for the channel. So we'll need to make sure that the Genesis block which we provisioned on our local host will be made available to this container. And as with the previous service, we will make sure of that in the volumes block. When defining a service, you can also specify the working directory for each of the containers. And in this case, we will make sure that we are in the directory where the orderer binary will be available, because as soon as the container is brought up, we will be running the command orderer in order to bring up the ordering service. And the port in which the ordering service will be listening is 7050. You may recall that for both the certificate authority as well as the ordering service, we had specified the port numbers in which they will be available in the connection.json file. It is those same port numbers which need to be used here as well. Following the port definition, we move along to the volumes, and here we make sure that a few different files are available to the container. At the very top, the config directory in our local host, that is the one which includes the Genesis block as well as the channel details, will be available in the container directory /etc/hyperledger/config-tx. We also make sure that all of the cryptographic material for both the orderer as well as the only peer in our network is also available to this container. And then finally, we specify the network, and this service will once again run in the basic network, which takes us along to the next service, which represents the peer in our network. And this is going to be called peer0.org1.lunicorn.com, which is also the name of the container. We specify the image from which this peer will be built, and then define a number of environment variables again. You will notice that there are a lot of environment variables for this one, so I'll only explain the significant ones. There is one called core peer address, where we set this particular peer to listen to port 7051. This is where other applications will be able to communicate with this peer. The peer will need to make use of a state database, and that state database will be available in the CouchDB container at port 5984. The definition of that CouchDB container will come later on in this YAML file. So just as with the ordering service, we have a working directory specified here, which will include the peer binary, which we will use when we bring up the container in order to start the peer. The peer service will be listening on two different ports, 7051, where you can establish connections with the peer itself, and port 7053 can be used to subscribe for events, which moves us along now to the volumes. So here, we map the /var/run directory on our host machine to /host/var/run in the container. And then following that, we ensure that the cryptographic material for the peer MSP, as well as for all of the users which were generated for the peer, will be available to this container. The last volume here will make available the config files for both the channel as well as the Genesis block which we generated. So I'll just scroll to the right so there you can see the full paths. It is now time to move on to the next block, where you can specify dependencies for this particular container. So here we specify that this particular service for the peer depends on the orderer service and the CouchDB service, which we will define later. So this service will be brought up only once those services and their corresponding containers are up and running. And finally, this service will run in the basic network. Moving along now to the CouchDB container. Once we set a name for the service and the container and the image from which it needs to be built, we specify within the environment variables that the CouchDB will not have any username or password. So we just leave those fields blank. And the port in which the CouchDB service will be listening is 5984. So with that, all of the components which will make up our Hyperledger Fabric network have been defined within this YAML file. So just to recap, this includes the certificate authority, the ordering service, a peer, and a CouchDB container which serves as a state database. While this will provision a Fabric network, in order for us to interact with it, we will make use of a CLI, and we can define a container for that as well. So after we set a name for the service and the container and specify the image from which it needs to be built, we set the value of a TTY field to true. This will enable a shell on that container which we will be using in order to interact with our Fabric network. We also define a number of different environment variables and do make special note of the environment variables which begin with core_peer. These are effectively pointing the CLI container to the single peer in our network, which is peer 0 on org1. Later in the course, we will be using the peer binaries from the CLI container in order to install and then instantiate chain code. And you must be aware that the installation of the chain code will happen by default on peer 0 thanks to these environment variables which we have set up in the CLI. I'm just going to scroll over to the right so that you can see the full core peer MSP config path. And then just as before, we have a working directory definition as well as the shell command to run once the container is up. And here we will simply be ensuring that the shell which we will be working with is the bash shell. The volumes and networks definitions can be copied from here as is. So with that, we have now defined our application which will provision a Hyperledger Fabric network as well as a CLI which will allow us to interact with it. With that, we can just save this file, and this needs to be called docker-compose.yaml. Note once again that I'm saving this in the project root directory because this YAML file makes use of a lot of relative paths. So where you save this file does influence how it will run. So now that our YAML file is ready, we're almost ready to go. So I'm just going to minimize all of these folders here. And then following that, there is one extra step which we need to perform. And this is to include a new file which will contain some global environment variables. So once this file has been created, I'm just going to paste in one line over here. And this is going to be to set an environment variable called compose_project_name. And the name of our Docker Compose project is going to be net. And I'm now going to save down this file as .env. With this file saved, all of the coding and configurations in order to set up a Fabric network has been done. It is now time for us to use these files in order to provision our Fabric network, and that is exactly what we will do in the next video. I will just close out all of the files which I don't need in the text editor. We have now concluded all of the setup work for the provisioning of a Hyperledger Fabric network. In our Docker Compose YAML file, we have defined the 4 different containers which will make up the Fabric network, and in addition to that, we have created a CLI which we will use to interact with that network. It is now time for us to bring up each of the containers defined in the YAML file, but before we do that, we need to make sure that we are working with a clean slate. In my case, I have provisioned Hyperledger Fabric networks before this, and all of the keys which I had used during that were stored in this directory called .hfc key store within my home directory. Hyperledger Fabric uses this directory as a cache for the keys, and since the keys which were already there are no longer valid, I'll get rid of this directory just to prevent them from potentially interfering with future interactions. If you run into trouble while provisioning the Fabric network and you need to repeat the steps, then do ensure that you get rid of this directory as I am right now. So once that directory disappears, I am going to get rid of all of the running Docker containers in my environment. Once again, this is just to ensure that some of the remnants of my old Hyperledger Fabric network does not interfere with the one we are about to provision. So once we execute this command, all of the running Docker containers will be terminated. And the final cleanup step is to ensure that none of the resources which were defined within the Docker Compose YAML file are up and running. To do this, we execute the command docker compose-f dockercompose.yaml down. Since all of the running Docker containers have been taken down, the only thing which running this command will bring down is the network which was provisioned as defined within the Docker Compose YAML file. So once that network is gone, we are finally ready to bring up all of the Docker containers to provision our Hyperledger Fabric network. The command we execute is docker compose-f dockercompose.yaml up, and then following that, we specify the -d argument, which will bring up a list of containers in detached mode. We follow this up with the list of services defined within our Docker Compose file, which need to be brought up. So we bring up the 4 services which make up our Hyperledger Fabric network, which includes the CA, the orderer, the peer, and the CouchDB state database. And when we execute this command, we see a few different things taking place. First of all, a network called net_basic has been provisioned, and this is a logical network for our Docker services. And the 4 services which have been brought up are the CouchDB, CA, orderer, and peer services. And you will recall that we had specified within the YAML file that the peer service depends on the orderer and the CouchDB service. And it is for this reason that the peer service was brought up only after its dependencies were up and running. So now that the services are up, let us see which containers are currently running. And for that, we can execute docker ps from the command line. And this shows that there are 4 containers, one for each service, which are currently running. This output shows us the image from which the container was spawned, the command which was executed when it was brought up, also how long the containers have been up and running, and the port mappings for that container as well. For those of you who are not familiar with Docker, a service can have multiple containers running within it, all of them built from the same image. That allows you to have replicas of the application which you have defined within the container. In our case, with these 4 containers up and running, all the pieces of our Fabric network are now functional. However, in order for the network to be usable, we need to set up the channel which we had defined. For that to happen, some additional setup work is necessary, which includes the setting of some environment variables. So I'm now setting this variable msp_id to org1 msp. And this is required because we will be provisioning our channel from our peer node, which is part of org1, and we need to specify the local MSP when we provision that channel. This MSP ID should correspond to what we had set in the configstx.yaml file earlier on. Following that, we set another environment variable, and this is for the MSP config path, and this corresponds to the MSP subdirectory for the administrator of this peer MSP. This directory includes the certificates for the organization's certificate authority, the admin certificate as well as this admin user's private key, and also the TLS certificates. So with these environment variables set, we are now ready to initialize our channel. The way to do this is to run the command peer channel create from within the peer node in our network. So in order to run a shell command from within one of our running containers, which represents the peer, we run docker exec and then specify the environment variables which need to be passed along to that container. And this is done using the -e option. And then we follow that up by specifying the name of the container, which is peer0.org1.lunicon.com. So the docker exec command is a way for us to execute a command from the shell of one of our running containers. And we can set environment variables for that command to use using the -e flag. And once we have specified the name of the container, what follows is what will be executed within the shell of that container. So we run peer channel create, followed by the options for that command. This includes the host and port at which the ordering service can be located, which is in the container orderer.lunicon.com at port 7050. Following the -c option, we set the name of the channel which we wish to provision, and this will be called my channel. And then after that, we specify the file which includes all of the configuration details for our channel. We had defined the profiles for our channel within the configs.tx.yaml file, and we had created this channel.tx out of one of those profiles. That profile defined a channel which connected one orderer and one peer which belonged to a single organization. All of the artifacts for that channel are defined within this channel.tx file. So we pass this along as an argument. And when we execute this command, the peer channel create command has been executed within our peer Docker container. So the first channel for our Hyperledger Fabric network has now been initialized. There is still one more step which we need to perform before it can be used, however, where we need to explicitly get the peer node to join the channel. And for that, we once again run a command from the shell of our peer container. So we use docker exec once more, and we pass along the two environment variables. And then we specify the name of the container where the command needs to be run. And the specific command is peer channel join. The argument to this command is going to be the name of the Genesis block created for that channel. And this was provisioned when we ran the peer channel create command previously. The name of this Genesis block file is the name of the channel.block. So it's going to be my channel.block in our case. And when we execute this command, the peer node has successfully joined the channel which we have provisioned. So we now have a Hyperledger Fabric network along with a channel which we can use to invoke transactions. And in order to initiate those transactions, we will be making use of the CLI container. And this is one which we haven't yet brought up. And the definition of that CLI is within the Docker Compose YAML file. So we run one more Docker Compose up command. And then we specify that it is the CLI service which needs to be brought up. And once that service has been initialized, we can quickly confirm that the CLI container is up and running by doing a docker ps. And a CLI container is also available for us to use, in addition to the 4 other containers which make up our Fabric network. In the next video, we will connect to the CLI container, we will write up some chain code, and then deploy it to our Fabric network so that we can interact with it. Now that our Hyperledger Fabric network has been set up, it is now time for us to interact with it. And for that, we will be coding up a smart contract or chain code. We need to install it on the peer we have provisioned in the Fabric network. And then following that, we will invoke transactions from that chain code. All of those operations will be easy to perform if we make use of the Hyperledger Fabric CLI. And since that CLI has been set up within a Docker container, we will now log into the shell of that container. The way we do that is to run the docker compose exec command, followed by the name of the container we wish to connect to, and then we will run the bash command in order to bring up the bash shell in that container. So with that, we are now connected to the bash shell of our CLI container. You may notice that the directory we are currently in is the working directory we had defined for this container in the docker compose YAML file. For our contract interactions though, we will be switching over to another directory. So I'm now going to cd into /opt/gopath/source/github.com. And then from there, the first thing we will do is to set up a text editor which we can use in order to code up a smart contract. The editor which I will be using is the Vim editor, which is why I'm going to run apt-get install Vim. You could, of course, set up some other text editor which you're more comfortable with, but I'm just going to go ahead with this installation. And once this text editor has been installed, we can create a new workspace directory for our smart contract. Since this smart contract effectively serves as an inventory of fruits, I'm going to call this project directory fruits and then cd into that. And then from there, we'll create another directory called go. After seeding into that directory, we can begin coding up our contract file. And this chain code will be developed in the Golang programming language. So we call this fruits.go. So note here that even if you're not familiar with the Golang language, you can still follow along. As long as you have some object-oriented programming experience, it should not be too hard to follow. And I will try my best to explain some of the quirks of the Golang language. What we will be implementing is effectively a store of key and value pairs, and this can be used to represent an inventory of fruits. We will be storing those key and value pairs within the contract state. We will implement two functions, get and set. The get function will accept a fruit name as an argument and will return the corresponding value from the contract state. And the set method will accept a key and value pair, that is a fruit and the quantity, and then add it to the inventory. So once the empty file is up, I'll go ahead and paste the source. And then following that, we'll explain the blocks one by one. Starting with the package definition. So we define that this particular source file will belong to a package called main, and then follow that up with a collection of import statements. Note that all of the packages which we import are defined within parentheses, and there are three different packages here. The first of these is the format or FMT package, and this will be used in order to format the output from our chain code. And the second thing we import is the chain code shim library, and this includes all of the APIs which we will need in order to access the state variables for our smart contract. And finally, the peer library will be used in order to capture the output coming in from the peers when we submit transactions to them. Which takes us along to the definition of a new type. This is called fruits and it's of type struct. You will notice that this has an empty body, and this is because we will be storing the details for various fruits in the state variables for this contract. We will then be defining functions which will interact with those state variables, and we will be attaching it to this fruit struct by means of something known as a receiver. Unlike object-oriented programming languages which have classes with functions defined within them, we cannot have functions which are directly defined as members of structs. However, as a workaround, we will be using this notion of receivers. An example of such a function is going to be the next one, and this is the init function for our contract. Any chain code which is defined using Golang for Hyperledger Fabric must have the init and invoke functions defined within them. The init function effectively serves as a constructor, and you'll notice that we begin the function definition with the keyword func, and then following that, we specify within parentheses a pointer to a fruits struct. This is what effectively serves as the receiver and attaches this init function to the fruit struct. The argument to init is a stub, which is of type shim.chaincodestub interface, and this will be used to interact with the state variables. And then what is returned by this init function is a response from the peer, and this is represented as peer.response, and this will include something like whether the operation was a success or not. Within the function definition, we start off by using the stub variable in order to get all of the arguments which are passed to the function. So we call stub.getStringArgs to get the arguments, and we capture this in an array called args. We then ensure that this args array has exactly two elements. That is, there are two arguments which have been passed in to this function, and these arguments are a key and a value. The key will be the name of a fruit, and the value will be the count of that fruit in the inventory. So when we initialize this chain code, we will need to pass in the name of one fruit and its corresponding quantity in order to set up this contract. Once we ensure that the correct number of arguments have been passed, we will store that data within the state variable. We do that by calling stub.putState, and the arguments to this are the key and the corresponding value. That is the name of the fruit, which is going to be the first argument, and the quantity of that fruit, which is cast as an array of bytes. We capture the return value of this put state invocation in the variable air, and then we ensure that this is in fact null. If the put state function returned anything other than null, then we print out the message, fail to create asset, and note the use of the format library here. On the other hand, if the operation was a success, we return shim.success with an argument of nil. Nil in the Go language represents a null value. We have now defined one of the two interfaces which we need for this chain code, and in the next video we will define the invoke interface. We then move on to the definition of the invoke function, and this once again has a receiver in order to attach it to the fruit struct. Just like with the init function, the argument to this is of type shim.chaincode stub interface, and then it returns a peer.response. One thing about the invoke operation though is that it in fact represents an umbrella of functions. And in order to get the function which has been invoked along with its argument, we make a call to stub.getFunction and parameters. The returned values are the name of the function being triggered, which is captured in the variable fn, and also the array of arguments for that function, which is captured in the array args. To capture the result of the function invocation, we initialize a variable called result, which is of type string. And then to check if there are any errors with the invocation, we create another variable called err, which is of type error. Following that, we check the name of the function which has been passed into this invoke operation. And if the name of the function is set, then we will invoke a function called set, which we will define a little later in the source file, whose arguments are the chain code stub interface as well as the arguments to the function. The values returned by the set function are captured in the variables result and err. And if there is any other function invocation, then we call the get function, which again we will define a little later in the source file. And once again, the arguments are stub and args, and the return values are captured in result and err. Note here that we effectively only have two types of operations which we have defined here, a call to the set function and any other call which will effectively result in a call to the get function. So if either of these operations were to return an error, then we return shim.error along with the details of the error which has been thrown. On the other hand, if no error is thrown, then we return shim.success along with the result which is returned, which has been cast as bytes. So within this invoke function definition, we have made calls to functions set and get. We can now define each of these functions, starting with the set function. The arguments to this one are the shim.chaincode stub interface, as well as an array of strings which represent the arguments to the function. And then what is returned are two values. The first of these is a string which represents the result of the operation, while the second returned value is the error code. We start off this function definition by checking that there are indeed two arguments which have been passed in. Since the set function will be used to add one more fruit to the inventory, this includes the name of the fruit as well as its corresponding quantity, we need to ensure that there are exactly two values which have been passed as arguments to the function, the key and the corresponding value. And if not, we throw an error. Note here that the return statement includes two variables, the first of these being an empty string, and the second one being of type error, which includes an error message, and the string and error types match what we defined in the signature of the function. If the number of arguments was indeed exactly 2, then we move along to the next line, where we'll invoke stub.putState, where once again, we add the key and value pair to the contract state. So we check that this does not return an error, and then if so, we return an empty string and an error type just as we did previously. And if this put state operation was a success, then what we return is the quantity of fruit which was added, and also a null value to represent the error, which takes us along now to the get function. And this again has the same signature as the set function. And the argument to this will be a key, and what will be returned is the corresponding value which we will retrieve from the contract state. We first check that exactly one argument has been passed into this function, which is going to be the name of the fruit, which is the key. And then following that, we invoke a call to stub.getState in order to return the value corresponding to the key which was passed in as argument. So we capture the value returned in the variable value, and we also check whether an error was returned. If the getState call did return an error, then we return an empty string and also an error. On the other hand, if the value which was returned was nil, that is, there was no value corresponding to the key which was passed in, then we will return once again an empty string, and the error message which we return is asset not found. On the other hand, if there was a key in the contract state corresponding to what was entered, then we return the value in the form of a string. And along with that, we return nil for the error. So with all of our functions defined, it is now time for us to define a main function for the smart contract. And within this main function, we effectively initialize this chain code by calling shim.start. The argument to this needs to be something which implements the invoke and init interfaces, which is why we pass in a new instance of our fruit struct. If this chain code initialization throws an error, we will print out the message that there was an error starting the fruits chain code. And with that, we have now defined our first chain code for a Hyperledger Fabric network. And just to summarize what we have done so far, we have essentially implemented an inventory, something which is able to store a collection of key and value pairs, which we will be using to represent an inventory of fruits. We implemented an init method which serves effectively as a constructor for the chain code, and it needs to be initialized with a key and value pair which will start off the inventory. And then following that, we also defined an invoke method that effectively serves as an umbrella for the get and set functions in order to add a new key and value pair to the inventory and to return a value corresponding to the input key. And all of the key and value pairs will be stored within the contract state. We can now save this file, and then following that, in the next video, we will invoke each of the operations, firstly to install and initialize this chain code, and then to invoke the get and set methods. In the previous video, we connected to our CLI container, and then from there, we defined the chain code which we wish to deploy and then operate on our Hyperledger Fabric network. There are a few steps involved for that to happen, and that is exactly what we will be doing in this video. I'm now in the shell of my CLI container in the same directory as the one where the contract has been provisioned. Before the contract can be deployed, I'm going to set a few environment variables which are related to the contract itself. Firstly, there is the variable called cc_runtime_language, and this is going to be set to a value of Golang, and we will be using this to signify that the chain code has been written in the Go language. Next, we also set the path in which the source file for the contract can be found, and this is stored in the variable cc_source_path. And note that this is a relative path from the go path/source directory, and this represents a directory which contains our Golang source files. And then following that, we will create a deployment spec for the chain code by running the command pure chain code install. The arguments to this include the name for the chain code, which is specified after the -n flag, and this is called fruit counter app. We then set a version of 1.0 for the chain code. We specify the path in which the chain code can be found, and for this we reference the environment variable which we just set. And then following that, we set the language for the chain code, which is going to be Golang, and once again we reference the environment variable for that. And when we run this, we will have created a chain code deployment specification, and this message confirms that this was created successfully. Keep in mind that the installation of this chain code has occurred on peer 0 in our network, and this is because of the environment variable core peer address, which we had configured for the CLI container. If you have additional peers in your network and you wish to install the chain code on each of them, then you can modify that environment variable and then run the peer chain code install command once again. Now, in order to deploy this chain code and instantiate it in the blockchain network, we will need to run the command peer chain code instantiate. And this one will take a number of different arguments, starting with the orderer service endpoint. So the orderer is available in the container orderer.lunicorn.com at port 7050. We then specify the channel to which this chain code will be deployed, and this is going to be my channel, which connects the ordering service to the peer on org1. One thing to note is that while chain code is installed on a peer, it is instantiated in a channel. This is done in order to improve efficiency, since you can have the same chain code on multiple channels. We then specify the name of the chain code which needs to be deployed, and this was set previously when we installed the chain code to fruit counter app. Once again, we specify the language for the chain code, which is going to be Golang, and we reference the environment variable for that, the version of the chain code which needs to be instantiated, and then following that, we pass along the arguments to the constructor for the chain code. Remember that the init operation which we defined within the chain code required a single key and value pair, and we pass these along as a JSON structure. So this includes a single field called args, and then the corresponding value is the array of arguments which we pass in to the constructor. The first one being the key called mango, and the second one being the corresponding quantity of mangoes, which is 80. The next thing we do is to define the endorsement policy for this chain code. The endorsement policy must define those peers in the network whose endorsement is required for a transaction to be validated. Now, there are different ways in which we can specify an endorsement policy. In our case, we say that either of org1 msp.member or org2 msp.member can give their endorsement for the transaction to be deemed valid. And we do that by listing each of these members within parentheses following the org keyword. Now you will recognize that there is no org2 MSP in our network. So all of the transactions which we invoke from this chain code will need the endorsement of org1 MSP. I have included this policy here just to indicate to you how exactly you can set the endorsement policy. So we now run this command, and our chain code is now being installed. And if we return to the shell with no error message, it means that our chain code or smart contract is now ready to be interacted with. So our fruits inventory has been initialized with 80 mangoes, and we will now go ahead and invoke one of the chain code operations. Specifically, we will make a call to the get method, and since this is an operation which does not invoke a transaction, we can run the command peer chain code query. The arguments to this include the channel on which this query will be executed, and this is going to be my channel, the name of the chain code to invoke, and this is going to be fruit counter app, and then following the -c flag, the lowercase c that is, we will pass along the name of the function to execute, followed by the arguments to the function. Just as we did when we passed along the arguments to the constructor in the peer chain code instantiate command, we pass in a JSON string where we have a single field called args, and the args include, firstly, the name of the function to invoke, and then we follow that up with the arguments to that function. So here we wish to invoke the get function, and the argument we pass to it is mango, and we expect that executing this will return to us the quantity of mangoes in our inventory. And yes, this does indeed return the value of 80, which is exactly what we expect. So we have now successfully invoked the get function defined within our chain code. Now, in order to call the set function, we will need to run a slightly different command, and this is because the set function will trigger a transaction since it changes the state of the contract. And the command to run from the command line for it is pure chain code invoke. Since this is a transaction, the arguments which we pass along include the location of the ordering service, which is orderer.lunicorn.com, port 7050. We then need to specify the channel in which this operation will be invoked, which is my channel, the name of the chain code to trigger, which is fruit counter app, and then finally, the arguments for the function call. So once again, we pass in a JSON structure, and then the arguments start with the name of the function to invoke, which is the set function, followed by its arguments. So this includes a key of apple and a value of 20. So we're adding 20 apples to our fruit inventory. So when we execute this, we don't get any errors. And in fact, the message says that the chain code invoke was successful. So that is clearly a good sign. But just to confirm that this operation did indeed work correctly, we once again run another pure chain code query operation. So this call is similar to the query call previously, except this time we wish to get the quantity corresponding to the key apple. So we make a call to the get function, and this returns a value of 20, which confirms that both our get and set methods work exactly as we expect them to. So we have now successfully deployed our first smart contract or chain code to a Hyperledger Fabric network and have interacted with that chain code. We have used the commands pure chain code install and then pure chain code instantiate in order to set up our contract. And then following that, we made use of the commands pure chain code query and then pure chain code invoke as well. You can continue playing with this chain code by perhaps adding more fruits to the inventory and then reading from it. Once you're done though, you can exit from this Docker container for the CLI by running exit from the command line, and this will take you back to the shell on your own local machine. Now that you know how to develop smart contracts for Hyperledger Fabrics using Golang, you can stick around in this learning path where we will cover how we can develop smart contracts in Node.js as well. In this exercise, you will start off by describing services in Docker. Each of the components in our Hyperledger Fabric network, which included the orderer, the certificate authority, a peer node, as well as a CouchDB instance which functions as a state database, were implemented as Docker services. And these definitions were included in the docker compose.yaml file. You will need to recall what exactly a service represents in Docker and the details which can be configured within the definition of a service. Next, you will recall the interfaces and the different steps involved in accessing the state of a smart contract from within your chain code. In this course, the smart contract or chain code which we implemented was meant to serve as an asset inventory. And we covered how we can add assets to that inventory and then later read from it in order to get the quantities of each asset. You will recollect the interfaces and the functions which were used in order to perform these tasks. And finally, you will list down the different steps involved in order to deploy chain code onto a channel. Once the smart contract has been coded up, in order for us to deploy to the Fabric network and then interact with it, there is in fact a two-step process involved, and you will need to identify what those two steps are and what each of them performs. All of these topics were covered during this course, so please pause this video and then take some time to perform each of these tasks on your own. For the first task in the exercise, you needed to describe what a Docker service is. A service in the context of Docker is meant to create containers built from the same image. Any large application will typically be made up of a number of different components, and the definition of each of these components can be recorded within a Docker image. And you can have multiple instances of those components running in your application if you implement them as a service. And the reason to have multiple containers or multiple instances of your components is to allow you to scale your application. For example, if your application happens to have a search service which is heavily used, then you can create multiple instances of the search service in order to cater to all of the requests which come to it. This is far more efficient than scaling your entire application, which may have several components which are lightly used and some which are more heavily used. And it is this Docker service which allows this efficient scaling. Within a Docker service, there are many different configuration options for the group of containers which fall within that service. This includes port mappings, where you can map ports on the host port over to a container port, and it is also possible for you to mount volumes from the host to the container so that files on the host file system can be available to the individual containers and can potentially be shared by them. Within a service definition, you can also define the environment variables for all of the containers which fall within that service, as well as the initialization commands in order to set up the containers. In our course, our initialization commands typically started up the service which was installed on those containers. And finally, if your service happens to be dependent on other services, then you can also specify that within its definition. Docker will then ensure that it is the dependencies which are provisioned first. There are several other configurations which are possible within services, but these are just some of the important ones. Moving along now to the next task in the exercise, where you needed to recall the different steps involved in accessing the state of a smart contract from within your chain code using interfaces and functions. Well, the way to do this, as we saw during the labs, was to make use of the chain code stub interface. This is an interface available in the chain code/shim package. And once we have imported that into our code, we can effectively treat the state of the smart contract as a collection of key and value pairs. So using our chain code stub interface, we can retrieve a particular value corresponding to a key by making use of its getState method. The argument to this is the key, and then this should return to you the corresponding value if the key does exist within the state. And then if you would like to add a new key value pair into the state, then you can use the stub interface's putState method, and the arguments to this are the key as well as the value which need to be added to the state. And finally, you needed to list down the different steps involved in deploying your chain code over to a Hyperledger Fabric channel. As touched upon earlier, this is in fact a two-step operation once the coding of the smart contract is done. So the first step is to perform an install of your chain code, and this is an operation which is performed on each individual peer, which needs to be able to execute and endorse transactions invoked from the chain code. The command used to perform this chain code installation is peer chain code install. During this course, we executed this command from the CLI Docker container, where we ensured that the core peer environment variables were pointing to the peer on which we needed to install the chain code. When running this command, you will identify the chain code which needs to be installed using a combination of the name of the chain code as well as its version. And as already mentioned, any peer which wishes to not only execute the transactions but also submit them needs to have the chain code installed. So the chain code install step is something which happens at a peer level, but the next step in order to deploy the chain code is to perform an instantiation, and this is something which happens at the level of a channel. So while you may need to run multiple peer chain code install commands in order to install the chain code on multiple peers, the chain code instantiation can happen just once, and this is done using a command peer chain code instantiate. Executing this command will call the init method defined within your chain code, which effectively serves as its constructor. With the combination of these two commands, your chain code will be deployed to your Fabric channel, and then you can use it in order to invoke transactions and query from your chain code. Previously in this learning path, we provisioned a Hyperledger Fabric network by means of Docker containers which we had running on our local machine. We then wrote a smart contract or chain code in the Golang language. And then once we deployed it to the network, we were able to invoke operations on that contract. We will now take a look at how we can develop smart contracts using Node.js. And to do that, we will be reusing a lot of the material which we had created previously. I'm now in the shell of my local machine, and then within the directory called Hyperledger, which I created within my home directory. Within this, I'm going to create a new subdirectory called car store. And to do that, I'll essentially be copying over all of the materials which we used previously for our Hyperledger Fabric network, which is present in the fruit counter directory. To ensure the entire contents of that directory, including the subdirectories, are copied over, I run the command cp-r. And once that is done, we can do an ls just to confirm that this car store directory has been created. When we navigate into that, we once again run an ls just to confirm the contents. And this includes a bin directory, which includes all of the binaries which we used previously, and then all of the artifacts which we generated from that, including the config.tx.yaml file, the crypto-config YAML file, the connection.json, and so on. So we will be using all of this material in order to provision another Hyperledger Fabric network in which we will deploy another smart contract, and this time it will be to store an inventory of cars. This contract will have additional features when compared to the previous one we built for an inventory of fruits, and this will also be coded in Node.js. And then following that, we will also be building a front end in order to interact with that contract. So now that we have all of the material, I'll clear the terminal window and then clear up all of the Docker containers which happen to be running right now as well. For that, I'll run the command docker compose down so that all of the containers or services which we have specified within the docker compose YAML file will be brought down. This will give us a clean slate to work with, which will make it easier for us to deploy our new contract. So once you execute this, all of the services will be stopped, and then the containers will also be deleted. And then the network on which those containers were running will also be removed. And now that we have toned down the old network, it is time to build up the new one. So we once again use the same docker compose YAML file, and we run docker compose up. And like we did before, we bring up 4 of the services defined within the YAML file. This includes the certificate authority, the orderer, the peer, and the couchDB. So once we do that, we see that the 4 services are now up, and we can confirm that the containers are indeed running by running docker ps. So yes, the 4 containers are now up and running. Now that the components for our Fabric network are up, it is time to provision the channels. And before that, we will set the environment variables we need for it, starting with the MSP ID, which we will use for the channel, and then the MSP config path as well. Again, this is similar to what we had done previously. And once that is done, we will need to execute the peer channel create command. And in order to run it from the peer container, we need to make use of the docker exec command. As we did before, we pass along the 2 environment variables which we created to the exec command, and then we specify the orderer, the name of the channel, as well as the channel artifacts file, which includes the details for the transaction which needs to be executed on the Fabric network to provision the channel. So when we execute that, a new channel called myChannel has been provisioned, and you'll remember that the channel.tx file contains the details to provision a channel, which includes a single orderer and a single organization which has 1 peer within it. So the peer channel create command will have created a new Genesis block for the channel. And now in order to join a node to the channel, we will need to make use of the Genesis block. And we do that by running the peer channel join command once again from the peer container. And then the argument which we pass to this is the Genesis block, which was provisioned earlier. And the name of this Genesis block file is mychannel.block. If you created your channel with a different name, then the name of the Genesis block file will also be different and will correspond to the name you set for the channel. And once that is done, The channel for our Hyperledger Fabric network is now ready. We can now use that channel to deploy smart contracts and then interact with them as well. To do that, we will once again make use of the CLI for Hyperledger Fabric. And for that, we will need to bring up the CLI container defined within the Docker Compose YAML file. So we run Docker Compose up once more, but this time we only bring up the CLI container in detached mode. So with the CLI service up, we will connect to the shell of that container by running Docker Compose exec, followed by the name of the container, which is CLI. And then in order to bring up the bash shell, we run the command bash. So with that, we are now connected to the bash shell of our container, and we have been connected to the working directory which we defined for the CLI. It is now time for us to cd into a different directory. So I'm now going to cd into the /opt/gopath/source/github.com directory. We can just examine the contents of this directory by running ls, and this shows us that there is a single directory called Hyperledger present here. It is in this directory where we will create a new project directory for our Node.js smart contract. We will do that, however, in the next video. Previously, we provisioned the Hyperledger Fabric network along with a channel, and it is now time for us to develop a Node.js smart contract and then deploy and interact with it in the network. We will be doing the development and the deployment of the contract from the CLI container which we have provisioned, and I'm currently in the directory /opt/gopath/source/github.com within that CLI container. We start off by creating a new project directory, and this is going to be called cars, and this will be an extension of one of the sample smart contracts supplied by Hyperledger Fabric, and that sample is called FabCar. We will be building upon it and then creating a user interface in order to interact with that contract. The contract will effectively serve as a repository of various cars. It will contain details of different vehicles, and we will be able to query the details of those vehicles by means of a car ID. So once we have created the project directory, we cd into it, and then from within the cars directory, we create another subdirectory, and this one is called JavaScript. So this is where we will store all of the JS files for our project. And then once we cd into that directory, before we begin creating the source files, we'll need to ensure that we have a text editor. So just as we did previously, we will install the Vim text editor. So I'm running apt-get install vim. And given that this could take a minute or two, I'm just going to fast forward through all of the installation steps. And once again, you can install and use any other text editor you're comfortable with. And once the text editor is ready, you can open up a new file, and then this is going to be called cars.js. So this will be the main source file for the contract. Just as before, I will paste the entire source code and then walk you through the code itself. We start off by saying that this code should be executed in strict mode, that is, we cannot have undeclared variables. We then import the libraries which we need. This includes the Fabric shim package, and this, just as with the Golang shim package, will be used in order to interact with the contract state. It also includes a few Fabric-specific functions. The util package is something which is used for Node.js and includes, as you would expect, a number of utility functions. We begin by defining a class called chaincode, and then within the class definition, just as with the previous smart contract in the learning path, we do need to implement the init and invoke interfaces. We start off with the definition of the init function, and you will recall that this effectively serves as the constructor of this contract. We define this to be an asynchronous function, and the argument is going to be a stub. Just as with the stub we used in the Golang contract, this stub will allow us to access details such as the arguments which are passed to the chaincode invocation or query. In the case of this contract, we don't really do much within the init function. We simply print out a message to the console and then return a success message by means of a call to shim.success. Moving along now to the invoke function. Once again, we define this to be asynchronous, and the argument to this is also a stub. Within this function, however, we use that stub variable in order to make a call to its get function and parameters function. This will return the name of the function being invoked as well as its list of parameters. These are captured in an object ret. Once we print out the contents of what has been returned, we then access the name of the function which has been invoked, and this is available in the field ret.fcn. We then check whether this smart contract includes a definition for the function being invoked by making use of the this global object. If the function has been defined, then that function will be captured in the variable method, and then we check whether this method variable is null. If it is, we print out a message to the console saying that the function cannot be found, and then throw an error. On the other hand, if the method has been defined, we then make a call to that method. Note that we make use of the await keyword before the method call, and this will ensure that the call to the function is completed before execution proceeds to the next line. The arguments to the method call include the stub as well as the arguments which were passed in for the function invocation. Those arguments are available in the field ret.params. So we capture the returned values from the function call in the variable payload, and if the call to the function is a success, then we return a shim.success message along with the returned payload. On the other hand, if an error has been thrown, then we catch the error, print it out to the console, and then return shim.error with the error message. So just as with the Golang contract, we are using the invoke method in order to make calls to other functions which are defined within our smart contract. And we start off the definition of those other functions with this definition of a function called query car. This function will take in as argument the ID of a car and will then return the details of that vehicle. So this takes in as argument a stub as well as the list of arguments to the function, and then immediately we check that the number of arguments which have been passed in is exactly 1, and this needs to be the ID of the car. If the number of arguments is not 1, we throw an error, and we also give an example of the type of ID we expect. If we get exactly 1 argument for the function, then we proceed with the code execution and then capture the car ID in the variable car number. And then following that, we use that car number variable in order to retrieve the details of the corresponding car from the contract state. Here, we need to make a call to stub.getState, whose argument is the car number, and we make use of the await keyword here so that the function call will complete before the code execution proceeds on to the next line. The value which is returned will be captured in the variable car as bytes, and this will be a JSON structure in the form of bytes. We then ensure that this car as bytes which is returned is neither null nor a blank string, and if it is, we throw an error saying that this particular car does not exist in the state. That is, we have no record for that particular car. On the other hand, if the car is found, then we will print it out to the console, and for this we run car as bytes.toString so that we stringify the JSON data, and then following that, we return this car as bytes over to the one invoking the function. So this concludes the first function definition within our smart contract, which allows us to query for the details of a particular car using its car ID. So we have defined the init and invoke methods as well as this query car function so far. All of the other functions for the smart contract we will define in the next video. In the previous video, we started off the definition of our Node.js smart contract in order to store details about various cars in the state of the contract. We finished the definition of the two functions which we need to implement within a smart contract, and those are the init and invoke methods. And then following that, we also wrote one function called query car, which will allow us to query for the details of a car using a car ID. Now, in order for this smart contract to be loaded with data, we will now define another function called initLedger. Now, this will load the details of 10 different cars, which we can query using the query car method. And later on, this will be the first function which we will invoke after the smart contract has been installed and instantiated. If you would like, you can include a call to this initLedger function within the init function which we defined previously. So the arguments to the initLedger function are the stub as well as a list of arguments, but we won't be referencing the arguments, and when we make the call to this function, we won't be passing any arguments either. Let us head into the definition. So we initialize an empty array called cars, and then we go on to push the details of various cars into this array. You will notice that the details for each car are in the form of a JSON data structure, which includes 4 different fields: the make of the vehicle, the model, the color, and the name of the owner of that vehicle. So the first car which we add into the array is a blue Toyota Prius, which is owned by Tomoko. And then we make use of the array's push method in order to add the details of that car. We then go on to add details for a Ford Mustang. Our database also includes a green Hyundai Tucson, as well as a yellow Volkswagen Passat. So clearly, this is a rather international list of vehicles. Now you can go ahead and add your own list of vehicles as well, and it need not be the same number of vehicles as I'm using right now. But in my case, I'm going to proceed with the addition of a Tesla, a Peugeot, and a few other cars, which also includes a Fiat as well as a Tata. And following the addition of this Holden Barina, I now have a list of 10 vehicles which can be loaded into our array. And then once the array has all of the details for the vehicles, we need to store each of those cars within the contract state. So we iterate through the members of the array, and then following that, we will add each vehicle into the contract state using the stub.putState method. Note how we are effectively generating a car ID, which starts with the text car, followed by a number which represents an index of that car in the array. So that car ID represents the key which we store in the state, and the corresponding value is in the form of a JSON string which holds all of the details of that car. And then following that, we print out to the console that the car has been added to our state. And at the end, we say that the ledger has been initialized. So this concludes the definition of our initLedger function, which gives us a few cars to work with. And now we proceed to the definition of some of the other functions, including one to add a new car to the state. So this is a function called createCar, and this accepts 5 different arguments. The first of these is a car ID, which must explicitly be specified. And then following that, we expect the various details for the car, which include the make, model, color, and owner, which we saw previously. So if this createCar method has been invoked with the correct number of arguments, we proceed to create a new JSON data structure called car, which is loaded with the data which was passed along as arguments, and we also set a doc type field to car. Once this JSON data structure has been set up, we can then go ahead and add it to the contract state by invoking stub.putState once more. The key in this case is the first argument which was passed in, which represents the car ID, and the value is going to be the details of the car in the form of a JSON string. We once again attach the await keyword so that the function execution will complete before the code execution proceeds onto the next step, where we simply print out to the console that the car has been created. We then move on to the next function definition, and this is one which will return all of the cars which we have in our database. So even though the arguments to this include a stub as well as a list of args, no arguments need to be passed to this. That is because it will simply return all of the cars within the contract state, or rather, to be a little more precise, it will return all of the cars from 0 until car 999. This is what we define as the start key and the end key for a query against this contract database. And then we use those values in the function call to stub.getStateByRange. So this will return all of the values within the contract state which fit within the range specified. That is from car 0 until car 999. And then all of these values will be captured in the variable iterator. Later on, we initialize an empty array called allResults, which will be loaded with the results of this query execution. And to perform this loading, we will iterate through each of the cars which have been captured in the iterator variable. So we set up a while loop, and then we start off by loading a variable called res to represent a response with the next car in the iterator. And then following that, we will check the value of the response and ensure that it is not null. And we also ensure that res.value.value is not null. We then initialize a JSON data structure called JSON response or JSON res. We also print out the value of the car which is returned to the console. And then following that, we begin to format the JSON response data. So we set the key for this to res.value.key, which is going to represent the car ID which is returned. And then after that, we set the JSON responsive record field to the value of the car itself. This will include the make, model, color, and owner of the car, which we can obtain from res.value.value.toString. We apply json.parse on this value returned, and if this json.parse is a successful operation, then we push the JSON res object into our allResults array. And if not, and an error is thrown, then we print out that error to the console. If the vehicle we are iterating over happens to be the last one in the return results, then the res.done field will be true. And in this case, we print out to the console that this is the end of the data. We then close down the iterator, print out all of the results captured in the allResults array. So this will include all of the data for all of the cars. And then we exit from this function call by means of the return statement, which will also break out of the while loop. And what we return is a string version of the allResults array. And with that done, the query allCars function has also been defined. In the next video, we will wrap up the definition of this smart contract and then go ahead and install it, instantiate it, and then invoke one of the operations on the contract. That will happen though in the next video. In the previous videos, we defined a number of different functions within our smart contract, which is storing details of various cars. We implemented the init and invoke methods, and then following that, we included methods in order to add a new car to our database, another function to initialize the database with 10 different cars, and then we also created a function called query all cars, which will return all of the cars which are stored within that database. We now implement another function, and this is called change car owner. As the name implies, this will allow us to edit the information about the car, specifically the owner field, and then change its ownership. So the arguments to this function, once again, are a stub and a list of arguments. And once we print out to the console that we have initiated this change car owner function, we once again check that exactly 2 arguments have been passed along to this function. This needs to include the car ID whose details are being modified, as well as the new owner which needs to be set for that car. Following the argument check, we then retrieve the details for the corresponding car by a call to stub.getState, and we use the first argument which is supplied, which should be the car ID for that. This will return to us the details of the car in the form of bytes. We then transform that to a JSON data structure by means of a call to json.parse. And then we edit the owner field of that JSON object and then update it to the new value supplied in the form of the second argument. With that done, we can now make a call to stub.putState, where we overwrite the existing entry in the database for the car. So we add in the key, which is the car ID, and the corresponding value is the stringified version of our JSON data structure representing the car details. And then once we print out that the car ownership has changed, our change car owner function has been implemented. With this done, all of the functions which we need for our car database have been defined. So we can close out all of the function definitions as well as the class. And the one thing we need to do now is to create a new instance of our chain code class by means of shim.start. So the argument to this is the new instance of the chain code, and this will implicitly make a call to the init method within our chain code. And with that done, our contract definition is complete. So I'm just going to save down the source file, and with cars.js now ready, we need to edit one more file before we can deploy the contract, and this is going to be the package.json file for this project. Here we need to include a lot of the data for the project, including its dependencies. So I'm now going to bring it up in the Vim text editor. And then within this, I'm going to paste the contents of the package.json file and then walk you through each of the sections. So here we have some details for our project. We give it a name, a version, and a description. And then following that, we specify which versions of Node and NPM can be used. So we set the Node versions to be greater than or equal to 8.4.0, and the NPM version to install this will be greater than or equal to 5.3.0. And when someone runs npm start from the project root directory, the command we will be executing is node cars.js. In order to enforce the engine versions which we have set, we set the engine strict flag to true. We also specify that this package is covered by the Apache 2.0 license. And then we include the dependencies for our project. Specifically, this uses fabric-shim and versions 1.4.0 of that package. So with that, we can go ahead and save this package.json. And now with the definition of our cars.js file, as well as the package.json for that project, our smart contract definition is now complete. We can now go ahead and install the smart contract, instantiate it, and then invoke operations on the contract. Now that we have finished coding up our smart contract, and we have also specified the package.json file for our Node.js project, it is time for us to deploy the chain code to the Hyperledger Fabric network. To do that, I'm first going to clear out this terminal window, and then I will initialize the environment variables which will be needed in order to deploy the chain code. The first variable I will set is cc_runtime_language to represent the chain code language, and this is going to be Node. Next, I'm going to set the path in which the source file for this chain code will be available, and this is the directory in our CLI container where we created that source file. And now that we have the two environment variables, we set one more, and this is going to be the MSP ID for the only organization in our network. This is org1 MSP. And there is one final environment variable which we need to set, and this is the MSP config path. And this represents a location within the peer node of our Hyperledger Fabric network. So this is going to be in the peer in org1. And with our environment set up, it is now time for us to deploy the smart contract. To do that, we run the peer chain code install command from the CLI container by means of this docker exec command. We pass along the environment variables which we have configured over to that CLI container. And then once we call the chain code install command, we pass along the arguments to that. This includes the name of the contract. So this is going to be car store. We set it a version of 1.0. We specify the path in which the source files can be obtained, and this is the path within the CLI container. And then we set the language for this chain code to Node. So running this command will initiate a deployment of this smart contract. And in order to initialize the smart contract in our network, we will need to execute the pure chain code instantiate command from the CLI container, and once again by means of the docker exec command. We pass in the MSP ID and the MSP config path over to the CLI container, and then we invoke the chain code instantiate command with a few arguments. This includes the location of the ordering service, which is at orderer.lunicorn.com at port 7050. Then we specify the name of the channel to which this deployment must take place, which is my channel. We set the name of the smart contract to be deployed, which is car store. The language of the smart contract must also be set here. And for that, we reference the environment variable, which we just set. The version of the smart contract is given here as well, which is 1.0. And then following that, after the -c flag, we can specify the arguments to be passed along to the constructor of our smart contract. You will recall that the init method which we defined did not perform any task and it only had a console.log statement. So we leave the args field here to be a blank array. We also set the same endorsement policy as we did previously, where an approval is required from either org1.msp or org2.msp for a transaction to be validated. And since there is no org2.msp yet, effectively we will need the endorsement from org1.msp. And with that, we execute this pure chain code instantiate function. And once it runs without any errors, it means that our smart contract has been installed to this Hyperledger Fabric network. It is now time for us to invoke an operation in order to load the smart contract state with a few cars. That is, we are initializing our cars database. And to do that, we need to make a call to the init ledger method, which we defined within our smart contract. We do that by means of a call to pure chain code invoke. And once again, we will be invoking this through the CLI container and once again through the docker exec command. So when we make this call to pure chain code invoke, we will effectively be making a call to the invoke function which we defined within our smart contract. A pure chain code invoke call from the CLI will need to know which ordering service to use, as well as the channel to which this call is being made. We also need to know the smart contract which is being triggered. And then following that, we pass along the details such as the function which is being triggered, as well as the arguments to that function. So here we make a call to the init ledger method, and then there are no arguments which need to be passed to that function. So the value of the args field is simply a blank array. So when we run this, we will be loading our ledger with 10 different cars. And I can see here that this call was successful. And at this point, feel free to invoke each of the functions which you defined, such as query all cars and create car and so on. You will need to make use of the pure chain code invoke command for that once more. And the use of this command will be similar to what we did for the previous smart contract where we had a fruit inventory. Since we have already seen a few examples of this pure chain code invoke operation, we won't be getting into the details of that. But in the case of our car store contract, we will take a look at a more practical use case for smart contracts on the Hyperledger Fabric network by building a user interface which will be able to interact with the deployed smart contract. That will be the focus of the subsequent videos in this learning path. In this exercise, you will start off by describing the required components in a Node.js smart contract written for Hyperledger Fabric. In this course, we did create a smart contract written in Node.js in order to implement an inventory of automobiles, and this included a number of different components and functions. You will, however, recollect exactly which of those are required in order for your code to function as a valid contract. The next and final task is to recall the different steps involved in deploying and then interacting with chain code using pure commands executed from your shell. The pure binary does include many different commands which you can use to work with and deploy channels as well as smart contracts. You will need to focus on the smart contract portion of it and recall the exact commands which we used during this course. Both of these tasks were covered during the labs of this course, so please pause this video and then take some time to perform these tasks on your own. For the first task, you needed to recall the different components which are involved within a Node.js smart contract for Hyperledger Fabric. Within our contract source file, we started off by importing the Fabric shim package. This is the crucial package for us because this includes a number of different interfaces in order to work with the smart contract. For example, we use this package in order to access both the contract state as well as transaction data. So while Fabric shim is a package which we need to import and then use, there are a couple of functions which we will need to implement within any contract. One of these is the init function. So this effectively serves as the constructor for the contract. Like with any constructor, this function is capable of accepting arguments, and it is called when the chain code is instantiated. The chain code instantiation is one of the steps involved when we deploy a smart contract to a channel. We move on now to another function which needs to be implemented within a smart contract, and this is the invoke function. The purpose of this function is not to perform a very specific task, but to effectively serve as an umbrella for multiple contract operations. So whenever someone wishes to invoke a query or a transaction using chain code, then they're effectively making a call to the invoke function, and the input to this function includes the name of the function to invoke as well as its arguments. So the different functions within your smart contract are not called directly, but through the invoke function. So while these are the functions which need to be implemented, within the rest of your contract, you can have all of the other functions. And those functions, again, cannot be called directly, but need to be called from within the invoke function. So all of this is a summary of what needs to be implemented within a smart contract coded in Node.js. We move along now to the next and final task in the exercise, which was to identify all of the different steps involved in deploying and then interacting with chain code. And this needed to be done using the shell using peer commands. The first step in deploying a smart contract is to perform an installation of the chain code. So this is an operation which is performed on each of the individual peers which need to be able to submit transactions and execute them. And the specific command which you need to execute for it is peer chain code install. The next step in deployment is to instantiate the chain code, and this is done at the level of a channel rather than a peer. And the specific peer command in order to perform this task is peer chain code instantiate. So at this point, your smart contract has been deployed to the Hyperledger Fabric channel, and you should be able to interact with it. But your interactions can fall into two different categories. The first of these is when you perform a query operation on your chain code. Querying is when your operation is a read-only one, and it does not modify the state of the contract or the blockchain. The specific command to execute when you are running a query operation is peer chain code query. And then, of course, there are operations which will modify the state of the contract or make additions to the ledger. And this is done by submitting new transactions. The specific command in order to invoke transactions is peer chain code invoke. So these four commands cover the different peer commands we use during the course in order to deploy and then interact with our chain code. We have previously deployed a smart contract to a Hyperledger Fabric network in order to represent a database of cars. That contract was coded in Node.js, and we will now be writing another application using Node in order to interact with that smart contract. This application can reside on an entirely different host than the one we have been using previously, and the ones which are running the Docker containers for our Hyperledger Fabric network. But it will need some of the files which we had made use of previously, including the connection.json file, which includes all of the details to connect to the different components of the Fabric network. For the sake of simplicity though, I will be creating this web application on the local host as well. This is the same host where I have the containers for the Fabric network running. I'll start off by spawning a new directory called JavaScript within the car store directory, which has been used previously in order to provision all of the config files and the cryptographic materials for a new Hyperledger Fabric network. So once this JavaScript directory has been created, I'll go ahead and cd into it. And since this is a Node.js project, we will install some of the dependencies which we will require. This includes the Fabric CA client so that we can provision some new identities for the network, which our application will use. And then we also include the Fabric network package. This will include the different APIs which we need in order to interact with the Fabric network. So I'm going to make sure that these are all installed locally for this project. And this installation can take a couple of minutes, so I'm just going to fast forward. And once the installation is complete, we're ready to go ahead and begin coding up our app, which will connect to our Fabric network and will also be able to interact with our deployed smart contract. To view the effects of our npm install command execution, I'm now going to bring up this directory within the text editor, and then this new JavaScript directory which has been created can be expanded. And then within that, there are two files, specifically one directory and one package.log.json file. And the node modules will, of course, include the two modules which we downloaded along with all of their dependencies. And then we can take a look at this package.log.json file. While in a package.json file, you can see those packages on which your app depends directly. Within the package.log.json file, you can see the entire dependency tree. When we examine the contents, we will see a whole host of minor packages which you normally wouldn't see within a package.json file. So there's no point in going through each of these in detail, so I'll just skip through all of them. And we can now begin coding up the first source file for this project. So I'm now going to create a new file within this JavaScript directory. And this is a source file which will enroll an administrative user for the Hyperledger Fabric network. The eventual goal is to have a new user to represent our application for the network. And in order to provision that application user, we will first need to create an administrator who in turn can create an application user. So let us begin coding this source file. We start off with a useString directive so that all variables need to be declared before being used. And then we import all of the libraries which we will require. The first of these is the Fabric CA client, which we just installed. This will be referenced as Fabric CA services. And this is what we will be using in order to enroll the administrative user in our network. We will be doing that by issuing an identity for the admin user. Then from the Fabric network package, we import the file system wallet, which allows us to maintain a wallet of identities on our own file system. We can then use one of those identities in order to interact with the Fabric network. The X509 wallet mixin will allow us to create identities which fit the X509 standard. That is, it will issue an X509 certificate along with the corresponding private key. We also import the file system or FS and path packages. Then, in order to connect to the Hyperledger Fabric network, we will create a variable called ccpath, which will effectively connect to the connection.json file which we have defined previously. This file, you'll remember, includes the details which we require to connect to the different components of our Fabric network, including the orderer, the peer, and the certificate authority. In these three lines, we connect to the file and then load its contents into a JSON object called ccp. And then we begin the definition of the main function for this source file. So this is going to be an asynchronous function. And then within that, we begin with a try block. The first thing we do within that is to make use of the ccp JSON object. to retrieve the URL of our certificate authority node. So this is captured in the variable CA_URL. And then we create an instance of the certificate authority by making use of the Fabric CA services object. We can use the CA object in order to function as a certificate authority and, for example, create identities. In these 3 lines, we initialize a wallet on our file system in which we will be storing the identities we will use to connect to our Hyperledger Fabric network. So we create a new directory for the wallet, and this is going to be a directory named wallet within our current directory. And then from there, we will initialize an instance of the wallet, or rather an instance of a file system wallet. This is an object in the Fabric network package, which allows us to use a wallet or one of the identities in the wallet to connect to the Fabric network. Next, we check whether an admin user, that is a user called admin, exists within the wallet. Since the purpose of the source file is to create an admin user, if that user already exists, we don't need to create another admin user, and we can simply return from this function. So if the user exists, we print it out to the console that an identity has already been created for admin, and then we return. On the other hand, if there is no admin user, we proceed with the code execution, and we go ahead and enroll the administrative user. To do that, we call the function ca.enroll, and the argument to this is going to be a JSON structure, which includes an enrollment ID and an enrollment secret. In our case, these are admin and admin PW respectively. Next, we create a new instance of an identity for the wallet, and this is done with a call to x509 wallet mixin.createIdentity. The arguments to this include the MSP ID of the MSP to which this identity belongs, followed by the certificate for that identity, followed by the private key of that identity. Both the certificate and the private key are available within the enrollment object, which was returned with the call to ca.enroll. And I apologize that you cannot see all of the arguments which we pass into this createIdentity function. But at the bottom of the screen, you can see the entire list of arguments, including the fact that the private key is accessed as enrollment.key.2bytes. Once the identity has been created, we import it into our file system wallet by means of a call to wallet.import. If there is any error thrown during this code execution, we will catch that error and then print it out to the console, and will also exit from the code. And with that, we also end the definition of our main function in order to enroll an admin user. And at the end, to ensure that the main function is called when this code is triggered, we specify this call to the main function. And with that, we can go ahead and save this file, which I'm now going to call enrolladmin.js. And with this done, the next step for us is to create another source file in order to register an application user. We will do that in the next video. In the previous video, we wrote down some source code in order to provision an admin user within org1 of our Hyperledger Fabric network. Now that we have written this code, we can now run this in order to create that admin user. So to do that, I'm now going to head over to my shell. And then from here, we'll simply run node enrolladmin.js. Of course, do make sure that you're in the same directory as the source file for this. And the output confirms that this identity has been created and has also been added to our file system wallet. To confirm this, I'm going to bring back my text editor up, and then this new wallet directory has been created here. And when that is expanded, I see a new subdirectory called admin to represent the admin user. And to see what has been created for this admin, we will need to expand this directory. And within that, there is at least one key file and one certificate. The file name, which has the long hexadecimal string, is the private key file, whereas the file called admin is the one containing the certificate. Now, having an admin user is all well and good, but our aim here is to have an application which interacts with the Hyperledger Fabric network and is able to invoke the chain code which we have deployed. And when that is the case, we need a separate identity for the application. To do that, we can use the admin credentials in order to create a new user. However, we will need to define a new source file in which to do this. So within this JavaScript directory, I'm going to create a brand new file, and I'll go ahead and paste the source code for this new user creation. We once again begin with the use strict directive, and then from the Fabric network package, we import the file system wallet, which we will be using to import the identity which we created earlier, and also to store the identity we will create within the source file. The gateway class will be used in order to connect to the Fabric network using the admin identity we created previously. And then once again, we will be making use of the X509 wallet mixin class in order to create the brand new identity for this application user. As we did before, we import the FS and path packages. And once again, to connect with the Hyperledger Fabric network, we will load the connection.json file into a JSON object. This is the object called CCP. We then go ahead with the main function definition. And within this, we will first initialize a wallet instance. So this is going to access the wallet directory which we created previously, and it should have access to the admin credential which we had provisioned. Following that, we check whether there already exists a user called user1 within the wallet. So the application user we will create will be called user1, and though I'm hardcoding this username over here, you can of course parameterize this if you wish. So you could have this source file accept an argument when it is executed from the command line, and the identity which is created will be based off that argument. I'm sticking with this hard-coded version over here though. So I first check whether a user called user1 already exists, and if so, we can simply return from this function. And if user1 does not exist, we will then check whether an admin user exists, because we will need to make use of the admin credentials in order to provision this new user. So if there is no admin user, we won't be able to create this user, and we can simply return from this function. But if the admin user does exist, the first thing we will do is to create a new instance of a gateway. As mentioned, this gateway can be used to connect to the Hyperledger Fabric network, and we do exactly that when we call the gateway instance's connect method. The arguments to this include the JSON object which we initialized with the contents of the connection.json file. That of course represents the connection profile. And then following that, we create another JSON object which includes our wallet instance. And then after that, we specify the identity within the wallet which needs to be used to connect to the Hyperledger Fabric network. So the identity we will use is the admin user, and we also disable the Fabric discovery service for this operation. Following that, we initialize an instance of the certificate authority, and for this we make use of the gateway object. So we call gateway.getClient.getCertificateAuthority, and we also create an instance of the admin identity with a call to gateway.getCurrentIdentity. Remember that the gateway has already been initialized with the admin credentials. The next thing to do is to enroll our application user, which is user1, to the Fabric network. We do that with a call to ca.register, and the arguments to this include a JSON object where we specify the affiliation of this user. So this user belongs to org1.department1. The enrollment ID of the user is also specified here, which is user1. The role for this user will be that of a client. So this user clearly does not have the same privileges as the admin. And then the next argument to the register function is the identity for the admin user, since we need those credentials in order to create a brand new user. The ca.register function will return a secret, which we will need to use in order to enroll this user to the Fabric network. So we next make a call to ca.enroll, and to this we pass along a JSON object which includes the enrollment ID for the user, which is user1, and the enrollment secret which was returned following the register call. This enrollment instance can be used to create a brand new identity, and for that we once again make a call to x509 wallet mixin.createIdentity. This identity is also for the org1 MSP, and the arguments to this include the certificate which was created with the call to ca.enroll, and also the private key which is available within the enrollment instance. So once again, we call enrollment.key.2bytes. Once this identity has been created, we will add it to the wallet by making a call to wallet.import, where user1 along with the user identity will be thrown into that wallet. So when we print out that this user has been successfully registered, we finish the execution of the function. But in case there were any errors thrown during the process, we will catch that error and then print it out to the console. And at the very end, we close out everything and then make a call to the main function. So with that done, our source code to register a new application user to the Fabric network has been concluded. So we can now go ahead and save this file, and I'm going to call this registeruser.js. And with that done, we can now execute this code in order to create the new application user. So heading back to the terminal, we can just run node registeruser.js. And the output confirms that the user has been created and added to the wallet. And to get the confirmation for that, we can bring back the text editor and then expand the wallet directory, within which a new user1 subdirectory is now present. So let us take a look at what the directory contains. So once again, there are two key files, and there is also a file called user1. And when we click on it, we see that this includes details for the user along with the certificate for that user as well. So we have now provisioned the application credentials, which we will need in order to interact with our deployed chain code on the Fabric network. So we can now close out these source files and then begin coding up our application, which we will begin in the next video. In the last couple of videos, we created two files. One of them was a source file to create a new admin user for our Fabric network. And then in the next source file, we made use of the admin user's credentials in order to provision an application user called user1. Now that a lot of the setup work has been done, we can actually begin coding up the application to interact with our deployed smart contract. That is, we will be making use of the user1 credentials to do that. Let us begin now. So within this JavaScript directory, we create a brand new source file. And the code in here will be used in order to make a call to the query all cars function defined within our contract. You will recall that this will return all of the cars which are available within the database stored within that contract state. So I'll go ahead and paste the code for this new source file. And once again, this uses the use strict directive. We import the file system wallet and gateway classes from the Fabric network package. And we also make use of the fs and path packages. Following that, we will load up the details in the connection.json file into a JSON object called CCP. So we will be using that to connect to our Fabric network. And after that, we begin the definition of the main function. Within the try block, we start off by creating a new wallet instance. And this, of course, now holds two sets of credentials, one for the admin and one for user1. And out of those two, we will first check that the user1 credential exists, because that is the one we will be using to connect to our Fabric network. If the user does not exist, then we need to return from this function, because we won't be able to connect to our network. However, if the user does exist, we can use that credential. But first, we need to initialize a gateway instance. Following that, we connect to the Fabric network by a call to gateway.connect. So the arguments to this include the connection profile, which is in the variable CCP, and then an object which includes our wallet. And then there is a field called identity, where we specify the identity within that wallet we wish to use for the transaction. So this is going to be the user1 identity. And then, just as we did previously, we turn off the discovery feature of Fabric. So now that we have the gateway instance which has connected to the network, we can use it in order to retrieve the channel which we defined earlier. So here we make a call to gateway.getNetwork, and the argument to this is the name of the channel we wish to connect to. Since our smart contract has been deployed to the channel called myChannel, that is the name of the channel I'm specifying here. And this is captured in a variable called network. Once we have this network instance, we can use it in order to retrieve an instance of the deployed smart contract. So a call to network.getContract needs to include an argument which is the name of the smart contract to retrieve. So here we specify the car store contract, and this will retrieve the latest version of that contract. And what do we do with that contract? Well, we need to make a call to the query all cars function, and we do that with a call to the contract's evaluate transaction method. And then the argument to this is the name of the function which we wish to invoke, which is query all cars. This should return to us all of the cars which are available within the database. And at this point, you'll recall that we have executed the init ledger method in the smart contract to load the database with 10 different cars. If you have added additional cars after that, all of those cars will be returned as well. So using the results which have been returned, we print out all of the cars to the console. And the call to our smart contract is as simple as that. In case there were any errors with this execution, we will catch it and then print out the error message to the console. But after that, we can simply close out the function definition and then end this source file with a call to the main method. So we can now go ahead and save the source file. So this is going to be called query.js. And now to test out whether this source file does indeed connect to our smart contract, we head over to the terminal and then run node query.js. And what is returned does confirm that we are able to query our smart contract, since all of the 10 cars in our database are now available here. So we have now learned that connecting to a deployed smart contract is not all that complicated in and of itself, but there is a lot of setup work which goes into it. So now we can close out this query.js file since we have made use of it successfully, and we will write another source file in order to connect to our Fabric network and our smart contract and to trigger the create car function within it. So I'll go ahead and create a new source file within the JavaScript directory, and then we'll go ahead and paste the contents. Just as before, it uses the useStrict directive. We import the file system wallet and gateway classes, and also the FS and path packages. We initialize the connection profile by using the connection.json file, and then begin the definition of the main function. Just as before, we create an instance of our wallet, and then we check whether user1 has already been initialized. And this is just copy pasting the code from the previous source file essentially. And then once we confirm that the user1 profile does exist, we'll then create our gateway instance. Once again, the user1 identity is used to establish the connection to our Fabric network. And then we create an instance of our channel using a call to gateway.getNetwork. And we use that channel instance in order to retrieve our car store smart contract. At this point, we can make a call to our smart contract's create car function. And on this occasion, our call is made to the contract.submitTransaction method. In the previous source file where we made a call to the query all cars function, the function which we invoked was contract.evaluateTransaction. The distinction here is that previously we simply performed a read operation from the contract state, whereas on this occasion we are performing an update to the contract state, which is why we need to submit a transaction. The arguments to submit transaction are what we will pass into the invoke function. That is, we start off with the name of the function within our contract which we want to invoke, which is create car, followed by the list of arguments to that function. There are, of course, 5 of these, starting with the ID for the car, which is car12, and then the make, model, color, and owner for the car, which we set to Honda, Accord, Black, and Bob. Once the transaction has been submitted, we print it out to the console, and then we use the gateway instance to disconnect from the network. This is to prevent any dangling connections from eating up our resources. With that, our function definition is complete, and at the end, we catch any errors which are thrown and then print them out to the console. And we end our source file with a call to the main function. So I'll quickly save this file, and I'll call this invoke.js. And then we can head over to the terminal in order to run this file. So we execute node invoke.js. And this time we get an output which just says that the transaction has been submitted. Since we hard-coded the addition of the new car, we will need to invoke the query all cars function to confirm that this has indeed been added to the database. And we do that by running node query.js. So the output does include a lot of cars here, and it may be a little complicated searching for the newly added car, which was car 12, but I'm just going to use the find feature in the terminal to search for car 12. And this confirms that the newly added car, which is a black Honda Accord, has indeed been added to the database. So we have now successfully queried data from our deployed smart contract, and we have also updated the contract state with a call to the create car function. Since we're able to do all this by means of a Node.js application, we should be able to do this from a user interface as well. And that is exactly what we will begin to do. We will now begin coding up what we require in order to have a front end for our smart contract application. This front end will allow us to view the details of a specific car by accepting a car ID from the user, and then it will effectively make a call to the query car function within our smart contract to retrieve the details of that vehicle. It will also include a form where we can enter details in order to add a new vehicle to our database. This will require a call to be made to the create car function in our smart contract. So we effectively need two different function calls for the UI. One to the query car function and another to the create car function. We can do that by means of another source file. So I'm now going to close down this invoke.js which we created previously. And then within the JavaScript folder, create another source file. As always, I'll first go ahead and paste the source code and then walk you through each of the steps. We have the use strict directive once more. We import the file system wallet and gateway classes from the Fabric network package, and also import the FS and path packages. We then load our connection profile into this variable called CCP, which is a JSON object. And then we define the first function. So this will be something which will be invoked from the UI. This is a function called getCar, which accepts as an argument the car ID. We will use that car ID in order to invoke a call to the query car function and retrieve the details of the car whose ID has been passed in. So within the try block of this function, we first initialize an instance of our wallet. And then with that wallet, we check whether there already exists a user called user1, because we need to make use of those credentials. If the user does not exist, we simply exit from this function. If the user does exist, however, we will initialize a gateway instance, and then we will make a call to gateway.connect in order to establish a connection to our Fabric network. And to do this, we will pass along the connection profile, which is in the CCP variable. And then we will pass along an object which includes the wallet. We specify the identity within that wallet which needs to be used for the connection, which is user1. And then we disable the discovery service. We will need to retrieve the smart contract in order to invoke the call to query car. And to do that, we first need to get a channel instance. So we retrieve an instance of my channel with a call to gateway.getNetwork. And then we use that channel instance in order to retrieve our car store smart contract. with that contract instance, we make a call to contract.evaluateTransaction. You will recall that evaluate transaction is used in order to read from the contract and not perform a write operation. And the argument to evaluate transaction starts with the name of the function within our smart contract, which needs to be invoked, which is query car, followed by the arguments to the function. In our case, there is just a single argument, which is the car ID, which we pass along to this function call. The value returned by the function call is captured in this variable called result, and then we print out the contents of that result to the console, and we will also return this result data to whoever has made the function call, which in our case will be the UI application. And then if there are any errors thrown during this function call, it will be caught, and then the details will be printed out to the console. So with this, the definition of our getCar function has been completed, and we move along to the second function which we need to define, which is called addCar. So this will allow the user through the UI to add the details of a single car into our database. The car details, of course, include 5 different fields which are passed along as arguments to this function, the fields being the ID for the car, the make, the model, the color, and the owner of the car. Just as we have done a few times before until this point, we initialize a wallet instance and check whether the application user exists in that wallet. We then make use of the user in order to establish a connection to our network by means of a gateway instance. And then we retrieve our smart contract by first creating an instance of my channel and then retrieving our contract instance from that. Now, we will first print out to the console all of the arguments which have been passed along to the function, and then make a call to contract.submitTransaction in order to submit the details of the vehicle to the contract and then add it to the database. The arguments to submit transaction will be the name of the function within our contract to invoke, which is createCar, followed by the 5 arguments to that function. And then we print out to the console that the transaction has been submitted, following which we use the gateway instance to disconnect from our Fabric network. We get to this point, of course, if the code execution has been a success, and in case of any errors, we catch it and print it out to the console. Now, just for debugging purposes, you can include a simple function which will just print out to the console some text in order to make sure that the connection from the UI to this particular JavaScript file does work as expected. If you do stick to the same code which I have used so far, you should not have any issues, but I just included this in case you run into problems. We will be importing this JavaScript source file into our UI JavaScript file. So in order to access each of the functions which we have defined here, we will need to explicitly export those functions so that they can be imported and accessed from the other source file. So getCar, addCar, and even the debugging function hello will be exported. And now we have completed the coding up of this source file. So I'm now going to save this to the system and call this car.js. It is now time for us to code up the front end of our application, and that will be importing this car.js file. And then that application can be created within a new folder within this JavaScript directory. The coding up of that application, though, will take place in the next video. Now that we have coded up this car.js source file, which makes calls to 2 different functions within our smart contract, one of these to retrieve the details of a car given its ID, and the other to publish the details of a single car to the database, we will now create a web application which will make use of these functions and enable interactions with our smart contracts by means of a web UI. To begin, we'll create a new directory within this JavaScript directory within our project, and I'm going to call this app. And then within the app directory, I'll create a new source file. As always, I'll paste the code and we'll walk through it. So we use the use strict directive, and the packages which we import are HTTP and Express. In case you haven't used it before, Express.js is a web application framework for Node.js. It includes all of the components which are needed to create a web application. All we need to supply is the code. So here we initialize our Express app by calling the Express constructor. And then following that, we import the car.js file which we just defined. So this is referenced as fabcar. And then following that, we will start up our HTTP server with a call to http.createServer. To this, we pass along our Express app as argument. And then we get the server to listen on port 3030. So we will start up this HTTP server serving our web application on port 3030 of our local host. We then print out to the console that the app has started, and we also set the timeout for the server. There will be a few different routes which we set up for our application, starting with one route called getOneCar. So this can be invoked with a GET request, and here we expect that the request body will contain the car ID for which details need to be fetched. We will then query the smart contract to retrieve the details for that car, and then we will publish the HTML which will display all of those car details. So within the body of this function, we first capture the ID of the car from the request body, and you'll observe that we are extracting this ID from the query parameters. And this we get in a variable called car ID. And then after that, we make a call to our smart contract by using the fabcar object, which of course represents the car.js file. So within that JS file, we make a call to the getCar function, whose argument is the ID of the car whose details need to be fetched. To ensure that the car ID is in the correct format, we perform a toString followed by a toUpperCase operation. So invoking this fabcar.getCar function will return to us a JSON string which will contain all of the details of the car. We capture the details in this response variable, and in this callback function we define exactly what needs to be done with that response. First of all, we print out that response to the console, and then beyond that, it is up to us to extract each of the individual fields in that JSON object and then display it in the HTML page. And there are a number of different operations being performed here. First of all, we convert the response to a string format using the toString function. Following that, we get rid of the first and last characters using the slice function. We then remove all double quotes in the response using the first replace function, and then there is a second replace function to substitute all colons with a hyphen. And finally, we perform a split operation on the comma character so that each of the fields in the response will become their own elements within an array. So this result variable created by this sequence of operations will be an array where each element of the array will be the name of the field which is returned, followed by a hyphen, and then followed by the value of that field. With the splice operation, we also include the car ID in the results array and then print it out to the console. So while we have printed out the data to the console, in order to display it on the HTML page, we can now begin formatting the HTML. So all of the car data will be included within an unordered list, and then each of the result fields will be a list item. So we create an unordered list and then iterate through each of the elements in the results variable and then include them as a list item. And then we close out the unordered list. So the entire HTML of our car data, which is within an unordered list, is within this variable called data, which we now need to embed within an HTML page. And that HTML page is what is returned within the response object for this get call. So here we create an HTML page which has the title of car shop, and you can see how we embed this data variable within the HTML page. So we have successfully defined a get operation where a user can supply a car ID, and then we return the details of that car and embed it within the response in an HTML page. Which moves us along to the next route in our web app, and this is one to add a new car to our database. So this again has been implemented as a get operation, but since all of the details which are submitted is included within the request body, this can also be implemented as a post operation. When this operation is invoked though, the request body must contain all of the details about the car which needs to be added to the database. So the callback, which includes the request and the response, will first extract all of the different fields for the car from the request body. This body needs to include the car ID, the make for the car, the model, a color, as well as the car's owner. We then print out each of these details to the console, mainly for debugging purposes. And then following that, we use the FabCar instance to invoke the addCar function. And this is where we will pass along all of the details which are included in the request body to add this new car to the contract database. You will recall that the addCar function accepts 5 different arguments: the car ID, the make, model, color, and owner. And in this case, we ensure that the car ID is in the correct format by performing a toString followed by a toUpperCase. So when the addCar operation is invoked, we won't be returning anything in the response body. And later on, when we do add a car to the database from the UI, we will check that the car has indeed been added by making a call to the getOneCar operation. So with our 2 main routes defined, I include another one called hello, and this is just for debugging purposes. So you don't really need to include this, but you may choose to. And then we define another route for our home page. So within this, we will define the HTML which makes up the home page. So we start off by setting a title for the page, which is car shop. And then within the body, we include one section where we have a header of resale car shop. And then we include a form where the user can enter the car ID for a vehicle and then hit a button so that the details for that vehicle will be retrieved and displayed. You can see in the action attribute for this form that hitting the submit button for this form will invoke a GET request on the getOneCar route. So this makes up one section of our homepage. And then in the next section, we include another form. And this is one where the details of a car can be entered, for which there are 5 different text boxes. And then when the submit button is hit, this will invoke an operation, specifically a GET request, on the addCar route. All of the details which have been filled up in the text fields for this form will be included within the body for this request. And then following that, we can just close out the form and then close out the body and the HTML tags as well. We also conclude the definition for our home page route. And with that, we have now finished the definition of the home page of our web app. Just one more thing before we save down this file though. Note the link to this particular CSS file, which we have included right at the very top. So with that, I'll just go ahead and save this file as index.js. And now all of the coding for our application is complete. All that is left in this course is for us to run this application and then make sure that it works exactly as we defined it to. Now that all of the coding for our web application is complete, we can start up an Express web server and then access our application and then make sure that it works exactly as we designed it to. In order to spin up an Express server though, we first need to make sure that Express has been installed. So we can head over to the terminal and then we use the npm package manager in order to install both the HTTP and Express packages. So we run npm install-save HTTP and Express. And once these packages have been installed, we are now ready to start up our web app. And we can do that by making sure that we are in the JavaScript directory. And then we run the command node app because our application is within the app directory. With that, we'll get a notification that the app has been started. And you will recall that within our JS file, we defined that the server should be brought up on port 3030. So we can now bring up a web browser and then try to access our app on localhost port 3030. And as long as everything has been typed correctly, the page will load up and you should see this resale car shop page within your own browser. Alright, so it's now time for us to put this web app to the test. And the first thing we can check is that the details of a particular car can be retrieved by supplying its car ID in this text field. So I have already run this a couple of times. So I have a couple of cars visible in my history. And out of these, I'm going to select car 2. And then upon hitting the submit button, this will invoke the get one car route, and all of the details for that car are now visible. So this operation has been a success. Our application was able to gather the car ID, connect to our Hyperledger Fabric network, and then retrieve all of the details for that car, and then display them in the web page. If we head back to the terminal where we started up our Express server, we can see that the console.log messages which we included have made sure that the details are output to the console as well. So I have highlighted the formatted output which we printed out, and then just above that you will see the other detail which we published to the console, which is the raw JSON which was returned by the invocation of the getOneCar function. Now, since this getOneCar operation was implemented as a GET request, all of the details which we submitted will be available within the URL. So here you can see that the ID is available here and is also available for us to edit. So if you would like to retrieve the details of another car, say car 12, then we can edit this query parameter in the URL and then hit enter. And the details of the black Honda Accord, which we added just a little earlier in this course, will be available in the HTML page. And in fact, we can also view the same details in the console. So our operation to retrieve the details of a particular car from the database does work exactly as we expect it to. Alright, so that is half of our web application, which seems to be in good working order. It is now time for us to test out the other operation. So let us head over now to the home page. So back to localhost port 3030, and then check out the second operation where we can add another car to the database. Now I'm going to make sure that I use a car ID which hasn't been used previously, just to ensure that it is a new car which is being added. If you use a car ID which already exists, then that data will simply be overwritten. So I'm specifying a car ID of car 13. And as for all of the other details of the car, this is going to be a Toyota, and the model for this is a Prius. I will go ahead and fill up the remaining fields in the form. So the color for this Prius is going to be black, and the owner of this Toyota is going to be someone called Adrian, let's just say. Alright, so with all the details filled in, I'm going to hit the submit button. And of course, this doesn't really produce any output. However, if you do want to confirm that the transaction to add this car has been submitted to the blockchain, we can head over to the console, and we have that confirmation here. The create car operation within our smart contract has been triggered, but to make sure that the addition of the car to the database has been a successful operation, we will need to query for the information first. Now, thanks to the fact that we implemented this operation with our UI, we can head back to our home page, and then from here in the get car details section, we'll now query for the details of car 13. Note here the difference in case. So when adding the car to the database, I specified car 13 using uppercase characters, and during the search operation, I'm entering lowercase characters for car. However, this will not be a problem because we handle that by performing a to uppercase operation on the ID which is included in the request. So with that, we can test out that this car has been added to the database by hitting submit. And the result confirms that this black Toyota Prius has indeed been added to our contract state. You can feel free to add more cars to the database and then query for them using the UI. But for completeness, we can also head back to the terminal and then ensure that all of the details have been printed out to the console as well. So we now have a web application which is able to interact with our deployed smart contract on a Hyperledger Fabric network. So let us quickly summarize what we have done here. We first wrote a smart contract which stores the details of various cars within the contract state. We deployed it to our Hyperledger Fabric network. And then we wrote a Node.js application which will use identities which are stored within a file system wallet to connect to the Fabric network and the smart contract and then interact with it. We then built a small web application which is able to interact with our Node.js file and through that interact with our deployed smart contract. So what we have implemented in this learning path is an end-to-end solution, from the provisioning of a Fabric network to building a web app which is able to work with contracts on that network. In this exercise, you will perform a couple of tasks related to working with chain code from a Node.js application. First of all, you will use a gateway instance in order to retrieve chain code from a Fabric network. A gateway instance will take in a connection profile and then establish a connection to the Fabric network. Once the connection has been established, it can be used in order to retrieve some chain code, which you can then use to invoke transactions and to perform query operations on that smart contract. Which in fact leads us to the next task, where you will use that retrieve chain code instance in order to perform read and write operations in your blockchain network. We saw that there are different operations which you need to invoke in order to perform read and write tasks, and you'll need to identify exactly what those are and what arguments need to be provided to those. Each of these topics were covered during this course, so please pause this video and then take some time to perform these tasks on your own. For the first task, you needed to retrieve an instance of your deployed chain code from a Hyperledger Fabric network using a gateway instance. Well, to start off with, you need to import the gateway class into your source code, and you can do that from the Fabric network package. Once you have the gateway class, you can create a new instance of the gateway, and with that instantiated gateway instance, you can connect to the Hyperledger Fabric network. All the details for that connection will be supplied in the connection profile file. This file includes definitions for the various components which make up your Hyperledger Fabric network. This includes the ordering service, certificate authorities, the different peers, even channels in your network. And it will also contain the details of the host and port at which each of these services are accessible. The connection profile is supplied as an argument to the gateway instance's connect method. The other argument to this connect method are a collection of options, and this can include a wallet as well as the identity within that wallet which needs to be used to establish that connection. So at this point, the gateway instance will have connected to the Fabric network and will be aware of every component which exists on that network, including all of the channels. You will then proceed to use that information in order to retrieve an instance of the channel which contains the deployed chain code you wish to access. The way to do this is to once again use the gateway instance, specifically its method getNetwork. And the argument to this is the name of the channel which needs to be retrieved. This will return to you an instance of the channel, and then you will go ahead and use that channel instance to retrieve the chain code. The specific function of your channel instance which you will need to call is getContract. The argument to this being a string which represents the name of the contract which needs to be retrieved. This will return to you an instance of your smart contract which you can use to perform a number of operations as defined within that contract. And this in fact takes us on to the next task, where you needed to use a deployed contracts instance in order to perform read and write operations. A read operation is one where you are effectively querying the contract state. This operation will not modify the state of the contract or of the ledger in any manner, and the way to perform this query operation is to use the contract instance's evaluate transaction method. The arguments to this include the name of the function defined within your contract which you need to call, followed by the list of arguments for that function. And just to reiterate, This particular function should not perform any write operations. That is, it should not invoke a transaction. And since there is no transaction involved, the responses which you receive from invoking this evaluate transaction function will not be sent to the orderer or committed to the ledger. So while this covers read operations on a contract, in order to perform a write operation, we will need to submit a transaction. The way to do this is to invoke the contract instance's submit transaction method. And once again, the arguments to this include the name of the function in your contract which will invoke this transaction, followed by its list of arguments. The responses obtained from calling that function will contain the details of the transaction, and that needs to be sent over to the ordering service. And then once that has been validated, it will be committed to the ledger. This course covers the lab section of using Hyperledger Composer, specifically using Hyperledger Composer Playground. We will explore how you can prototype a business blockchain network using Composer Playground, where you make use of the Composer Playground UI and also the business level abstractions within Composer in order to specify what exactly your blockchain network consists of and the types of operations which are permitted on it. We will then cover how we can deploy that blockchain network over to a test environment. And after the testing is complete, we will take a look at how we can export the network definition over into another environment, which could be your production setting. Now, Hyperledger Composer Playground can be downloaded onto your own host, or if you simply want to quickly prototype a network, then you can make use of the Composer Playground on the cloud, which is what we're going to navigate to right now. This is available at composer-playground.bluemix.net. And once we navigate over to this website, we can see that they advertise themselves as a web sandbox where you can provision a blockchain network and test it out and ensure that it works exactly as you want it to before you deploy it within your own organization or organization consortium. The availability of Hyperledger Composer Playground on the cloud attests to the fact that Hyperledger does truly seek to democratize blockchain technology by making it as easy for users to build out their blockchain application as it could possibly be. All right, so we can now head over and then begin creating our blockchain network, for which we just click Let's Blockchain. The home page of Composer Playground shows you the different networks which you have provisioned. Currently, there is only a basic sample network, and this is in fact a good point for us to get started with Composer Playground. So you can just go ahead and click on this Get Started button, and this will log you in as an admin user within this basic sample network. So you can see that this comes pre-packaged with all of the files which you need in order to define the network, and you can see the files listed here along the menu on the left. At the top, there is a README file, and we will explore the content shortly. There is the model file, which has the CTO extension, and this is where you define the different resources within the network. There is the script file, which is the transaction processor, and then the access control file with the ACL extension. We can explore each of the files in the sample network one by one, starting with the README file. So this is already up in the menu on the right, and this includes details of what this sample network currently contains. And within your own application, you should create something similar which will allow other developers to jump on board and begin developing or extending the blockchain network. So we can scroll down within this file, and you'll see there are a number of details which include, for example, what kind of participant exists within the application. And remember, the participant is defined within the CTO file. And there is also a sample asset which is defined within that CTO file. So all of these, you will observe, are represented in a JSON-like format. And this README file is just meant to get a new user familiar with all of the details defined within the CTO file and the rest of the application. In our case though, let us now head straight over to the model file. And this, you will remember, is a file within which you can define the different resources which make up your blockchain network, and the resources could include assets, participants, transactions, and so on. And this is done using a modeling language. We can now take a look at exactly what this looks like. So the modeling file does start off with a comment section, and then we move along and we start off with the definition of a namespace. So this is the namespace org.example.basic, within which all of the resources defined within this model file fall under. The namespace is a good way to reference all of the resources within your model file, and we will be using that within the access control file, which we will explore just a little later. For now though, we move along to the definition of the resources within the CTO file, starting with the definition of an asset. We do this by using the keyword asset with a lowercase a, and the name of this asset is sample asset. Each asset of type sample asset will have an identifier, and in order to specify that, we make use of the key phrase identified by, and the identifier in this case will be asset ID, and that is a property defined within the definition of the sample asset. So the sample asset definition contains three different properties. The first of which is a string type, and this is the asset ID, which is the identifier. And you will notice the lowercase o at the beginning, which represents a property which is owned by this particular resource. This also applies to the third property here, which is called value, and that is also of type string. Note here that string begins with an uppercase S. So these cover the two owned properties of this asset, which represent the asset ID and the value of the asset itself. And then in order to represent the owner of the asset, we make use of a reference type, which is denoted by the arrow symbol made up of two dashes followed by a greater than sign. Such a reference must pertain to another resource which is defined within the CTO file, which in our case is a sample participant whom we call owner. We move along now to the next resource, which does define the sample participant type. A participant is defined using the keyword participant, and once again we make use of the identified by clause in order to specify the identifier for this particular participant. So it is the participant ID property which is going to be the identifier, and we have two other properties for the participant, the first name and the last name. All of these are own properties of this resource, and there are no references in this case. We now move along to a different resource within the CTO file, which is of type transaction. We call this sample transaction, and the definition of a transaction within the CTO file typically references an asset and potentially a participant as well, along with some other details, but only at a high level. The actual processing of the transaction is defined within the transaction processor script. So in our particular example, the transaction references the sample asset type, which was defined a little earlier, and then also includes another property called new value, which is of type string. So this sample transaction, when it is invoked, will reference an instance of sample asset and will also take in a string called new value. It will then update the value property within the sample asset instance with the contents of the new value variable. So effectively, this transaction is to update the value of the asset it references. And just to reiterate, the actual logic to update the field within the asset will be defined within the transaction script file, which moves us along to a third type of resource within the CTO file, and this is an event. So just like with the other resources, you can have both reference types as well as owned properties within an event. So in this particular sample event, it will be thrown each time a sample transaction is invoked, and we will reference the asset which is being updated by the transaction, and will also display the contents of the old value field within the asset and the new value it is being updated to. All of this, once again, will be implemented within the transaction processor script. And with that, we come to the end of the definition of this CTO file. In the previous video, we accessed Hyperledger Composer Playground on the cloud and then started going over the sample network definition which was already provided. We already took a look at the model file, which is in the CTO language, and within that, 4 different types of resources have been defined: an asset, a participant, a transaction, and an event. While the CTO file did contain what exactly the transaction instance will look like, we now need to define within the transaction processor the exact logic to implement within the transaction. As touched upon previously, what we do wish to implement is for the value field in a particular instance of an asset to be updated with a new value. Let us now take a look at how this can be done using the transaction script. So within this script, which is a JavaScript source file, we see that it begins with a comment section. So this particular comment section is not all that important, but there is one immediately following this and just before the beginning of our transaction function definition, which absolutely is necessary. Even though it looks like a comment, this in fact defines a lot of the details of the transaction itself. So it contains essentially 3 different lines. The first one is just a one-line description of what the transaction processor does. The next one, which begins with @param, defines the particular transaction resource which the transaction processing function immediately following it will be referencing. In our case, you need to specify the resource using the full namespace definition. So it is org.example.basic.sample transaction. And the instance of the transaction within this processor will be referenced as tx. This is followed by the third line, which is @transaction, and it defines the following function as a transaction processor. We follow this up with the beginning of the definition of the transaction processing function. This one is called sample transaction, and the argument to this will be an instance of the transaction resource. You will recall that within the CTO file, we defined a transaction resource to include an instance of a sample asset and also a field called new value. This sample transaction function begins by setting a variable called old value to the contents of the value field of the asset which is referenced within the transaction. Note here that the transaction's asset can be referenced as tx.asset. So this old value variable will contain the value of the asset before it gets updated within this transaction processing function. And in the next line, we define exactly how this update will occur, where we set the value of tx.asset.value to tx.newValue, which is something which the user will need to provide when invoking the transaction. So at this point, the value of the asset instance within this transaction processor has been updated, but in order to update it within the state of the blockchain network, it needs to be set in the asset registry. This is what we access now in the next step, where we make a call to get asset registry, and the argument to this is the type of resource defined within the CTO file for which the registry needs to be retrieved. Of course, in our case, this is org.example.basic.sample asset, and this will return all of the instances of sample asset which we have defined. Now, this is available in a variable called asset registry, and we call the asset registry.update method in order to update the registry with the new contents of the asset. Remember that each sample asset instance is identified by the asset ID field. So this will update the specific asset which has been referenced within the transaction. So now that our asset has been updated, the last thing for us to do within this transaction processor is to emit an event which records the fact that an asset has been updated. So in order to get an instance of a new event, we make use of the getFactory method. And with the factory instance which is returned, we invoke the new event method in order to get an instance of the sample event as defined within our CTO file. So with that sample event, we will update the asset. We set values for the old value as well as the new value properties defined within the sample event. And following that, we emit the event by calling the emit method from this function. So this concludes our transaction processing script, where we have defined exactly how a particular asset instance can be updated and then recorded an event. Previously, we covered the modeling file as well as the transaction processing script for this sample blockchain network on Composer. We can now move along to the ACL file within our blockchain network definition. And this, of course, contains the different permissions for the various resources within the blockchain network. So we can now view what this sample ACL file looks like. So it starts off with a big comment section, but when we scroll further down, you'll see that it includes a collection of rules. Each rule has a name followed by a lot of data related to the rule. And we can now take a look at the first rule here, whose definition begins with the keyword rule, followed by the name of the rule, which is everybody can read everything. This rule is meant to permit all instances of sample participant in the network to read data about all of the resources on the network. The rule, as you can see, is defined using a JSON-like syntax, and this specific rule has 5 different fields, which starts off with a description, followed by the specific participant whom this rule applies to. This, of course, is of type org.example.basic.sampleParticipant, and all instances of the sample participant will be able to perform a read operation, which is defined in the next field, and the resources on which they will be able to perform this read operation are all of those which are defined within the org.example.basic namespace. The asterisk here is a wildcard which denotes all top-level resources in the namespace, and the type of action which this rule applies is allow. So just to summarize, this rule means that all instances of the sample participant will be able to perform read operations on all resources defined within the org.example.basic namespace, which moves us along to the next rule for our network. And this is called everybody can submit transactions. And as the name suggests, this is meant to allow all instances of sample participant to create transactions on the network. So following the description, we define that this rule applies to all instances of sample participant, and the resource to which the rule applies is of type sample transaction. And what exactly can instances of sample participant do with instances of sample transaction? Well, they are allowed to create new instances of the sample transaction. So the different values for the operation field can be create, read, update, and delete. Or if you simply wish to reference all of those types of operation, you can use the keyword all. And the permitted values for the action field are allow and deny. Which moves us along now to the next rule, where we have a slight variation on the previous rules. So in addition to the description, operation, and action fields, you will notice that with the participant and resource fields, we are now referencing specific instances of a participant and resource. And then we are also applying a condition. As the name of the rule implies, this particular rule is meant to allow the owner of an asset to do anything on the asset which they own. And this new notation is necessary in order to reference the specific owner of a specific asset. So here, we follow the name of the participant field by mentioning a variable p in the parentheses to denote that this references a specific instance of a sample participant. And similarly, we define that this rule applies to a specific instance of a sample asset, which we reference as R. So using the combination of the action and the operation, we say that a particular instance of a sample participant has all access to a particular instance of the sample resource. And what are these particular instances of the sample participant and the resource? Well, this is what we specify in the condition field, where we point out that the owner of the asset must be the same as the participant who is invoking this operation. So the combined effect here is that the owner of a particular asset will be allowed to perform all operations on the resources which they own. So while the three rules we have covered so far have been specific to this basic sample network, we now come along to a few generic rules which are included within the ACL file and will typically apply to any blockchain network. So we start off with one called System ACL, where all of the participants in the system are given all access to all system level resources. So all participants in the network are referenced as org.hyperledger.composer.system.participant, which of course is a system level resource, and we allow them all access to all system level resources, which are referenced using the namespace org.hyperledger.composer.system. Note the double asterisk following the system namespace here, which references not only the top level resources within that namespace, but all sub resources as well. So while this particular rule may be a little too permissive for many different blockchain systems, this is just an example of how you can reference system level resources, which takes us along to the next rule, which applies to a network admin user. So this is a user which is automatically provisioned by Hyperledger Composer, so you don't need to explicitly define it within the CTO file. And the specific participant is org.hyperledger.composer.system.networkadmin. And you see that they have access to every single resource in the blockchain network. And similarly, if you'd like to grant your network admin access to all system level resources, then you will grant the same participant access to all resources defined in the namespace org.hyperledger.composer.system. And with that, we come to the end of the definition of the ACL file for the blockchain network. A couple of things to keep in mind with the ACL file is that all of the rules which are defined within this are evaluated in order. When there is a particular action which has been invoked in the blockchain network, say a participant tries to access a resource, then Composer will check within the ACL file, starting with the first rule, whether there is a rule which matches that particular operation. The first rule which applies to that resource and participant will be the one which is applied, and if there is no matching rule which has been defined, then by default, that action is denied. And with that, we come to the end of our definition of the business blockchain network on Composer Playground. In the next video, we will deploy this network over to a test environment and see exactly how one can interact with the network. So the sample network, which has been defined within Hyperledger Composer, contains three different definition files. One of these is the model file with the CTO extension. There is the transaction processing script file, and then an ACL file. There is also a query definition file which can be included as part of the network definition, but this is purely optional. We will be skipping that for the sample network. And in order to see how we can test out the functioning of this network, we will now go ahead and deploy it to a test environment. So note here, just above the deploy changes button, there is a to field, and this is where you can edit the version number of the blockchain network definition. So I'm going to leave this as the default, which is 0.2.6-deploy.0. And when hitting the deploy changes button, there is a notification on the right which confirms that the changes have been deployed, and this deployment has happened in the test environment. Notice just above the deploy changes button that the version number has also changed. This will apply to the next deployment. So now that our network has been deployed to a test environment, how exactly can we access it? Well, for that, we head over to this test button at the top of the page. And then from here, we can create instances of the different resources which we defined within our application. So we can create instances of sample participant, sample asset, and also create new transaction instances. So clicking on the sample participant button here, we can see on the right that there are no instances of sample participant yet, That is, the asset registry for this particular resource is empty. We can add a new instance of a participant to this registry by clicking on this button, Create New Participant. And this will present to us a user interface where we can enter details of a participant using a JSON definition. You will notice that within this JSON definition, there are 4 different fields. The first one references the class to which this particular JSON data structure points to. And then following that, the 3 fields of the sample participant instance can be initialized. A value has already been entered for the participant ID, while the first name and last name properties have been set to blank strings. Let us now go ahead and fill in our own details. Firstly, this sample participant instance will have an ID of 001. Her first name is Alice, and her last name will be set to Doe. We scroll down and click on the button Create New, and Alice Doe is now a new participant who has been created in our blockchain network. We can go ahead and create another new participant, and once again we edit this JSON definition. So this one will have a participant ID of 002. The first name will be Bob, and the last name is Smith. Scrolling down, we create this new participant here, and we now have Alice Doe and Bob Smith as 2 instances of sample participant. Alright, with that we can go ahead and create a new sample asset instance. So clicking on sample asset in this menu, this registry is also empty, unsurprisingly. So we'll create a new asset. And once again, we are presented with this JSON data structure. So once again, there are 4 fields which include the 3 properties for the asset as well as the class field. And you'll notice here that the owner field references an instance of sample participant. So we will need to specify the ID of the sample participant who owns this asset. Let us begin editing this data structure. So this new asset we are creating will have an ID of 01. We then edit the owner field, and we need to reference one of the sample participant instances we have created already. So to make sure that Alice is the one who owns this asset, we set the value here to 001, which references the Alice participant. And then finally, we set a value for this asset as 1000. So with this instance of sample asset defined, we will go ahead and create this new asset. So we now have a new asset in our blockchain network as well. To view all the transactions which have been invoked in this blockchain network, we can head over to the transactions section and click all transactions. And you'll observe that 4 transactions have already been recorded. The transactions here are in reverse chronological order, and the first transaction, which is at the bottom, represents the creation of the current identity. If you notice on the top right, we are logged into this test network as the admin user. The other transactions were the ones created in order to create the new participants and the asset. To view the details of a transaction, we can click on the link View Record, and this will take us to the historian record where all transaction details are logged. So the historian record is defined using the JSON format as well, and the details of the different transactions in the record are available here. So you can see that this particular transaction represents the creation of our sample asset instance. This contains the details of the asset which was added, followed by its addition to the registry. In the historian record, we are currently in the transaction tab. And if you'd like to view all of the events which have been recorded in the blockchain network, those are also available in the historian record on the events tab. There are no events recorded so far. However, one will be created if we invoke the transaction which we defined within our blockchain network. That is something we will be doing in the next video. So for now, you can just close out of this historian record. We have now created 2 instances of participants in our blockchain application, and we have also created an instance of an asset. It is now time for us to record a transaction, and you will recall that the transaction which we have defined alters the value of the value field in the asset with a new value. Before we invoke a new transaction, we can take a look at the sample asset instance we have created. So this has an asset ID of 01 and a value of 1000. We can now go ahead and alter this value field by hitting Submit Transaction from the menu on the left. Clicking this will bring up a dialog where we can see that the details of the transaction can be entered using this JSON definition once more. And you'll see within the JSON structure that it references an asset, and there is also the new value property which we defined. Now, within this particular dialog, you can choose from a drop-down menu the specific transaction which you wish to invoke. This is not quite applicable for our blockchain network since there is just one transaction defined in our CTO file, and this is the sample transaction which has currently been selected. Let us now invoke the sample transaction instance. So here we specify that this is meant to alter the asset which has an asset ID of 01. So we enter the ID of the asset here. And then following that, we specify the new value property which will be assigned to the value field within the sample asset instance. So we'll be altering that value from 1000 to 500. With this change made, we scroll down and hit Submit. And within a few seconds, you should see this notification pop up in the top right that the transaction submission was successful. The real confirmation of a successful transaction, though, is to check that the value field within our asset has indeed been modified, and we can see that right here. So the transaction processor has successfully altered the value of this sample asset instance. We can now go ahead and submit one more transaction, and this time we will try something a little different. So when the dialog pops up, we have the JSON definition once more for the transaction. And on this occasion, we will alter this asset which is being referenced in the transaction, and we will specify an asset which does not exist. So this time, we will reference an asset with the ID 002, and we'll set it a value of 20. What happens if we submit this transaction? Well, we get an error, and this is expected because there is no such asset defined within our blockchain network. So the Composer Playground application ensures that we're working with resources which do exist. We can cancel this particular transaction, and I'll now go ahead and alter the JSON definition so that it is referencing an asset with the ID 001. And remember, the ID of our asset is in fact 01. What happens if we submit this transaction? Does it disregard the first 0? Well, the answer is no. So this once again has thrown an error, and clearly 0 is not an insignificant number here because the asset ID field in the sample asset is in fact a string. So with a couple of failed attempts, I'm just going to go ahead and reference the asset ID which does exist. So this is 01, and then hit Submit. And this transaction has also been submitted successfully, and we can confirm from the value field that the new value which we set to it has also been applied. So we have now successfully invoked transactions and recorded them on our blockchain network. One thing to keep in mind here, that all this while we have been logged into this test network as the admin user, which you can confirm from this top right menu here. And there are options available where we can create IDs for the instances of participants we have created and then log in as them. But that is something we will cover in the next demo. So if you head over to the test tab and then take a look at the two sample participant instances we have created, it is possible to connect to the network as either Alice or Bob and then record transactions which will change the value of the assets. So you now have a fairly good idea of what Hyperledger Composer Playground is all about. We saw in this sample network how we have different definitions in the model file as well as the transaction processor and the ACL file as well. We saw how we can deploy the blockchain network over to a test environment and create new instances of assets, participants, and also submit transactions in order to test out our network definition. It is now time for us to build our own blockchain network, which we will do so in the next demo. But first, let us head back to the main page of Composer Playground, which you can access by clicking on the admin button and then clicking on Business Networks. With the previous demo, where we took a look at the basic sample network which is available in Hyperledger Composer Playground, you will now be rather familiar with the Composer Playground interface. You also have some idea of the CTO language, the transaction processing script, as well as the ACL language. So we can now go ahead and use that knowledge which we have just acquired in order to move on from the sample network and then deploy our own business network. So by clicking on this button, we will be prompted to enter details about the new business network which we wish to provision. And we have a few options here. If you scroll further down, you see that there is an option to create this new network out of an existing template. And there are many different templates which are already available, which you can download using npm. So for example, there is one for animal tracking, also one for a car auction, and one which represents digital property. Each of these will create a blockchain network which contains the model definitions as well as transaction processing functions and ACLs, all suited for the particular application. You can then build upon that in order to customize the network for your own purposes. Scrolling further down, you can see that there are networks available for perishable goods and also one to track a vehicle during its entire lifespan. And these can be particularly useful if they mirror what you wish to implement. For this particular demo, however, we will be building a network essentially from scratch. So we scroll back up and then choose to provision an empty business network. The business network we are about to build is meant to track assets which are moving through a supply chain. So we make the selection, and then following that, we specify a name. So I'm going to clear out this default name which has been generated and call this trading network, since this is going to involve assets being traded from one participant in the supply chain to another. Here I'm going to set a description for this network. And then following that, we need to specify something called a network admin card. This is essentially a form of identity which is issued to the administrator for the network. So I'm going to call this admin at trading-network. So these are the only details which we need to supply, and the details are summarized on the right here. So I'm just going to go scroll further down and hit deploy in order to provision this empty business network. This takes us back to the home page of Composer Playground, and you can see that this identity of admin at trading network is now available for us to use in order to log in to our network. So we can hit connect now, and we are now signed in as the administrator on our brand new trading network. So in our empty business network, you can see that even the README file is virtually blank, and we won't be touching this for this demo. We will head over instead to the CTO file, and this includes the comment section, and following that, just a namespace definition. We don't really need any of this, so I'll just go ahead and clear out the CTO file and then paste in the contents of the new one. We can now walk through each of these sections one by one, starting with the definition of the namespace. So I'm now going to call this org.lunicorn.trading. So this is the namespace within which all of the resources will be defined. And there is just one asset for our network, which is called commodity. And this is used to reference a batch of a particular product. So this is a generic asset, and this is identified by the field commodity ID, which is of type string. There is also a string description, and the quantity of the product in this particular batch is represented by a double type. Each commodity instance will have an owner, and this is of type trader. trader is another participant resource we will be defining later in this CTO file. In fact, that is the next thing which we define, and each trader is identified by a trader ID, which is a string, as well as a name. So in a blockchain network, we have participants of type trader and then assets of type commodity, and different traders will be able to pass along commodities to one another by invoking a transaction. So this is a transaction representing the sale of a commodity from one instance of a trader to another. And within the full definition of this sell transaction, which will come up in the transaction processing file, we will be transferring the ownership of the commodity from one trader to another. And in this particular definition, we reference the instance of the commodity whose ownership is changing, as well as the instance of the trader who will be the new owner for that particular batch of product. We create an event called sale notification, and this references an instance of a commodity. And this is an event which will be emitted when the sell transaction is invoked. We now define another transaction called remove commodities, and this is invoked in order to remove all commodities, that is, all batches of products which exceed a certain quantity. It is that quantity which is passed as an argument to this transaction. We also create another transaction called remove commodities by owner, and this will remove from the asset registry all of the commodity instances which belong to a specific trader. The ID of the trader, which is something which needs to be passed along to this transaction. And we then define another event for our blockchain application, and this is called remove notification. And this is triggered each time a commodity is removed, whether by removing commodities based on quantity or by its ownership. With that, our CTO file definition is complete, and it is time to create a transaction script, for which we head over to the Add a File button. And when we hit this, we can see the 4 different types of files which can be created within a blockchain network on Composer. In our case, we choose the option to create a new script file. And the file which is created by default is pretty much blank. I'll now clean this up and then paste the code for the new script file, and then walk you through each of the blocks one at a time. And we define a function called sell commodity, which maps to the sell transaction defined within our CTO file. And you can see in the lines just above this function that we are referencing org.lunicorn.trading.sell following the @param sign in the second line. We also use @transaction in order to denote that this is a transaction processing function. So the argument to sell commodity is an instance of the sell transaction, which we reference as TX. And this, you will recall, contains 2 fields. One is an instance of commodity whose ownership is changing, and the other represents an instance of the trader who is the new owner of that commodity. We start off the definition of this transaction processor by setting the value for the new owner of the commodity instance. So tx.commodity.owner will be set to tx.newOwner. And then following that, we retrieve an instance of the asset registry, specifically the registry for org.lunicorn.trading.commodity instances. The returned registry is captured in a variable called asset registry. And then before we update that registry, we will first record an event. So we create an instance of an event called org.lunicorn.trading.sales notification, and we set the commodity for that event to tx.commodity. We then emit this sale notification. And then it is after that where we update the asset registry with the modified commodity instance, which now has a new owner. And with that, the definition of our first transaction processing function for our new blockchain app is complete. In the next video, we will complete the transaction script by defining one more transaction processor, and then we'll also define the query file, and then move on to the ACL file. We are now in the process of defining a blockchain network, which can be used by participants in a supply chain to hand over batches of products to each other. We have previously defined the CTO file, and we defined the sell transaction within our transaction processor. It is now time to define the other transaction processing function, and this is to remove commodities by quantity. So this will iterate over the asset registry and then remove all of the commodity instances which exceed a certain quantity value. Once again, keep track of what we have defined within the comment block just before this function definition, where we specify that this particular transaction processor pertains to the transaction org.lunicorn.trading.removeCommodities, and that this is a transaction processor. So this remove commodities function accepts an argument which is a transaction instance, which we will reference as tx, and this transaction instance contains just one field, and this is a quantity value, where all of the assets which exceed this particular quantity will need to be removed. Within the function definition, we first retrieve an instance of the asset registry for all the commodity instances, and then in order to retrieve all of those commodities which exceed a certain quantity, we invoke a query. So this particular query will be defined just a little later within the query definition file, but do note here how we invoke the query by calling the query function. The arguments to this include the name of the query which needs to be executed, and this is select commodities with high quantity. And then following that, within a JSON structure, we pass along the arguments to that query. The argument is a field called quantity, and the value of that can be accessed from tx.quantity. This will return a list of commodity instances where the batch size exceeds the quantity specified, and we then iterate through that list and then remove from the asset registry each of those commodity instances. So for each instance of commodity which has a high quantity, we first instantiate an event in order to record the removal of this asset. We then instantiate that event with the commodity instance which is being removed and then emit the event. And then following that, we remove that commodity instance from the asset registry. So the second transaction in our blockchain application has now been defined, and it is now time to define the last one. And this is where you can remove commodities based on its ownership. So once we specify that within this comment block, we then start the function definition, and this is called remove commodities by owner. We once again retrieve an instance of the asset registry, and then this results variable is going to be populated with the data returned by another query which we will define in the query processor. So this is a query called select commodities by owner, whose argument is an owner ID. This owner ID will be available within the transaction body, and this will return to us all of the commodity instances owned by a particular trader. We iterate over this list, and then for each commodity instance, we initialize an event of type remove notification. We then populate that event with the correct commodity and then emit the event. And then finally, we remove the commodity instance from the asset registry. And with that, our transaction processor is complete. And on this occasion, we have defined 3 different transaction processor functions. We now move ahead and define the query processor. And once again, we head over to add a file, and we select that this is going to be a new query file. And I'm just going to clear out the contents of this file here and then paste in the new contents. So this is a query file which will contain the 2 different queries which we have called from our transaction processor. The first one is called select commodities by owner, and this is defined using the query keyword. This again has a JSON-like definition. So there is a description and then a statement for the query. This statement is pretty much the same as a SQL statement. So the registry of commodity instances can be accessed as a SQL table. So we select from org.lunicorn.trading.commodity, and within the where clause, we specify that the owner of the commodity instance must be the same as the owner ID, which is the argument to this query. Note how we reference this argument here using the underscore followed by a $sign. This takes us now to the second query, which is called select commodities with high quantity. And once again, there is a SQL-like statement in order to retrieve those commodity instances where the batch quantity exceeds the quantity value which is supplied as argument. So with the query definition file complete, it is now time for us to move on to the ACL file. So I'm going to start off by clearing out the pre-populated contents and then paste in the new rules, starting with one rule which allows a trader to view the details of any asset where that participant is an owner. So this rule applies to any resource within the namespace org.lunicorn.trading which has an owner field. So this is a very generic rule, but the next one is more specific, which allows participants of type org.lunicorn.trading.trader to create records on the historian record. So the historian record is one which records transactions. So this will allow us to view the details of the transaction on the historian record. And the path to the particular resource is org.hyperledger.composer.system.historian record. So here the operation is create and the type of action is allow. In the sample blockchain network which we saw previously, each participant had access to every resource within the Composer system namespace, whereas here we are assigning a more specific permission. The next rule is one which will allow trader instances to invoke sell transactions. So every trader has all permissions on resources of type org.lunicorn.trading.sell. We also specify one more rule to allow trader instances to invoke the remove commodities transaction. The next rule, which is called trader has full access to their assets, we grant them all permissions to commodity instances which they own. Once again, note the syntax within the condition clause in order to establish the ownership of the asset and to match it with the one invoking the transaction. We then move along to the system level rules, and this allows all participants all access to everything within the org.hyperledger.composer.system namespace. Now this includes the historian record for which we have already specified a rule. So if you find this particular system ACL rule too permissive, you can get rid of that and participants will still be able to record transactions. We now move along to the network admin rules and we leave the default rules as they were to allow network admins access to all resources and also to everything in the composer.system namespace. So this concludes the definition of a blockchain network, which can be used to transfer an asset from one participant to another in a supply chain. In the next video, we will deploy this network over to a test environment and then create instances of the different participants and record transactions on the blockchain network. Now that this definition of our asset transfer network has been completed, it is now time to deploy this network to the test environment and then play around with it, for which we head over to the Update Network section. And you can see here that the version of the network is set to change from 0.0.1 to 0.0.2-deploy.0. This particular version number is a bit of a mouthful for me, so I'm going to alter this by clicking the Edit button and then set it to a much simpler 0.0.2. And then we can go ahead and hit the Deploy Changes button. So within a matter of seconds, you'll get the notification that the changes have been deployed, which means that this particular blockchain network is now available for us in the test environment. We can head over to that by hitting the Test button. And you can see on the menu on the left that we can use this in order to create new participants, assets, and transactions. And heading over to the Trader tab, we can see that this particular registry is empty. We can add new instances of traders by clicking on Create New Participant. And within this JSON definition, we can go ahead and enter the details for this trader. So I'll first alter the trader ID and set this to a value of distributor, since this is a string after all. And then after that, we can specify that the name of this distributor is Alice. So I'll go ahead and create this new trader instance, who is a distributor named Alice. We can create another trader instance. So I'll click on Create New Participant once more, and then set the trader ID to a value of wholesaler. So this is going to be another part of the supply chain, and the name of this wholesaler is Bob. So with that, I'll just create new, and then we have two different traders who are part of the supply chain. We can go ahead and create a couple of other participants. So I'll create a third one now, and this is going to be a retailer. And since there will be two retailers which I'm going to create, I'll call this one retailer 1, and this person's name is Joe. So I hit the create button, and we now have three different participants. I'll go ahead and add the second retailer. So this one will be called retailer 2, and the name of this retailer is Ross. So after hitting the create new button, we now have 4 different participants in our supply chain. And we can now go ahead and define the different commodity batches. So heading over to the commodity section, this registry is also empty as of now. And we can go ahead and create a couple of new assets. So head over to create new asset. And then within this JSON definition, I will specify a commodity ID of 01. And then within the description field, we'll say that this is going to represent a batch of headphones, and to be more precise, a batch of 1000 headphones. As for the owner of this particular batch, we can set this to one of the trader instances which we created, and I will assign this to the distributor, which of course is Alice. So hitting create new, we have now created a batch of 1000 headphones which has a commodity ID of 01, and it belongs to the distributor which we created, whose name is Alice. We can now create another asset. So this one will have a commodity ID of 02, and this will represent a batch of bags. Now what kind of bags? Well, that is up to you. And the quantity of bags in this batch will be 500. As for the owner of this batch, we can say that this also belongs to our distributor. So both of the assets which we have defined will belong to the distributor. That is, of course, once we create the second batch. And now it is time for us to transact with this network. But to ensure that all of the permissions which we defined in the ACL file are correct, we won't be running as the admin user, but will instead head over to the admin tab and then over to the ID registry, where we'll create new IDs for each of the other participant instances in our network. So in this particular ID registry page, we can see all of the IDs which have been issued for this particular network, and there is just one for the administrative user. In order to create one for each of the other instances we have created for participants, we click on Issue New ID, and then from this page, we can go ahead and specify the details of this new identity. The first one will be assigned to the distributor in our network, so I'm going to call the name of this ID distributor. And as for the specific participant instance this will apply to, we can specify the full path to this distributor instance. So this is going to be org.lunicorn.trading.trader followed by the # and then distributor. Fortunately, there is an autocomplete which you may have noticed. So with that done, we can hit create, and a new ID card has been added to this wallet, and this identity can be used by the distributor to connect to the network, and they will have the permissions which they have been assigned. We will now issue new IDs. So this one is going to be for the wholesaler. So I'll just search for wholesaler in the participant field, and the autocomplete picks the wholesaler instance. and then hit create new. So we now have another identity here. So within the My ID section, you can see the IDs issued by the current user, and then admin users will be able to see all of the issued IDs. So we'll create identities for the retailers. This is the one for retailer 1, and we can search for retailer 1 in the participant field and then hit create new. We can now confirm that this retailer identity has been created and then head over and create the ID for the second retailer. I'll first close out this notification and then hit issue new ID once more. This one is called retailer 2, and the participant to whom this will apply is the one called retailer 2. So by hitting create new, we have now issued all the 4 identities which we need for this blockchain network. And now to transact as these users, we can head over to the admin tab in the top right, and then we head over to My Business Networks. This navigates us now to the home page of Composer Playground, and from within My Business Networks, we can see that there are different ways for us to log into our deployed blockchain network. There is one button available for each of the new identities which we created. So we can log in as either the distributor, the wholesaler, or either of the 2 retailers, in addition to connecting to our network as an admin. Before we proceed with this demo, let us quickly summarize where we are. We have provisioned a blockchain network which can be used by members in a supply chain to trade assets. In our Composer Playground application, these assets are defined in terms of batches of commodities, and each of these batches has an owner as well as a quantity. We have defined each participant in the supply chain as a trader, and we have created 4 instances of these traders. One is a distributor who currently owns the 2 commodity instances we have produced. There is a wholesaler, and there are 2 different retailers. We have issued identities to each of the participants, and now we can connect to the blockchain network by using the identities for any of them. At this point, let us now go ahead and connect to the blockchain network as a distributor who currently owns the 2 instances of assets which we have generated. So we are now in the Composer homepage for this user, and though we can edit the definition files here if we want to, that is not what we're here for. And we head instead to the test environment where this defined blockchain network has been deployed. Since we are no longer the admin user, we don't see any instances of the trader participants we have created in this view. We head now over to the commodity section and see if any of those are visible. And the answer is yes. Since both of these commodities have been assigned to the distributor, the permissions which we set in the ACL file ensure that a particular trader will be able to see all of the assets which they own, which is exactly the case with this distributor. To confirm whether that logic has been implemented successfully though, we can log in as one of the other participants in our network. So heading over to the top right, we can now switch over to another user by heading to My Business Networks. And then from here, we select the wholesaler. So we are now connected to the blockchain network as the wholesaler, and we can head over to the test environment. Once again, no instances of trader are visible here, but we head over to the commodity section, and even over here, the register appears empty. So the rule defined in our ACL file, which restricts access to commodity instances to only their owners, has been set up just as we planned it to. We can now test out another set of permissions defined in the ACL file. So we can now try to submit a transaction as the wholesaler. Now, by default, it is the remove commodities transaction which has been selected because this is the one which is now available in the dropdown. When we expand the dropdown, all 3 of the transactions defined in our application are available, and the one which we wish to test out is the sell transaction. Now we have defined the rules in our ACL file in such a way that any instance of trader can invoke a sell transaction. However, invoking such a transaction involves changing the details of a batch of commodities, and not everyone has that permission. So it is only the owner of a commodity instance who has the ability to alter its details. Let us now put that to the test. So on this occasion, we will try to invoke a sell transaction, and we will reference a commodity which has the ID 01, and this of course belongs to the distributor and not the wholesaler who we are currently logged in as. We can now try to assign the ownership of this batch of commodities to the wholesaler, and you can consider this as the wholesaler trying to effectively steal a batch of commodities by assigning the ownership to themselves. Will this actually work? Well, we can go ahead and submit this transaction, and we immediately get the notification that this operation is not possible because the wholesaler does not have the required permissions on the commodity. So the rules which we specified in the ACL files have had their desired effect. They make sure that only the owner of a commodity can transfer its ownership. We can now close out of this particular window and then make sure that it's not every trader instance who cannot alter the ownership of the commodity. And we head back to the business network section and connect as the distributor and make sure that they are able to hand over the commodity to someone else. Heading over now to the test environment and then over to the commodity section. Firstly, we can confirm that both the commodities are visible, but we will now try to hand over the ownership of commodity with the ID 1 to someone else, specifically the wholesaler. For that, we head over to submit transaction. And by default, once more, remove commodities has been selected because that is the first by alphabetical order. So I'll just alter this to the sell transaction. And in this editor, we can enter the details. So this is going to be for commodity 01. And the new owner will be the wholesaler instance. So let us now transfer this ownership by scrolling down and hitting submit. And the notification in the top right confirms that the submission of this transaction has been a success. So we have now tested out two of the desired behaviors in our application. Firstly, we have confirmed that someone who does not own an asset is not able to change its ownership. And following that, we verified that the actual owner of the asset is able to hand it over to someone else. Now, in order to view the details of this transaction, we can head over to the transaction section and click all transactions. And then from here, there is a record of all of the transactions which have been submitted in this network. The one we are interested in is the one at the very top, which is the newest transaction. And this is the sell transaction which we just submitted. So we click on view record, and we can firstly see that in the historian record, this transaction has been recorded. In fact, we can also confirm that the event which was emitted as a result of invoking the sell transaction has also been recorded here. So we head over to the events tab. And yes, the details of the event are available here as well. To view all of the data, we will need to expand this view. And the entire JSON object is available for us now. So the distributor was able to add an entry onto the historian record. And we can also confirm that this event emission was a success, which means that we defined it correctly in the transaction processor. Closing out of this window now, we will confirm one more permission again. So we head over to the asset section and take a look at our commodity batches. And the distributor is only able to see one of these commodity batches, since the other one has been handed over to the wholesaler. All right. So a number of our permissions have been set up correctly, and we can continue performing some tests on our application. So we head over to submit transaction, and again, remove commodities is selected. So I'll go ahead and pick sell. And we can now try to sell an asset which this distributor used to own, specifically the one with asset ID 01, which is the batch of headphones. We can now try to sell this off to the wholesaler once more. So you can say that the distributor just forgot about this transaction and tries to perform the sale for the second time. And we'll go ahead and submit the transaction. And this operation is a failure, once again, because the distributor does not have the permission to alter a commodity which they don't own. So we can now go ahead and try to sell off the one batch of commodity which is still with the distributor, which has an ID of 02. And this is the batch of 500 bags. We go ahead and submit this transaction. And this has also gone through successfully. And both the batches of commodities should now belong to the wholesaler. And the distributor does not see any instances of commodity since they don't own anything at the moment. We can continue performing some sanity checks here by heading over to the list of transactions. And at the very top, the most recent sell transaction has also been recorded. We can just confirm this by hitting View Record. And the data is available in the Historian record. And then heading over to the Events tab and then expanding the event details, we can confirm that the event has also been correctly recorded. We can close out of this window and then move on to the next video. So in our blockchain network, we have successfully managed to record 2 transactions selling off 2 batches of commodities from the distributor over to the wholesaler. Just to get a high-level view of where everything is, we can now log in as the admin user. So we head over to this menu on the top right and then over to My Business Networks, and we connect to the network as the admin. Heading over to Test, we can view in the participant section that all of our 4 participants are still here. And then heading over to Commodities, we can observe both of the commodity instances which we created. And when we expand the view, we can confirm that the ownership has indeed been transferred over from the distributor to the wholesaler. We quickly confirm this for the second commodity as well. And this batch of 500 bags also belongs to the wholesaler. We will now continue with our testing by logging in as the wholesaler and then selling it off to the different retailers. So heading over to My Business Networks. And from all the options available, we will log in as the wholesaler. We'll need to head over to the Test tab in order to perform any transactions. But before doing that, we will head over to Commodities, and then we confirm that both the commodities are indeed visible when logged in as the wholesaler. Once we confirm that all the details are exactly as they should be, we will go ahead and submit a transaction, and we will do so in order for the wholesaler to sell off these 2 batches of commodities over to the retailers. So we select the sell transaction from the drop-down, and firstly, we will sell off the batch of commodities with the ID 01, which is the batch of 1000 headphones. And then the new owner for this batch of commodities will be retailer 1. Heading over now to submit the transaction. And this submission was a success. In fact, in the list of assets, we can only view the batch of bags which are still here, which confirms that the batch of headphones have been passed along to a different owner. We can confirm the recording of this transaction by heading over to All Transactions. And at the very top, this sell transaction initiated by the wholesaler is visible. We click on View Record, and the details of this transaction are available for us. Closing out of this view, it is now time for us to go ahead and sell off the one remaining commodity instance, this time to the second retailer. So we confirm that this commodity instance is available, and we can now go ahead and initiate another transaction. So this time we will sell off this batch of 500 bags with the ID 02 over to retailer number 2. This particular transaction also goes through smoothly. And then we can also confirm from this commodity view that there are no commodities visible in the registry for the wholesaler. So it's now time for us to log in as one of the retailers. So heading over to my business networks, I'm now going to connect as retailer 1. And to view all of the assets, we will need to head over to test. And then from here, we head straight over to the list of commodity instances. And the batch of 1000 headphones, which was handed over by the wholesaler, is now available to this retailer. So everything checks out fine so far. This batch of headphones has been handed over from the distributor to the wholesaler to retailer 1. The permissions have been checked out on each occasion, and we have found that all of the rules defined in our ACL are working exactly as we wanted them to. As a final confirmation, we'll need to now log in as retailer 2 and make sure that the batch of 500 bags is visible to that user. So heading over to my business networks and then connecting as retailer 2, we'll need to head over to test once more. And in the list of commodity instances, retailer 2 is able to view the details of this batch of 500 bags. So we have now tested out various permutations with this sell transaction, where each of the wholesaler and the distributor have initiated them, and finally the ownership has successfully passed through to the retailers. What remains to be tested out are the remaining 2 transactions which we defined in our network, and this is to be able to remove certain commodities from the network depending on certain conditions. We can consider that those 2 operations will be invoked by someone who wishes to perform a cleanup of the network, and in our case, this needs to be the admin user. Since we are now logged in as the retailer, we can switch the user, and then heading over to my business networks, we will go ahead and log in as the administrator and then invoke each of the 2 remaining transactions in order to remove commodities either based on quantity or by owner. We will do that, however, in the next video. Since we have defined and then deployed our blockchain network over to a test environment, we have connected to the network as all the different participant instances we have created, and we have been able to confirm a number of the behaviors which we wanted to implement. The permissions in the ACL file have made sure that only the owners of an asset will be able to view those assets in the first place and then also transact with them. And we have invoked multiple instances of the sell transaction. So we know that that works as expected. Now, we will log in as the admin user to the blockchain network and then invoke the remaining 2 transactions defined, which are the remove commodities by quantity and the one to remove commodities by owner. Each of these makes use of queries defined within the query file. So invoking these transactions will test out those queries as well. So we head over now to the test environment. And then from here, we can head over to the commodities view, where both of these commodities are still visible. They now belong to the different retailers in our network. And we can now take a look at each of their quantities in order to test out the remove commodities based on quantities function. So the first batch of commodities has 1000 headphones, whereas the second one represents 500 bags. So let's just say this administrator wants to perform a cleanup and leave this particular asset in the registry, but wants to remove the batch of 1000 headphones. We can head over to submit transaction, and then from the list, the transaction which we want to invoke, which is to remove commodities based on quantity, is the one which has already been selected. In order to delete only the batch of headphones, we can supply a quantity value to this as 700. So the batch of 500 bags will remain, whereas the batch of 1000 headphones will disappear. We'll scroll down and hit submit transaction, and immediately we not only get the confirmation that this transaction has been submitted successfully, but the batch of headphones has disappeared from the commodities view on screen. All right, so this first function works exactly as we expect it to. And in order to confirm that this has indeed gone from the registry itself, we can also ensure that it's not visible for the first retailer who used to own the asset. So we sign out of this as the admin, and then we reconnect to the network as retailer 1, who is the former owner of the asset. Head over to test, and then commodities. And this batch of headphones is not visible to the retailer as well. It's now time to test out the last of our transactions. So we sign out of this network as retailer 1, and we will reconnect as the admin user. Head over to test once more, from where we will invoke the remove commodities by owner function. And then from the default view, where we can view all of the participants, we head over first to commodity. So the batch of 500 bags is still visible here, and this is owned by retailer 2. And in order to get rid of this one, we head over now to submit transaction. From here, we will change the function from remove commodities to remove commodities by owner. And the argument to this needs to be the owner whose assets will be removed from the network. And the batch of 500 bags is of course owned by retailer 2. The owner ID needs to be specified in full. So we give the full path to the resource. So we specify this as resource followed by colon, and then we specify the full path to the retailer 2 instance. And then we go ahead and hit submit. And just as before, the feedback is immediate. Not only do we get this notification of a successful transaction, the registry for the commodity instances is empty. At this point, we may conclude that the testing of our blockchain network definition is complete. We have played out multiple different scenarios where we have connected as different participants, invoked all of the different transactions which we defined, and we are also satisfied that the permissions have been set up correctly. At this point, we may feel confident that this network is ready to move out of the playground and onto the real field. So let's just say we want to export this network and then deploy it into a higher environment. For that, we head over to the Define tab. And then from here, just make sure that you're happy with the deployment version number which you have set. And if you like, you can modify it and then redeploy so that the version number takes effect. But once you're satisfied, one way to export this network definition is to head over to the Export button. This will download the network definition file, and this has been downloaded as trading-network.bna. BNA is short for Business Network Archive. This network file can be imported into a real Hyperledger Fabric network in order to deploy our blockchain network definition. And this covers the use case where we define our blockchain network using Hyperledger Composer Playground. We have used Composer Playground not only as an IDE where we can provision a project, either a blank one or one based out of a template, and then define all of the files which are needed in order to set up a business blockchain network. We were able to deploy that network into a test environment, test it out, and then export it as this business network archive file. And later in this learning path, we will cover how we can define a network outside of Hyperledger Composer Playground and then create a BNA file out of that, which we will load into a real Hyperledger Fabric network. In this exercise, you will first list down the 4 different definition files which we need to create for a Hyperledger Composer blockchain application. When defining a business network using Hyperledger Composer, there are up to 4 different files which you can use in order to define the network, and some of these involve the use of business level abstractions. You will need to recollect what exactly the files are, what their formats are, and what purpose each of them serve. Next, you will connect to the test environment of Hyperledger Composer as an instance of a participant. Once we have defined our network application and then deployed it to the test environment, we can create instances of each participant, but there are certain steps which we need to follow in order to be able to connect to that test environment as one of those instances. You will recollect exactly what those steps are. Each of these topics were covered during this course, so please pause this video and spend a few minutes to perform these tasks on your own. For the first task in the exercise, you needed to list down the 4 different definition files which we will need to create when setting up a business network from Hyperledger Composer. The first of these is a modeling file, and this is written in a proprietary language called CTO. As a result, this has an extension of .cto, and it is within this file where you will define the different resources which make up your business network. These resources include assets, participants, and also at a higher level, what your transactions will look like. While this will include the high-level definition of the transaction, the actual implementation of it will be within the transaction processor script. Now, this is the next definition file, and it is a JavaScript source. So you'll need to write it in JavaScript, and this will include the implementation for each of the transactions which you have defined at a high level in the CTO file. So now that covers 2 of the files which we can create, and moving along to the third one, which is the access control list. This has an extension of .acl, and it is within this file where you'll define the different rules which govern the permissions for each of the participants on the different resources in your network. So for example, if you only want specific participants to be able to invoke transactions involving particular assets, it is within the ACL file where you will define these permissions. The last file which we can define in Hyperledger Composer is optional, and this is the query processor. It is within this file where you will define the different queries which can be executed against your blockchain network, and this file has an extension of .qry. Once all of these definition files have been developed, then you can deploy it over to a test environment within Composer Playground, or alternatively, you can export it to a business network archive or BNA file, and then deploy to a real Fabric network. For the next task in the exercise, you needed to recollect the specific steps involved in order to connect to your business network defined in Composer as an instance of a participant. Once you have defined your blockchain network in Composer Playground, you can deploy it over to a test environment, and then following that, you can use the Playground UI in order to create instances of each participant. Now, in order to test the permissions of your network and to ensure that your participant instances are able to invoke the transactions which they're supposed to, and potentially not be able to view data which they are not meant to have access to, you will need to be able to connect as that participant instance, and for that, you will need to issue identities for each of those participant instances. This can be done when you're connected to Composer Playground as the admin, and for that, you will navigate over to the ID registry, and then from there, you will issue a new ID. At the time of creating this ID, you will need to specify the instance of the participant it belongs to, and once that is done, you will be able to connect to the application using that ID from the Composer Playground UI. So far in this learning path, we have seen how we can define a Hyperledger Fabric network using Hyperledger Composer Playground. Composer Playground is a very convenient tool in order for you to very quickly prototype your business network definitions, then deploy them to a test environment, and then test out different scenarios to ensure that the network definitions have been set up correctly. However, this may not particularly scale since all of the testing is done manually, and you may want to use an IDE which is different from the one provided in Composer Playground. In this demo, we will cover how you can develop your blockchain network definitions for Hyperledger Composer on your own machine, and then export the network definition to a BNA file, which you can then load into a real Hyperledger Fabric network. To start off with, you can head to a directory on your file system which you want to use as a workspace, and then create a new directory for this blockchain network project. In my case, I have a directory called Hyperledger within my home directory, and then I'm now creating a new directory called trading-app, which will serve as the root project directory for us to define our blockchain network. It is within this project directory where we will essentially redefine the same blockchain network which we created previously in Composer Playground. This is one which allows various participants in a supply chain to trade batches of commodities. So once we create this trading app directory, we will now cd into it. And this is the point at which we need to set up the prerequisites to use Hyperledger Composer from our own machines. Now, this is where there may be a bit of a divergence, where I'm going to follow the instructions for macOS. So if you are on any other system, then you should search within the Hyperledger Composer documentation for the prerequisite steps for your own OS. If you are on a Mac, however, you can just follow along with me, where the first thing we will do is to install Node Version Manager, or NVM. This is a tool which makes it very simple to switch between different versions of Node.js on your system. And as of this recording, Composer is not compatible with the latest available versions of Node and needs to run on version 8.x. I'm now downloading NVM version 0.33.0 from GitHub and then executing its installation script. So this will take maybe a minute or two, but once it is done, we can confirm its installation by running nvm --version from the command line. So this is version 0.33.0, which I have. All right. So the next thing we can do is to check the different versions of Node which are on your system. And for that, we can execute nvm ls. And this shows that the current version of Node for me is 8.16.0. Now, if you don't have any version 8 of Node on your system, then you will need to install that. And once you do, in order to switch to that version 8, you can execute the command nvm use followed by the version of Node you wish to switch to. I'm adding the delete prefix flag here, and this is to ensure that you don't run into any issues with your npm config. So when you execute that, then your version 8 of Node will be the active one on your system, and this will also give you the version of npm which is currently in use. In my case, this is version 6.4.1. Hyperledger Composer under the hood will set up a Hyperledger Fabric network. And to do that, it will make use of Docker, where each of the components of the Fabric network will be run as Docker containers. And just to verify your Docker installation, you can run docker --version. And in my case, it's version 18.09.2 which is installed. The other tool of Docker which will be required is Docker Compose. And in my case, it's version 1.23.2 of Docker Compose. Once again, Docker Compose is required in order to set up a multi-container Docker application. And this is precisely what the underlying Fabric network will be. So it's version 1.23.2 of Docker Compose for me. Moving along now, we will now need to set up a Composer CLI. Since we won't be working directly with Hyperledger Fabric, we will be using the abstractions available in Composer. So we can go ahead and install the Composer CLI using npm or Node Package Manager. So the command here is npm install -g composer-cli. And I'm installing Composer CLI version 0.20 here. Once that is done, the other tool we can install is Composer REST Server. As the name implies, this will set up a REST server which will allow us to interact with our blockchain network using a REST API. A number of the tasks which we previously did using Composer Playground can be done with the REST API, and this can be used in order to set up your own application which will be able to interact with the underlying blockchain network. So to install this, we run npm install-g composer-rest-server. And once again, I'm specifically installing version 0.20. With the REST server installed, there is one more tool we will use, and this is called Generator Hyperledger Composer. This is one which will generate a Hyperledger Composer business network definition out of a Composer project. So this is once again version 0.20 which is installed. And once this is done, we will now install a tool called Yeoman, or Yo for short. And you can think of this as effectively some kind of framework for web applications. So this will provide all of the scaffolding which you require in order to set up a web app, so that you can mainly focus on your own application rather than worry about implementing a web app. So we use npm to set this up once more. And once Yo has been installed, we can also set up Composer Playground on our own machines. So previously we were using the cloud version of Playground, and in order to run it from our own hosts, we can use npm once more, and we install Composer-Playground version 0.20. Once Composer Playground has been set up, we will now download a set of tools which will ease the task of setting up a Fabric network. And this is available in the GitHub repo Fabric Dev Servers. This repo includes a number of different helper scripts to set up the Fabric network. And then these scripts will also make it easier for us to deploy networks defined using Hyperledger Composer. So we use curl to download this tar.gzip archive. We can then run ls just to confirm that it has been downloaded. And following that, we will unpack this archive by running tar with the -xvf options. So all of the files in Fabric Dev Servers will be extracted. And with that, all of the prerequisites for setting up a Hyperledger Composer dev environment on our own machines has been completed. Starting from the next video, we will take a look at all of the helper scripts which we have downloaded. And following that, we will redefine the same business network which we used previously from Composer Playground. In the previous video, we installed all of the prerequisites in order to define a blockchain business network using Hyperledger Composer from our own machines. I have now brought up my project workspace in a text editor, and while I'm using Sublime Text, you can use any other text editor or IDE which you're comfortable with. Now the specific project directory which I had created was trading-app, so I'll go ahead and expand its contents. And now this includes a number of different scripts and also a fabric-scripts directory. Let us take a quick look at some of these scripts. If you go into create composer profile.sh, for example, we can see from the code that this has been deprecated because it asks us to use the create peer admin card.sh script. The reason I bring this up is that Hyperledger Composer is constantly under development, and you will need to be mindful of any big changes which have occurred between this recording and the time you're viewing this video. In any case, we can now zero in on the fact that this particular script calls the _loader.sh script. And in fact, if we head over to the create peer admin card script, we can see that the loader is referenced here as well. In fact, this is also the case with download fabric.sh. So again, just be mindful of the fact that some of the scripts which have been downloaded may be deprecated. We will take a look at the loader script just a little later. But for now, we can proceed with the other files which have been downloaded here, starting with the package.json, where you can see all of the details of this node app. We can just go ahead and close this and move along to this start fabric.sh script. Once again, this references loader.sh, as does stop fabric. There are also scripts over here to help you clean up your environment. For example, there is one called tear down all Docker, which will clean up all of the Docker and resources provisioned. And then the final script in this list here, to tear down Fabric, also references this loader script. So let us now take a look at what exactly it contains which is so crucial. So within the loader script, you can see that there are a lot of different configurations which are being set up. A number of different environment variables are being set. And in my case, a default version of Fabric which is being set up is version 1.2, which is set up in the fabric_version environment variable. In fact, right at the very end, there is a specific script which is being called in order to provision a Fabric network using that version. Let us take a look now at this Fabric scripts directory. So within this, I'm just going to expand one of the directories to view its contents. So you can see for version 1 of Fabric, there are a few scripts, and the Composer directory only contains a text file. We move into the version 1.1 directory, and this has a similar structure, but there is more support for Composer here, which is evident when you expand the directory and you see all of the config files in order to set up a network. Moving now to version 1.2, once again this has the same set of scripts, and the Composer directory also includes all of the configurations which you need to set up the network. Let us take a look at some of these scripts here. So this create composer profile.sh has been deprecated, and one of the scripts which we will be executing a little later is this create peer admin card.sh script. As the name implies, this will create an identity for the administrator in order to connect to the underlying blockchain network. If we navigate through this file, we can get an idea of what all it does, including the fact that this includes a connection profile definition. So this is one to set up a Hyperledger Fabric network with a single org containing a single peer and a certificate authority. And while this will help you provision a network very quickly in a dev environment, you may want to modify its configurations in order to suit your own requirements. For example, you may need to modify the host and port definitions right here for the orderers, peers, CAs, and so on. This is set to use the downloaded certificates and keys, and if you generated your own cryptographic material, you will need to modify all of these values as well. And finally, you can also configure the name of the peer admin card which is created in this location. You can view the command over here which uses the Composer CLI in order to create this peer admin card. And if you already have a pre-existing card which you would like to use, then you can set the no import environment variable. So this is just to give you an idea of how we can use an admin identity in order to connect to a network defined using Composer. So these scripts are specific to Hyperledger Composer, but it's clear that it uses Hyperledger Fabric under the hood. Now I won't get into the details of all of these scripts, but if you expand the Composer directory, all of the details of the Fabric network which have been provisioned underneath are visible. This includes the configstx.yaml file, and if you would like to set up a Fabric network with a different configuration, then you can go ahead and modify, say, the profile section, and also all of the organizations which are defined within this file. The setting up of a configstx.yaml file was covered earlier on in this learning path, so I won't get into the details. There is also the cryptoconfig.yaml file which you can use, and this is the one which will decide the cryptographic materials which are generated. And in addition to these, we also have a couple of Docker Compose YAML files. So there is one which you can use in order to define your dev environment. And there is a separate one called just Docker Compose.yaml, which you can use for a higher environment and potentially even your production setting. So now that we have taken a look at the downloaded scripts and config files, we can use them in order to set up a Hyperledger Fabric network. So I've gone back to my shell. I'll begin running the scripts in order to set up the network. But first, we can set up an environment variable in order to ensure that it is version 1.2 of Fabric which is used. So the Fabric_version variable is set to HLF v12. And if a newer version of Fabric is available within Fabric dev servers by the time you view this video, feel free to use that. So once this has been set, we run the download fabric.sh script, And this will download all of the Docker images which are required in order to set up the Fabric network. Since I already have all of these, this runs very quickly, but it may take you a while depending on how many images you already have. So once this is done, the next script to execute is startfabric.sh. So this will start up your Fabric network using all of the downloaded images. And you can see that this has issued a number of identities and so on. But just to confirm that each of the components of your network are up and running, you can execute the Docker command, docker ps. So this will list all of the Docker processes, and the output confirms that the 4 different containers representing a Fabric network, which includes an ordering service, a peer node, a certificate authority, as well as a CouchDB instance, have all been set up and are running. And now it is time for us to execute the create peer admin card script. So this will create the identity which we can use in order to connect to our network using Composer. And in the next video, we will take a look at how we can use this admin card in order to instantiate a business blockchain network defined using all of the high-level abstractions of Hyperledger Composer. Now that our Fabric network is up and running, we will need to create a project where we can define our blockchain network using the Composer abstractions. In order to generate such a project, we will be making use of the Yeoman tool, which is accessible using the Yo binary in our command line now. And to do this, we run Yo followed by a generator which will be used in order to set up a project. The specific generator in our case is going to be Hyperledger-Composer followed by a colon and then business network. This will provision a structured project within which we can include all of our business network definition files and then later use that in order to export a business network archive or BNA file. So when we run this command, we will be asked to enter a few details of the Hyperledger Composer network which we wish to define. So the name of this business network I'm going to set to trading-network. We can set a description, specify the name and email of the author, the license to attach to this network, and also a namespace which we will create. And this is a namespace we will reference in the CTO file. You can see from the output here that a number of different files have been created. There is a package.json, but there are also the Composer definition files, including a CTO file, an ACL file, and the transaction processor is going to be in the lib/logic.js file. So this has laid out the structure for our project, and we just need to go ahead and modify it. Just to confirm what has been generated, we can run ls, and the detail to note in the output is the trading-network directory which has been created. And we can now in fact cd into that directory and run ls once more to view the contents. So the Yeoman generator has created all of these files and directories. We can now bring up this directory in our text editor or IDE. So I'm now going to close up any files which I had previously and then navigate over into this trading-network directory. Expanding its contents, you can see the different files and directories from this view. We can explore the contents one by one. There is a directory called features, and then within the support subdirectory, there is an index.js file, since this can be used as a web app. We will not be touching any of these files in our demo, and will instead head over to the models directory, which includes a CTO file. The contents include definition for all of the sample resources, but I'm just going to go ahead and clear out all of this and then paste the contents of our own CTO file, which we have used previously. So this includes definition for the trader participants, the commodity assets, and also transactions to sell and to remove the commodities. Moving over now to the lib directory, and this is one which includes a logic.js source file, which functions as the transaction processor. So I'll clear out the contents in this one as well, and then paste in our own transaction processor. This, of course, includes definitions for the 3 different transactions which we have. And do note here that these comments are important, which define the fact that this is a transaction processor, and also map this transaction processor to the specific transaction defined within the CTO file. So this sell commodity function maps to the sell transaction. And then, of course, we have the other transaction processors defined here to remove commodities based on quantity and to remove commodities based on their owners. There is also a test directory, and this is where you can define all of the tests for your application. Now, when we previously deployed our network to Composer Playground, we were able to run tests in the test environment, but we had to do that manually. That is clearly not a scalable solution. And within this test directory, there is this logic.js file where you can make use of the Chai framework and define all of the tests which need to be run against your network. The actual tests themselves are beyond the scope for this course, but once you begin using Composer on a regular basis, you can begin defining all of your tests here rather than running them manually from Composer Playground. We move along now to one of the other files which we will modify, which is the permissions.acl file. So again, this includes some predefined code, which I'm going to clear out, and then paste in our own set of rules, which we defined in our own permissions ACL file. So once all of our rules are in place, we had one more file to create, and this is the query processor. So this has not been included by default as part of the standard network definition. So we will need to create a brand new file within the root directory of this trading network project. And then I'll go ahead and paste the contents of our query processor, which of course includes the 2 queries in order to select commodities based on quantity and another one to select commodities based on owner. So I'll just go ahead and save this within the trading network directory as queries.qry. And with that complete, all of the 4 network definition files have been set up. It is now time for us to use this network definition and install it on the Fabric network, which we have set up previously. To do that, we head back to the shell. And the first thing we will do is to create a business network archive file. And this is the BNA file, which we previously created from the Composer Playground UI. The command to run to do this is composer archive create. We use the -t flag to specify that the sources for this network are within a directory. And the -n flag followed by the dot specify that the source directory is the current directory. And executing this command does create the BNA file. So this is version 0.0.1, which has been set automatically. So we now have a network definition which creates an application to enable the trading of assets on a blockchain network. This is where we left off our demo on Composer Playground, and we can now explore how we can use this network definition and deploy it to a real Fabric network. First, we can do an ls to see what has been generated, and this trading network BNA file is the one which includes all of the network definitions. So we can now go ahead and use that BNA file to deploy our business network definition to the Hyperledger Fabric network, which has been set up. We will need to make use of the peer admin card which we created previously, and this is specified as the card parameter, and the archive file argument needs to point to the BNA file which was just generated. And when we execute this, our business network has been installed to Hyperledger Fabric. It is not quite ready to use yet though, because we will now need to start up the business network. The command to execute for that is composer network start, and there are a number of different arguments which we need to specify. This includes the name of the network which needs to be started up, which is trading network. We also specify the version of the network which needs to be deployed, and this should match the one for a BNA file, so it's going to be 0.0.1. The credentials for the network administrator include the name, which is admin, and the password, which we set to admin pw. Once again, we need to make use of the peer admin card, which we had previously created. And then we can also specify the location of the network admin card file. This is the identity which will be created by running this network start command. And when we run this, the network has been started up and the network admin card has been created. In order to use that network card from Composer, we will need to import it first. So we run Composer card import, and then this network admin card will be available within Composer in order for us to connect to the network as an administrator. And in fact, we can establish that connection right away just to ensure that the Composer network is indeed up and running. So this is our business network. So we run Composer network ping using the network admin identity. And this is a successful operation confirming that our blockchain network is now running. So far, we have covered how we can generate a blockchain network definition using Hyperledger Composer Playground from our own dev environment on our local machines, rather than having to use Composer Playground. We then install that network definition onto a Fabric network, and it is now possible for us to connect to that network and then interact with it. How exactly can we do it though? Well, there are a couple of options for us to connect to the network, and we will now explore one of them by making use of the Composer REST server. So this will set up a REST API server, which will enable us to perform a lot of the tasks which we did using the Composer Playground UI, but by using REST API calls. So we have previously installed the Composer REST server, and now we can bring it up and then connect to our deployed blockchain network. In order to bring it up, we only need to run composer-rest-server from our command line. And then we will be prompted to enter the details of the network which we wish to connect to. We firstly need to specify the identity we will be using to connect to the network, and this is in the form of a business network card. And we will make use of the card which was just generated previously for the admin for our trading network. And its name is admin@trading-network. We just need to specify the name because this will be retrieved from the Composer wallet. There are a number of other details which need to be entered, such as whether we want to enable an API key or we wish to enable authentication using the passport tool. But I'm just going to hit enter on all of this so that the default values are used. So once all of these configurations have been defined, the REST API server will start up. And by default, this will come up on port 3000 of your local host. All right, so I'm just going to copy this URL and then paste it into the browser. And when we navigate to this page, we can see the Composer REST server come up, and this API has been built up using Swagger. And once the page has been loaded, you will be able to view all of the different operations which are available for us to interact with the deployed Fabric network. For example, we can expand this commodity section, and this will show the different operations related to our commodity instances. The first GET request will allow us to retrieve all of the commodity instances we have defined. There is also a POST request which can be made in order to add commodity instances. And a few of these we will explore just a little later. Heading over now to the next group of operations for queries. And this is where we have the two queries which can be invoked using a GET request. Now there are three transactions we have defined, and there is one section here for each of them. So for remove commodities, there are three different operations which are possible. Now these have been generated automatically, and we don't really need all of them here. Similarly, for remove commodities by owner, we can invoke this either by using query parameters in a GET request or by including the parameters in the body of the request using a POST request. And heading over now to all of the API calls related to our participant, which is the trader, we have the array of operations in order to create and also to view, modify, and delete trader instances. So it is now clear that we can use all of these operations in order to create instances of all of our resources and to also invoke transactions. The idea of this REST API server is that you can now build an application with your own user interface and then make REST API calls to the blockchain network in order to interact with it. One thing to keep in mind, though, is that we have brought up this REST API server using the admin identity, so we will be connecting to it as an admin user. To connect to the network using a different set of permissions, you will need to create a separate admin card and potentially run the REST API server in multi-user mode. That is beyond the scope of this course, so we will now continue interacting with our network using this REST API UI. So the first thing we will do is to create instances of our trader. So we expand this trader view, and then we will submit a post request, which will include the details of the trader we want to create. So here we have examples of how we can submit JSON data to create a new trader. And you will observe that this JSON structure is similar to what we submitted from the Composer Playground UI each time we submitted a transaction. So in order to make a post request to create a new trader instance, I'm now going to expand this example value, which is also available here, and then copy its contents over to this data text field. Here I'll specify the ID of the trader which needs to be created, and this is going to be a distributor. And then we set the name for this distributor, just as we did before, to Alice. And with that, we can just go ahead and hit try it out. And this JSON request has been sent, and the new trader instance has been created. If you would like to make such a request from the command line, then the curl command which you can execute to do that is available here. Also, the request URL will tell you where you can submit your post request, and the response sent by the REST API server is also available here. The response code will tell you whether the operation was a success, and it was, given that we get a value of 200 here. And now that we have successfully created our first participant in this business network, we will go ahead and create another one. So this one will have a trader ID of wholesaler, and the name of this wholesaler is Bob. So we'll just go ahead and submit this request as well. And this operation is also a success, which is confirmed by the 200 response code. All right, so we now have two participants. We can now minimize this particular view where the API calls effectively function as setters for our blockchain application. And then we will invoke a getter, and this is the one to retrieve the details of all of the trader instances. So you can see the details of the request which is created here. But in our case, all we wish to do is to retrieve all of the traders. So we can just hit the try route button without specifying any arguments. We firstly see the details of the request being made. And then following that, in the response body, we get the details of the two trader instances. All right, so we now have confirmation that these two traders were indeed created. So we can now minimize this particular view, which included the call which we can make in order to retrieve the details of all trader instances. And then we head over to the other GET request here, which is to retrieve the details of a specific trader instance. So here we can just head over to this ID field, which is a required one, and specify the ID of the trader whose details we wish to retrieve, which is going to be distributor. And then we make the REST API GET call, and the details have been returned within the response body. So all of these API methods have been generated automatically for us. All we need to do is invoke them either from the command line or from our own application. I will now go ahead and minimize this particular section, and we can continue interacting with our network using this REST API interface. So far, we have made use of POST requests in order to create new instances of traders in our application. And then we made use of GET requests in order to retrieve the details of those trader instances. We will now invoke another type of REST API call, and this is a head request. A head request is typically similar to a GET request, with the main difference being the fact that there will be no body in the response of a head request. Such requests are often used in order to check for the existence of a particular resource. So if you'd like to check whether a particular trader instance exists with a given ID, then we can make use of such a head request. So let us do that by passing along the ID of the distributor to check whether a distributor exists in our blockchain network. And when we try this out, this returns to us a response code of 200 with no response body, which confirms that this trader who is a distributor exists. From GET, POST, and HEAD requests, we will now take a look at a PUT request which we can make for a trader instance. So in this case, we can make this request in order to update the details for a particular trader. So this is usually the case for a PUT request. So the body will include the JSON of the trader instance which we wish to update. And we will scroll a little further down to make use of the form available in order to update the details for a trader. In this ID field, we need to specify the specific instance which we want to update. And we will now make an update to the wholesaler. And in the data body, we will specify that this is the trader ID of wholesaler. And what we are updating is the name. It is now currently set to Bob, and we will be changing it to Smith. With that, we make this request. And this also seems to have gone through successfully. And to confirm that this trader update has indeed taken place, we will make another GET request. So we will get the details of a specific trader instance. So this is going to be the wholesaler, which we just updated. And once we make the request, we can see that the name for this wholesaler has indeed been updated to Smith. So there are a wide range of API calls which we can make to this deployed blockchain network. And while we can do that from our own application, we will make use of the web browser directly in order to make one such request. So in order to retrieve the details of all of the trader instances in our network, we just need to copy over this link. And then heading over to a new tab in the browser, I'll just paste this in the address bar and hit enter. And the details of the two trader instances, the distributor and the wholesaler, are available. And once again, we can confirm that the name of the distributor is Alice and the updated name of the wholesaler is Smith. So just to confirm that we can retrieve the details of Alice, who is the distributor, we can just modify the URL in our address bar currently. So here we add the distributor extension, and the details of our distributor, which is Alice, have now been retrieved. So we can now close out of this tab and then continue interacting with our blockchain network from this REST API. And now we will make use of the delete request which is available in order to delete a specific instance of a trader. So we can now try to delete the distributor from our network. And then when we hit the button, we can see that this has returned a code of 204, which implies a successful operation. But just to confirm that this distributor is no longer available in the network, we can copy over this URL. And now I'm going to open up a new tab once more and paste this in the address bar. And when we head over to this location, we can see that this distributor no longer exists. And we can confirm this fact by retrieving the details of all of our trader instances using this URL. And this only returns the details of the wholesaler named Smith. So Alice, the distributor, is no longer part of our blockchain network. Since the purpose of our business blockchain network is to invoke transactions involving the trading of assets from one participant to another, it doesn't really make sense to have just one participant right now. So we can fix that by heading back to our UI. And then we will make another post request to create a second trader instance. So from this view, we will go ahead and submit a new request with a new JSON body. So this is going to be another distributor. And the name of this new distributor is Henry. So I'll go ahead and make this post request as well. And now we're back to having two participants in our blockchain network. Now, in order to invoke transactions, we not only need two traders, but we also need assets which can be traded. So let us now minimize out of this view and then create some new instances of our commodity assets. So in order to create these commodity instances, we will need to make use of a post request. And then in this view, we will once again have to submit a JSON request body, which looks something like this. And we will do just that in this data field below. So we are creating a batch of 10,000 headphones this time. And the owner of this batch will be the distributor. So we go ahead and make this post request. And our first batch of commodities have been created. So we'll go ahead and create another batch. So this is going to be for a batch of bags, just as we had before. And the quantity of bags will be 500. Heading back down, I'm going to hit the try it out button once more. And now we have two batches of commodity instances. This one for a collection of bags. This time, we will also add a third batch of assets. So this is going to be a batch of cameras. And the number of cameras in this batch is 100. So all three of these commodity instances will belong to the distributor. So we hit the try it out button. And we now have three different batches of assets to trade. Now that we have made post requests to add new assets, we will retrieve all of those assets using a GET request. So once we minimize this view, we head over to this particular GET request. And we can head straight for the try it out button, since we don't really need to pass in any parameters. And scrolling down will give us all of the three commodity instances which we have created. So the batches for headphones, bags, and cameras are all visible here. The other GET request which we will now check out is the one to retrieve details of a specific commodity instance. So we'll head over to this GET request now. And then we will retrieve the details of the headphones. And when we hit the try it out button, we get the confirmation that this particular GET request is also successful. So this particular REST API server makes it very convenient for us to interact with the blockchain network. The last test which we need to perform is to record transactions, and that is precisely what we will do in the next video. So far, we have provisioned two instances of traders in our supply chain blockchain network. And we have also created three instances of batches of commodities. Since then, I have gone ahead and deleted one of those batches, specifically the batch of 500 handbags, and then have modified the quantities in the batch of cameras from 100 to 90. You can go ahead and make those same changes, or you can just come along with me, because we are now going to invoke some of the other REST API operations which this REST API server provides. Specifically, we are now going to invoke the queries which we have defined. So if we expand this query view, the first thing we will do is to select commodities by owner. We need to supply an argument to this query, which is the specific owner whose commodities we wish to retrieve. So here, we specify in the owner ID field the distributor who currently owns all of the commodities which we have provisioned. And when we hit try it out, we can see all of those commodities listed here. So in my case, as I mentioned, I deleted the batch of bags, which is why the camera and the headphone batches are visible. So the first of our queries has now been tested out, and we can minimize this and then head over to the second queries, which will return all commodities which exceed a specified quantity. The argument to this is a double value, which will be the quantity in the batch which we wish to set as a threshold. So first, let us try by specifying a value of 0. So this should return all of the commodity instances we have created. And that is precisely what it does. We can now make one more call so that exactly one of these batches of commodities is returned. So in my case, I'll specify a new threshold value of 100 and then make this API call for the second time. And this time, it is just the batches of headphones which is returned. Okay, so we're now satisfied that both of our queries work as expected. So now that we have tested out the creation of commodity instances and trader instances and the queries, it is time to invoke a transaction. So we expand this cell view here. And then from the three different options which are available to us, we really just need one of them. Specifically, we can make a post request. And then from here, we will need to specify a body which looks something like this. So I'm now just going to copy this content and then paste it in the data field. And just as we did previously from Composer Playground, we will need to populate all of the fields here. Since the full string specifications for the fields can get a little long, I'm now going to expand this view. And then following that, we'll paste the entire JSON data structure containing the transaction information. So in our case, we wish to transfer the headphones from the distributor who currently owns it over to the wholesaler. So with all of the details specified, we hit try it out. And this transaction seems to have gone through successfully. So we can see the curl request body in case we wish to use curl to invoke such a request. And the response body confirms that this commodity has been transferred over to a new owner. And we also have a transaction ID here. In fact, if you wish to retrieve the details for a specific transaction, we can just copy over this transaction ID. And then minimizing this post request view, we make a GET request, specifically the second GET request, which includes an ID as a query parameter. So here we head over to the ID field, and what we need to supply is the transaction ID, which we just copied over. So once that has been pasted, we just hit try it out. And all of the details of that transaction, which we just invoked, are visible here. So we can see that it was the commodity, which is the batch of headphones, which was involved in the transaction, and that the new owner of that batch of headphones is the wholesaler. All right, so we can minimize this now. And now that we're satisfied that the cell transaction works correctly from this REST API interface, we can invoke the remove commodities operation. So clicking on this, we can make a post request. And remember that this is a transaction which will remove all commodity instances where the batch size exceeds a specified threshold value. That threshold quantity will need to be included in the JSON request body. So I'm just going to paste this and then update the quantity field, which is by default 0, to 100. So the batch of cameras, which is currently set to 90 for me, should not get deleted, whereas the batch of headphones should be removed from the asset registry. So when we run this, it looks like this was a successful invocation. The details don't really make it clear whether the batch of headphones disappeared, however. And to get that information, we can get out of this particular view and then head over to the commodity section. From here, if we invoke first of these GET calls, which will retrieve all of the commodity instances we currently have in our network, we'll just go ahead and then make this call, and the return data confirms that the batch of headphones has disappeared and all that is left is this batch of 90 cameras. Alright, so the remove commodities by quantity function clearly works. And there is just one last operation which we need to check out, and this is the one where we can remove commodities based on its ownership. So when we expand this, and then we will make the post request for this once more. And just like with the remove commodities transaction, here within the JSON object which is supplied in the post request body, we will specify the name of the owner whose commodities need to be deleted. So I'll just expand this particular view, and then following that, just truncate this JSON to reduce it to the fields which we really need. And then for the owner ID, I'll specify the full path so that all commodities belonging to the distributor will disappear. So when we invoke this, looks like this invocation was also a success. And just like we did before, you can retrieve the details of all of the commodities to confirm that nothing is returned and that we are now at a clean slate, at least in terms of instances of our assets. What we still do have in our network, however, are two instances of participants. Specifically, we have one distributor and one wholesaler. In the next video, we will take a look at how we can build a front-end application which will be able to make these REST API calls in order to interact with our deployed business blockchain network. So far in this course, we have covered a number of different REST API calls which can be made in order to interact with our deployed business blockchain network, which was defined using Hyperledger Composer abstractions. Now, the whole point of a REST API server is for us to be able to make those API calls from an application, and we will now see how we can build such an application. Previously in the learning path, I have emphasized that one of the primary goals of the Hyperledger project was to simplify the adoption of blockchain technology. You have seen that this REST API server does go a long way towards making it easy for us to interact with the blockchain network, since a number of these REST API calls are already available for us. All we need to do is to call them when needed. Now, to make things even more convenient for us, Hyperledger does not expect us to build a web application from scratch, but provides us with a template web application which we can build upon. To see exactly how this works, I'm now going to bring up a new tab in my terminal. Since this app will be using the REST API server, do leave it running. So in this new tab, we can now set up this application. And for that, I'm first going to head up one directory level so that we are in the trading-app directory. And then we'll make sure that node version 8.16.0 is being used. So this is the one which I am using. You may have a different version of node 8.x. Once the node version has been set, it is now time to set up this new application. And for this, we will be making use of the Yeoman tool once more. Now, the specific generator which we will use in order to create this app is Hyperledger-Composer :Angular. So this is going to be an AngularJS web application, and we will see exactly what it looks like. You will be prompted for a lot of information, starting with the name of your project. So I'm going to call this trading-app. I will use default values for a lot of these, but you will need to specify details such as the name of the business network card, and very importantly, the location of your REST API server, because that is what your application will be using. So in my case, this is running on localhost at port 3000, which I have specified. So now that the setup is complete, I'll just let the installation go on. And there is this confirmation now that this application has been generated. So what does this look like? Well, first of all, I'll just run an ls, and in the output, the trading-app directory has been created. So we can cd into that and run ls once more, and the output here confirms that this is a full-fledged web application which includes a Docker file. Now, to get a better idea of what this web app looks like, I'm now going to bring it up in my text editor. So when we expand this trading app directory, we can see that this includes 3 different subdirectories. When we expand node modules, we can view that there are a lot of dependencies for this app. And then moving along to the source directory, we can see that there is a nice structure. So within the app directory, for example, you will find each of the different components which make up our application. So there is a subdirectory here for each of the resources which we defined in the CTO file, which includes the commodity as well as the trader and the 3 different transactions. So if we expand this trader subdirectory, within that, we can see that there is an HTML file, a CSS file, and also a handful of TypeScript files. We can view this definition for the HTML page for the trader. Now, getting into the details of Angular is beyond the scope of this course, but when we bring up the application in just a little bit, you will see exactly what this page looks like. Now, heading out of this trader directory, when we get into asset, we can view assets such as the different images which will be used in this web application. So this gives you an idea of how exactly this app is structured. All of the resources related to commodity can be found within this commodity directory, and the home page of the application is defined within this home directory. Now, getting out of this app directory, we can also view the environments directory, which includes definitions for different environments to which you could deploy this application. So the purpose of this Angular app is so that you don't have to start from scratch when setting up an application to interact with your deployed Composer network. In the next video, we will run the app and then interact with our blockchain network once again by creating assets and invoking transactions, but from our own web application. Now that we have downloaded and set up our application to communicate with our deployed network, which was defined using Composer abstractions, it is now time for us to start up the application and see exactly what it looks like. We are now within the home directory of this web application, which includes the package.json file. And now I'm just going to clear the terminal window. And then to start up our application, we need to execute npm start. So this will bring up the web app. And this might take a couple of minutes to come up. But once everything has been loaded, we just need to bring up a new tab in our browser. And this app will run on port 4200 of your local host. And once we navigate to that, we land at the home page of our application. So you can see here that this does not include much. So it is a bare bones application, but we have different tabs for assets, participants, and transactions. Heading over now to the participant section, the 2 participant instances which we created previously for the wholesaler and the distributor are still visible here. You will notice that in this particular instance, this is similar to the application on Composer Playground in the test environment, where we could view the assets, participants, and then invoke transactions as well. In fact, this is pretty much exactly the same, except that this application can be modified by us. So now we can head over to the Assets tab, and there are no instances of our commodities defined here. And to create new instances of the commodities, we just need to click Create Asset. Now, as opposed to Composer Playground, we don't have to specify a JSON data structure containing all of the details, and this interface really ensures that we only need to specify exactly the details which we require. So we specify the commodity ID as headphones, we supply a description and a quantity, and as for the owner, we just set it to a value of distributor. So we only specify the ID of the trader instance who owns this asset, rather than specifying the full path to the distributor. So we just hit confirm, and this commodity instance has been created. And under the owner column, you can see that the full path has been generated automatically by the app. So this is another convenience of this Angular app. So we can make use of that once more to create another asset. This time our commodity is going to be a batch of laptops, and the quantity is going to be 50. As for the owner of this batch, this will belong to the distributor as well. So when we create this asset, all of the details have been populated for the owner once more, and we are left with two different assets to trade. And both of these belong to the distributor. Now, in order to invoke the trade transactions, we will head over to the Transactions tab. And here we have the option to select from the three different transactions. We will invoke a sell operation, and there is a summary of the sell operation now, and then we have the option to invoke this transaction. When we do that, we need to specify the two parameters for this. And though both of these parameters reference different types in our application, we only need to supply their respective identifiers. So this is going to be a batch of laptops, and the new owner will be the wholesaler. So when we invoke this transaction, it looks like it has gone through since we don't see an error message. But to confirm that the ownership has changed for the asset, we head over to the asset menu, and then from the commodities, this view confirms that the laptop has changed ownership and it now belongs to the wholesaler. Alright, we can now invoke one more transaction, and this time we will check out the remove commodities one. So once again, we will click invoke, and the quantity which we will specify as the threshold is 100. This means that our batch of headphones will be deleted, which we can confirm by heading over to assets and hit commodity. And the only assets we are left with is the batch of laptops. So 2 out of the 3 transactions which we have defined work. And before we invoke the third transaction, let us confirm the ownership of this asset, since we will need to specify the wholesaler when we invoke the remove commodities by owner transaction. So heading once more to transactions and then selecting the remove commodities by owner. When we hit invoke, this time when we supply the argument, we will specify the full link to the resource which represents the wholesaler, and then hit confirm. Again, the transaction seems to have gone through smoothly, and when we head over to assets and commodity, all of our assets have disappeared, and we have now successfully tested out all 3 of the transactions in our network. So just to recap what we have covered in this course, we first defined a blockchain network using Hyperledger Composer abstractions, and we did this on our own local machine, for which we made use of the Yeoman generator. We saw how we can make use of the Composer REST API server in order to interact with our deployed blockchain network. And finally, we took a look at this boilerplate Angular application, which makes use of the REST API server and provides a very nice user interface for us to work with our blockchain network. In this exercise, you will summarize all of the steps involved in order to deploy a Hyperledger Composer application to a Fabric network. During this course, we defined a blockchain application using Hyperledger Composer abstractions, and after we set up a Hyperledger Fabric network, we deployed the blockchain application over to it. This particular deployment was not a one-step process, however, and you will need to recollect exactly what was involved. Next, you will describe the boilerplate web application which is available for Hyperledger Composer. One of the goals of the Hyperledger project is to make it very simple for anybody to adopt blockchain technology in order to record their transactions. Setting up a blockchain network application is made easier by the availability of Hyperledger Composer, where we can make use of business-level abstractions to define our network application. And in order to ease the setting up of a web application to interact with the network, Hyperledger has also provided a standard application with a web UI. You will need to describe the properties of this web app. These topics were covered during this course, so please pause this video and take some time to perform these tasks on your own. For the first task in the exercise, you needed to recollect the exact steps involved in order to deploy a Composer application to Fabric. So let us start from the very beginning. Step number 1 is to make use of Hyperledger Composer abstractions to define the network. And during the course, we covered that one very useful way to do this is to make use of the Yeoman tool. And here you will need to make use of the generator Hyperledger-Composer business network. This will set up a project with a predefined structure, and this will include some of the network definition files for a Composer application. That is, there will be a CTO file, a transaction processing script, an ACL file, and optionally a query file. Once the network definitions are in place, we can export the entire network which we have defined to a business network archive file, and this has the extension .bna. We can make use of the Composer binary to create this file, and the specific command to run for this is composer archive create. Once we have this network archive file, we will need to install it to a Hyperledger Fabric network, and once again we can use the Composer binary, the specific command here being composer network install. When running this command, the arguments will not only include the BNA file, but also a pure admin card. Now that our network has been installed to Hyperledger Fabric, we will need to explicitly start the business network. And the specific command for that is composer network start. And once our business network is up and running, a network admin card will have been created. And as a final step to start up the network, we will need to import this generated network admin card. And the command for that is composer card import. So clearly there are a lot of steps involved in deploying our business network over to Fabric. For the next task in the exercise, you needed to describe the boilerplate web application which is available to interact with a deployed Composer network. The web application which is available for us is built using AngularJS, and we can set up this tool on our own machines by making use of the Yeoman tool. The specific command which you can execute from the command line is yo hyperledger-composer :angular. This will download a web application with default implementations which we are free to extend according to our own requirements. This app is structured as a collection of interconnected components, and there will be separate components for all of the participant types in your application, for all of the different assets, and also for the various transactions which you have defined. This web application will make use of the Composer REST server. So it will be interacting with the business network using REST calls. And when you're setting up this application using Yeoman, you will need to specify the location of your REST server.